After which in 2012, he shifted to Hepai National University for Physical Science at the Microscale University of Science and Technology of China and as a postdoctoral fellow under Foreign Expert Joint Program of India-China Government for Advancement of Scientific Research. In 2017, Dr. Shirolkar shifted to Tamkam University, Taiwan. His research interests range from functional nano-oxide, polymer-based nanocomposite and biocompatible functional material. Dr. Shirolkar is associated with SCNN since August 2018. So I request Dr. Mandar to please join and start the session. Dr.
Yeah,
Mandar, welcome you, sir.
yes, yeah, thank you very much. First of all, good morning, everyone. Thank you, Professor Smita Acharya, Madam, for giving me opportunity to talk. I remember 2 years back, I delivered a series lecture on the topic which you asked me to deliver on the computer-assisted data analysis. Now today I'm giving the presentation on some other topic on which I'm working, and I would like to add one more point that currently I'm also working on the drug delivery applications of nanomaterials, and at present I have two industry projects based on the same drug delivery topic. So I have expanded my vision from the ferroelectric materials to something else also.
Good, good, Mandar. Okay.
Yeah. So I want to share the content. So I'm sharing the content through the Google Drive. Just wait. Actually, on my PC, but the WebEx is not working. Hello.
Mandar,
Yeah.
I have make you presenter and you can share there, but we have not seen your screen.
Yeah. I'm sharing the screen through. So hence I'm presenting through mobile. Just wait. Yeah.
Okay,
Now
okay, okay.
my presentation is now uploading. Just wait.
Okay. Yes, yes. Now we can see the your screen. Yeah.
Yeah. Just wait. It is loading.
The screen is still not visible. My screen, your presentation is not visible. Yeah. Now it's opening. Now it's opening.
Yeah. That is tunable room temperature magnetoelectric theory PF nanocomposites. So the outline of my talk is what is multiferroics, multiferroics and magnetoelectric oxides, magnetoelectric effects in BiFeO3 PVDF nanocomposite. Now I will go details of actually the multiferroics, and since we all are listening to this concept since yesterday and today, Dhiren Pradhan give excellent lecture on the same topic. However, in brief, it is defined as the material which exhibit more than one primary ferroic exhibit more than one primary ferroic order parameter simultaneously, that is in the single phase. So it could be ferroelectric, ferroelastic, ferromagnetic, ferroelastic, or the ferromagnetic, ferroelectric. Now coming to the main topic, the multiferric and magnetoelectric oxides. The multiferrics are considered to be a rare because the magnetism and ferroelectricity required entirely different criteria for the materials. Several oxides exhibit the magnetic and electric order parameters and display a electric properties. For example, magnetoelectric, for example, BiFeO3. The however, magnetoelectric property of this BiFeO3 in nanoform or in bulk, it is very low. It is something around 0.15 milliwatt per centimeter Oersted. But if BiFeO3 is combined with piezoelectric or polyvinyl, then we can achieve the excellent magnetic property in nanocomposite. What we have done is we prepared BiFeO3 and then we mix it with PVDF and we prepare a composite film. The slide represent the SEM micrograph of the BiFeO3 PVDF nanocomposite. And as we can see that the films are flexible as well as they are nearly transparent, depends on the concentration of BiFeO3. Now, further, as we go on increasing the BiFeO3 concentration, what we observe is the surface roughness is increasing. Okay, so it's the structural measurement of this nanocomposite, and these structural measurements are performed at the Photon Factory Indian Beam Line, and what we observe is 100 plane of BiFeO3 and 110 plane of PVD. They are affecting during the nanocomposite formation. So here I have shown pattern which are means the diffraction pattern is taken at room temperature, and simultaneously the electron density analysis of the particular lattice BiFeO3 and PVDF combination and electron density analysis. So further, what we did is we perform the magnetic and ferroelectric measurements on these nanocomposites. In this slide, I have showed the how the BiFeO3 and the PVDF lattice are combined together, and how they are interacting with each other through electron density interaction. On the I have showed the ferroelectric property and magnetic property of these nanocomposites. Now, as we increase, means the what we obtain from the ferroelectric and the magnetic measurements, they are as follows. So what we observe is the magnetic and increase the filler concentration, that is BiF3 concentration in PVDF matrix. Now, so perform one measurement called as a magnetoelectric measurement. So in magnetoelectric measurements, the information is given over here. So it is complex mathematics, but what we perform is we poll the samples and then simultaneously we applied magnetic field to it, and then the magnetoelectric measurements were performed. And these measurements were performed during at my postdoctoral station in the collaboration with Chinese group. And what we observed is actually here in this slide I have showed the magnetoelectric loop obtained on the BiFeO3 PVDF nanocomposite. I'm sorry, on the right side there is one graph. It is the magnetostriction graph, magnetostriction and piezomagnetic measurement graph, but it is not visible. Is it visible to others?
Yeah. That's magnetoelectric property, no? BiF3 PVDF
Yeah,
nanocomposite
BiFeO3
graph.
PVDF.
Yeah.
Yeah, nanocomposite. On the right side there is one.
No.
Visible.
We can't
Yeah,
see it.
yeah, that.
No, we can't see it.
On the left side, what we observe is the noise electric property of its nanocomposites. So the concentration of a BiFeO3 in PVD matrix, we obtained excellent magnetoelectric effects. And further, what we observe means the graph is not visible here. But, we perform the magnetic measurements, and it's impressive the magnetoelectric property of these nanocomposites. So what we further we perform the measurement in order to see whether the material is actually can be applicable for memory applications. So we switch the magnetic field at particular time interval. It's the switching of the magnetoelectric effects. So here I have showed it for 1500 seconds, and it shows the excellent stability. And bottom side, the graph which is showed with the blue color, it represent that can be used for data storage, and you can resemble operation or the 1-bit data storage operation. So just on the this slide on the right side, I have showed the schematic how this material is acting for the memory or the magnetoelectric could be applicable for magnetoelectric memory applications. So when the sample is unpolled, so the electric polarization components are randomly oriented. But when we polled, then the components are oriented, and the material itself is having some magnetic property. So based on the electrical phenomena applied magnetic field, we can exploit its magneto applications. So coming to the conclusion, and so BIF in this work we have prepared BiFO3 PVDF nanocomposite with variable concentration of a BiFO3 nanoparticles. The nanoparticles show again ferroelectric and magnetic properties. The maximum magnetic was observed to be 5 millivolt per centimeter Oersted when BiFO3 nanoparticles concentration in PVDF. Now, I want to add one point that beyond 20%, the PVDF is losing its elastic property or the polymeric property. 20%. The nanocomposites show the time-dependent magnetoelectric switching property representing the memory applications. Now, compared to the previously known non-volatile memory, this magnetoelectric coefficient-based memory would have applications. For example, the ferroelectric RAM possesses while via polarization switching for but they are from without. However, the type application and to electrification does not require polarization. The writing of digital information requires a polarization which is very similar to FRAMs. While readout process is completed by simply measuring the sign of alpha, employing low magnetic field, and the induced voltage is evaluated across the two electrodes. Convenient reading operation compared to the which are available and magnetic and access memory which are available in the market. Now, further, I want to add one point. This is need or the generator of the order of 1 thus the single reading coil can be shared by for the memory information storage as well as retrievation as well as to retrieve the memory as well as the actually consumption for the for low power consumption for the high density memory applications. And this memory if memory this type of memory applications have potential of future smart devices such as self-bias memory devices, precision detection of a magnetic field, and the tunable microwave filters.
Thank you, Mandar, for very interesting,
Yeah, I
and
have
you had
completed.
trying to develop some smart material.
Yeah,
Only the problem is that you have a mechanical strength and all this. Have you studied this? Because I always face the problem of mechanical strength about this film.
yeah, we
So, and
studying
thank
that
you.
property. Uh,
Yeah.
I said that after 20%, the material or the PVDF is losing its physicochemical properties like elasticity.
Okay.
That's why we cannot go beyond
I
20%. But yeah, means this data is under review, and in that we have done some simulation work also, COMSOL based simulation work, which I have not presented here, but
Okay. And the second issue we always face is that during cooling, the
hmm,
polymer, in a case of a BIFU3, there is no problem, but the film of ceramic polymer, then pooling always the issue. So, have you faced that same problem? Yeah. Have you sort out? Can you give some tips to sort out this problem?
during uh, polling, of course. So that's why means we are trying to optimize this issue. So we face issue like the thing is all the sample, the polling was not coming properly. Means the magnetoelectric effect is not coming properly. So it also BFO3 or the filler and they are interacting. How uniform material there in the particular sample. So mixing is the main issue. So if mixing is proper, then I'm sure the material will show material can be poured at very material could be without any problem.
And then is another question from Soib Abbas. He asked
Yeah,
why there is a change in Yumi property with different BiFeO3 nanoparticles concentration. Any reason?
yeah. BFO3 is it is having itself some magnetic property as well as it is it has piezoelectric property and PVDF is piezoelectric material. So the combination using the BiFeO3 concentration. So the the interaction between the BiFeO3 BiFeO3 enhances as well as the TF is also enhancing. Electric effect is increasing, but it has some limitation because of a material's own inherent property. That's why we cannot go beyond 20%.
Okay.
Breaking means when we try to peel from the surface, then it was not coming properly. So between the magnetoelectric material and matrix, polymer matrix, they are actually important for this particular application.
So, any other question? There is no question. So, we should say the thanks to Mandar for
Yeah,
such
thank
a
you, madam.
interesting lecture. Yeah.
Thank you,
And
madam, for giving me opportunity to talk.
yeah, I know you are working there now. And okay, so now
So
we are
and
going.
this work,
Yeah.
just one thing. Uh,
Yeah.
this work I have done in collaboration with my postdoctoral professor, but the some we are trying to develop at symbiosis. So it is actually bulky setup, but we have few components ready with us, and a few electrometers are necessary to. So
Okay.
here
Okay. Once again, a
in
question is raised by Muddasir Rashid. Is there any basic difference between multiferroic and magnetoelectric material? Or criteria for explaining a material in multiferroic? Hello.
material means we will say the hello, yeah, the there are type of multiferric materials, type 1 and type 2, but to have magnetoelectric effects in the particular material, we have to have certain combination of cations. So be showing at room temperature, but there are some materials such as SMFeO3 which will not show at room temperature. So if you combine this PVDF FeO3, then we can have this effect in this particular material.
Okay, okay, Mandar. Now there is no question. So we here start the oral. In this session, actually, we planned the 3 oral talks, but we can't communicate them. Only the Anina Anju B. She is from CSIR National Aerofis Laboratories. Okay, so I invite Anina Anju to start her oral presentation. The time for you is 10 minutes for oral presentation. Anina Anju. Anina, okay.
Smita,
Yeah.
can you hear me, Smita?
Yes, yes, ma'am. Yes, ma'am.
It was disconnected for some time, so I could not because I can't see it. The video is not getting on.
Okay, okay. Now we can hear you, ma'am. Now I have started. I have conducted your session. I have started. Now it is a live presentation.
I was trying hard, but
Okay,
it is not internet for some time. Now I
okay,
can
okay, sir.
you can hear me.
Okay, okay. So Anila, you can start. Okay, ma'am.
Yeah. And
Hi.
then we will have one more,
Ha,
Satyanarayan Patel, Anina Anju. Okay.
Hello.
Anila, you can start. Ha.
Okay. Um, Today I'm going to talk about enhancement in the energy storage properties of lead zirconate titanate thin films with lanthanum and bismuth topping. So I will be covering introduction, experiments performed, results, and conclusion. We know that there are a number of energy storage devices available, such as supercapacitors, battery, fuel cells, dielectric capacitor, and electrochemical capacitor. But as we look into the energy storage devices, we can broadly classify them into two. One is those which are used for long-term energy applications, and the other is those are used for short-term energy applications. From the Ragun plot, it is clear that devices such as batteries and fuel cells are having high energy density, so they can be used for long-term energy applications. But to compete with short-term energy applications, such as in pulse power applications, the material should possess high power density, such as in the case of dielectric capacitor, for which the power density is 10 power 8 volt per kilogram. Also, the dielectric capacitors are having fast discharge speed in the range of certain microseconds to nanoseconds and high operating voltage in the range of certain kilovolts. So if we can somehow enhance the energy density of dielectric capacitors, we can extend the application domain of dielectric capacitors and we can bring in miniaturization of modern electronics. The same can also be expected from batteries and fuel cells by enhancing the power density. But the end product is not going to be as good as that of a dielectric capacitor because dielectric capacitors have additional advantages such as high thermal stability in the range of minus 50 degrees centigrade to 250 degrees centigrade and less complex physical structure compared to supercapacitors. and lower leakage current. So we know that dielectric capacitors are having a number of applications, but I would like to talk about only the energy applications of dielectric capacitors. So as far as the energy storage is concerned, the dielectric materials can be broadly classified into linear dielectrics, ferroelectrics, relaxer ferroelectrics, and anti-ferroelectrics. For linear dielectric systems, the polarization is a linear function of electric field. So all the energy that is stored during charging process can be completely recovered during its discharge process. But the case is a little different for nonlinear systems such as ferroelectric, relaxer, and anti-ferroelectric systems. For them, the polarization is not a linear function of electric field. So we have polarization, electric field hysteresis loop, and due to the remnant polarization, all the energy that is stored during this charging process cannot be completely recovered during its discharge process. So if we know the electric field dependence of polarization, we can calculate the energy storage properties of these dielectric systems. So with the mathematical formulations given here, we can calculate the energy storage density of these material systems. For linear dielectric systems, the energy storage is half epsilon 0 epsilon r e square. But for nonlinear systems, the total energy storage density is different from that of its recoverable energy storage density. The total energy storage density is the integral of EdP from 0 to Pmax, which is represented by the region shaded in green and blue. But the recoverable energy storage density is the integral of EdP, but it is from PR to Pmax, meaning that it is represented by the region shaded in green alone. So the energy efficiency of the material system can be calculated by finding out the ratio of recoverable energy storage density to the total energy storage density into 100%. Similarly, the power density can also be calculated with the help of this equation given here. Now we want to find out which of this material system is best for energy applications. So we have seen, as far as the energy efficiency is concerned, linear dielectric, ferroelectrics, antiferroelectrics, and relaxer ferroelectric systems are equally good for energy applications. But as far as the energy storage density is concerned, we have seen that relaxer ferroelectric, antiferroelectric, and ferroelectric systems are good for energy applications. But the material system is itself available in different forms, such as bulk, thick, and thin film. So as we move down from bulk system to a thin film system, the material thickness reduces and the associated material defect will also get reduced. This will contribute to the improvement of dielectric breakdown strength, which will improve the energy storage density of the material system. This is also verified with literature, and hence we have decided to prepare thin films of PZT, PLZT, and PBLZT. We have prepared these thin films in chemical solution deposition method, for which we have made use of spin coating unit. For the physical characterization, we have taken XRD, FESEM, AFM, and optical micrograph images. And finally, the functional characterization is carried out with the help of PE hysteresis loop, CV loop, with the help of a thin film analyzer. Now, from the XRD pattern, we have confirmed the peaks corresponding to tetragonal perovskite phase of PZT for all the thin films. From the FECM images, we have verified the formation of pore-free dense microstructure and uniform distribution of grains in PZT, PLZT, and PBLZT thin films. To verify the thickness of the prepared thin films, we have used profilometer and cross-section length SCM images. The thickness of PZT, PLZT, and PBLZT samples is 485 nanometer, 485 nanometer, and 500 nanometer respectively. Now, as we have extended the thin film fabrication of PZT thin films on 4-inch platinum wafers, we have taken additional characterizations on 4-inch platinum thin films. The AFM images of PZT film confirm crack-free and pore-free film with an average roughness value of 1.5 nanometer to 2.35 nanometer. We have also plotted the capacitance against voltage for our PZT thin film and compared it with that of a commercially available PZT thin film. We have seen that our PZT thin film has shown better peak values of capacitance and is almost symmetric about 0 voltage. Finally, the energy storage properties of the prepared thin films is calculated with the help of a polarization electric field hysteresis field. We have seen that the PZT thin film is having highest saturation polarization and remnant polarization value of 88 and 45 microcoulomb per centimeter square. As we have introduced lanthanum into the PZT structure to form PLZT, the remnant polarization value is reduced to 8.32 microcoulomb per centimeter square, and the dielectric breakdown strength is also improved. The further addition of bismuth into the PLZT system to form PDLZT thin film, the dielectric breakdown strength again enhanced. So in short, we have received a recoverable energy density of 15.34 joule per centimeter cube for PZT thin film and 24.13 joule per centimeter cube for PLZT thin film. Finally, the maximum recoverable energy storage density is observed in PDLZT thin film with a value of 27.86 joule per centimeter cube. Here, I would like to mention that minimum of 30 joule per centimeter cube is required for a material to compete with that of the output of a supercapacitor. So, from the results, we have seen that the maximum energy efficiency of 84.6% is obtained for PLZT thin film, and a maximum recoverable energy storage density of 27.8 joule per centimeter cube is obtained for PDLZT thin film. Our conclusion is that the prepared PZT thin film grown on PTTI SiO2Si substrate by spin coating chemical solution showed ferroelectric hysteresis with high saturation polarization as well as high remnant polarization. The high remnant polarization of PZT thin films diminished their potential in energy applications. The lanthanum modification on lead silicon titanate thin films induced relaxer behavior to the PZT system with reduced value of remnant polarization and hence have better energy storage properties. Bismuth doping in the relaxer PLZT film further enhanced the energy storage properties of PLBZT system, making it a promising material system for energy applications. This was a part of my PhD program under the guidance of my supervisor, Dr. Somadatta. And that's all. Thank you.
Okay, Anina, thank you for the nice talk.
Thank you.
Just any question from our participants? Any question from? There is no questions for you. Okay. So now the third, yeah, Satyanarayan is there. Satyanarayan Patel.
We can move.
Madam, yeah, madam, can you hear me, madam?
Yeah, I can. I can. Yes.
Yeah.
So we are starting Dr. Satyanarayan Patel,
Yeah.
and his topic is flexo-oblique elastocaloric analysis of lead magnesium niobate with 34 lead titanate single crystals. He is a mechanical engineer in Indian Institute of Technology, Indore. So we will welcome you, Dr. Patel. Please start your talk.
Yeah, Dr. Patel, we make you presenter. Yeah, we make you present. You can see the share screen. You can see the share tab.
Yeah, but I am unable to click on share is hidden.
No, we make you presenter. 1 minute, sir. 1 minute. Sir, can you see the share screen?
Yes. Now I can.
Now you open your PPT in share screen. Welcome, sir. Bashpiya sir is joined. Sir, welcome.
Good morning, madam. Professor
Yeah,
Smita
good
Acharya
morning.
and Professor
Morning,
Kamal Singh, madam. Good
Yes.
morning, madam. Pranam.
Morning. Ashirwad beta. Khali mere saath, and now I can see you. I'm so happy to see you.
Dr. Satyanarayan, you can start. We
Okay.
can see your screen. Yeah.
Okay, good afternoon, everyone. So I am Dr. Satyan Patel, and today I am presenting this flexo-elastocaloric response in PMN34 PT single crystal. So I would say maybe this is little bit less known, or I would say that we don't know that much about this flexo thing. So I just try to give some little introduction or something about this. So as we already know that we have this ferroelectric material which we are using for many applications. So because it is, I hope everybody know like why we are using those materials. That the problem. So and the main key point like to using this kind of sensor actuator that we have multifunctional coupling. So we have like polarization, strain, electric field temperature, all different kind of couplings are over there. So we can use for different applications. But sometime problem will come with its temperature. If we are going above the temperature, this functionality will vanish, right? So to improve those temperature, like we can either go for chemical modification or some other modification, change the composite or something. But here we are going for different strategy, which is effect is known as flexoelectric effect or flexoelectricity. So in flexoelectricity, what we are doing is generally in case of our like piezoelectric material, like because our ferroelectric is also piezo. So we are mechanical strain or mechanical stress to get the polarization. But in case of flux, so instead of simple mechanical, we are using gradient of mechanical strain. So what it means is, if I just talk about our simplest effect or simple piezoelectric effect, how I got the polarization or some voltage, I have this piezoelectric coefficient with my strain component. So this is case if I have just normal strain. But if I use a strain gradient, I don't want to go for this normal strain. If I have this strain gradient, then I use one thing which is known as fluxoelectric coefficient, and that is fourth rate tensor. So the case for this third case is second case I would say is here. So if I have the undeformed, if I have the material, which is the simplest case over here, central atom. Then if I have the uniform deformed, which is the first term, I would say normal piezoelectric effect. Then if I have the non-uniform strain or gradient strain, then the second term. So what is the advantage? So advantage for this second term is over here. The fluxo coefficient is fourth rank tensor. Our DC3 piezo coefficient is third rank tensor. It means we have to go for the non-centrosymmetric. But if I have a fluxo coefficient which is fourth rank tensor, so in principle it can be go for all kind of material. So whatever material, even it is centrosymmetric, non-centrosymmetric, insulator, everywhere this effect should be one. They say the piezoelectric is limited to non-centrosymmetric only, but the fluxo can be go in centrosymmetric also. So the strain gradient is inversely proportional to the scale, and the effect can be side. And this is the first effect where now you can say, okay, this is very small effect, right? Because in general case we get in some microcoulomb range, and this is nanocoulomb range. So effect is very small, but if we change the material, so nowadays like earlier this was very small with small fluxoelectric coefficient, but the experimental researchers are working in this direction, and they found that they have very high fluxoelectric coefficient. So this coefficient is very high, and we can go for more than this nano region. So we can come around like 10 to the power minus 8, or if you have very high strain gradient, you can even come to equal to your normal piezoelectric material. But then you have to go for very high strain gradient, and that is generally only be achieved in nano scale. So how we can achieve it is I give the example like either you have one kind of B where you are using some bending with electrode, and using those you can create some strain gradient over here. You can go either for twisting, you can go for the 4-point bending or 2-point bending, or the simplest case you can make it a triple ADG. Okay. So in this trapezoidal shape, if you apply the stress, obviously now I have the strain gradient. And using those strain gradient, I can go for my sensing equation or some piezoelectric or ferroelectric property. So now we will come to our main topic. So that is the kind of idea like what is the fluxoelectric effect. And now I talk about fluxocaloric. So using this non-centrosymmetric thing, I want to go for the cooling effect. So caloric means cooling. So from those case, I want to look about the cooling. So I choose like one trapezoidal shape of material and I applying some stress and I am this stress I apply with different thickness. So if I am changing the thickness of this trapezoidal shape material, I am getting, you can see the different polarization. Okay, the polarization is different in this case, and this polarization I want to know. Okay, using this polarization change, I want to find out what is my real temperature change. So I given some equation over here. So if I know this polarization, okay, P. So this polarization P is generally we got from this fluxoelectric coefficient with strain gradient. So for this material, I know my this fluxoelectric coefficient with temperature. I know my strain gradient and I measure this P. So here we have P. And using those P with this dielectric constant, I can get the electric field modes. So once I know these two parameters with temperature dependent, I can come over here with my fluxocaloric temperature change. And how it will work, you can see with side. So if I apply the stress, my material will become hot. If then it will be released this temperature to environment, it is coming to normal temperature. If I release it, absorb. So in this way, we can produce the cooling using the material. And for PM and PT, these are the data like here you can see. So first we need the dielectric data. So we know, okay, till here I have the, if I just say, okay, 425 Kelvin, before 425 Kelvin, I have the piezo effect. So I have the piezo plus fluxo. So here, before this case, before one this temperature, I have the piezo plus fluxo. But if I go beyond the temperature limit, if I just say okay here, so this effect, I would say if I am getting any kind of effect over here, they will only just because there is a no dipole remain. Here we have the centrosymmetric, non-centrosymmetric case. Here you have this polar nano region, and this region, even you are getting some kind of this strain, this polarization, or I would say some fluxoelectric coefficient, this data, it means it is completely fluxo. And all this data is we have taken by 3-point bendings analysis. So we have the one B, and on the B, as I said in the like here. So this kind of the case here, 3-point bending, and this kind of analysis, and simultaneously you can measure your fluxoelectric coefficient, your Young modulus, and dielectric. All three you can measure, and all three data is. So this your fluxoelectric coefficient, here Young modulus, and your dielectric coefficient. And using those fluxo, we can also find out the fluxo voltage coupling coefficient. And all this data is used for our fluxocaloric analysis. So we have the polarization, and using the polarization, we try to get out, okay, what is temperature change over there. So you can see it is really small because we are looking just flux of polarization. And at the transition where I have this fluid temperature, I have very high temperature difference. Then this range, I would say this range is completely due to just fluxoelectric effect. And these are the equation from where you can do. But now the question is come. So main key question is here when I am using this stress and I am looking the polarization. Or if I am using this stress, then I can use directly the strain, and using this strain I can get the calorie. So why I have to go for this polarization term or electric field? So if I want to go for this fluxocaloric effect, this is the general method which in literature the people are using. But my idea is if I am applying the stress, I can directly know the strain gradient. So why we cannot go for stress to strain gradient and calculate how much temperature change will be there? So that is here. So for that young modulus, previously I showed a young modulus, so I assume some stress level. Okay, for those young modulus, I assume different stress level, and using those stress level, like you can see over here, I assume different stress level with young modulus. I try to find out this strain with temperature, and using those strain temperature data, I try to find out okay what will be my last effect and what will be my fluxo effect. So if you look over here, this is very high value, but the strain gradient is quite high. And the value of my last curve is 0.5 Kelvin only, but it is 80 megapascal. So if I reverse convert, if I convert this 80 megapascal over here, which come only just 10 only. So 10 meter inverse strain gradient. So 10 meter inverse means my cooling is in millikelvin.
Dr. Satyanarayan, you just
Yes.
conclude because we're going out of time.
Yeah. So I have last slide. Last
Yeah.
slide.
Okay.
So this is the case. Like it means what I want to say over here is, if I have the fluxocaloric temperature is this one, and I have the elastocaloric is this one. But if I compare both for the same strain level, I have the only just elastocaloric contribution, no fluxocaloric contribution. So this is like first time I try to figure out, okay, it is really kind of the polarization effect or it is due to strain effect. So the both measurement or caloric is we find out in single measurement. Okay. So to confirm this, we need obviously some experimental data or real time experiment because I just did the indirect estimation. But from all this analysis, I figure out that it is just elastocaloric effect, but people are using more than fluxocaloric. So still if somebody can look more detailed. So that is the whole analysis of. Thank you.
Hello.
Yes. Yes.
And some question we asked.
Yes. Yeah. Sure.
I have a question for you.
Yes.
You are talking about 66% lead magnesium niobate and 34 lead titanium.
Yes.
Did you check about the other compositions and the stoichiometric effects?
Thing is like from literature I found out okay this has a quite nice this uh, fluxo coefficient. So I just looking from the literature which composition has the good fluxo coefficient and I just pick up that.
Dr. Patel, can I ask one question?
Yes.
See, you were saying that it is a force-rank tensor, and
Yes.
if flexoelectric effect is a force-rank effect, and it depends on the size of the particle. At
Yes.
micron size, the effect is very small. So, have you correlated with the size of your composition, whether this effect is enhanced by decreasing the size of the composition?
No, you are right. I did not change any thickness or something, but in literature, like during those first principle and all those, it is already they established this relation. But I did not check it. But from literature, it is well known.
Okay, and second important thing is whether these cycles are repeated or only for a single Curie temperature cycle you have seen the effect.
Yes, that is a very good question because as I said, this is indirect measurement. So until or unless I don't have direct measurement, it means I just took the data and using equation I predict that this much temperature is available. Until or unless we don't do experiment, I cannot comment on it.
Okay. Sir, Bashpiya sir, are you okay
Yes.
with his answer?
No, it's not actually what I am worried when you are putting the pressure, 5000
Yes.
per meter strain you are putting, so this may be the excitations that are done mechanically. And if it is not repeated, this large number is slightly dubious in my opinion, because all these switching materials need to be verified for how many cycles the effect is stable. Because otherwise
Yes.
this localized polarization effect might be contributing, and that will be a extraneous effect.
Yes, I completely agree. Like we have to do the fatigue study. Then only we can comment like how much cycle it sustains.
Thank you.
I agree. Excuse me, I agree with Professor Vajpayee, because the particle size and the elastic properties are very much related. Stress and strain.
Yes, yes.
Over the particle.
Yeah, yes, so then I agree with both of you. That's why I also written like for the validate, we need the real experimental data. So in conclusion, I already written that this is just indirect way of estimation. We really need direct measurement. Only we can comment that really it will work or not.
Is Praveen Kadne, you want to ask? Praveen Kadne?
So
Okay.
I think if there are no questions,
Yeah, madam, you conclude the session so that we can start next session. Yeah. Kamal Singh, ma'am, you conclude the session.
yeah, that is what, because you said somebody is asking questions from me. So we can conclude and we can thank Dr. Patel that it's a very open field, as Parmendra Vajpayee is saying. And for a student, lot of things to be taken on the experimental, care has to be taken, and reproducibility has to be taken. So I thank you, and I'm very grateful for getting this invitation to share the session, and extremely sorry for in between getting disconnected because I had lost interconnectivity connectivity. So I'm very sorry for that. And all these speakers were very good keynote speaker, and I enjoyed the talk really, specifically on lead free to ceramic, because it is needed, and looking at the lead poisonability. So thank you very much, Smita, and I'm very happy to see Parmendra after a pretty long time. Thank you so much. And I thank all the participants and all the speakers of today. Thank you so much.
So thank you, ma'am, for conducting this session. Actually, now I start. There is a time for our next session. So we skip the tea break and we start the next session, session 9. It's a fundamental of dielectric, ferroelectric and related material. The chairperson of this session is Dr. P.K. Vajpayee. So just I introduce the P.K. Vajpayee, sir. Sir is professor and head Department of Pure and Applied Physics, Center in charge, National Center for Accelerator-Based Research, Department of Pure and Applied Physics, head Sophisticated Analytical Instrumentation Facility, Guru Ghasidas Vishwavidyalaya, Bilaspur. Sir had been the coordinator of National Knowledge Commission Network Based Activities, chairman of Core Committee Integrated University Management System in e-govern initiative of the university from 2012 to 2017, coordinator or director of IQSC from 4 to 18, coordinator of National Center for Protection and Preservation of Endangered Language from 2013 to 2018, has many noteworthy achievements and honors to his credit. He established National Center for Accelerator-Based Research. Sir hold distinguished position in many statutory bodies in various universities. He has got the award Board of Director for Research, American Biographical Institute, USA, and sorry, is Board of Director for Research, American Biographical Institute, USA. He is recipient of INSA Costed Visiting Fellowship in 1992, SCRC Visiting Fellowship 1995-96, and his PhD thesis was selected as one of the 6 best research work in solid-state physics at national level in 1987. Sir holds distinguished position in many statutory bodies of various universities. He has great contribution to the Guru Ghasidas University, chairing many committees. Sir is the editor of more than 30 international journals, published about 285 research papers of national and international repute. 15 research scholars completed their PhD under his supervision. Sir has guided 33 MPhil students. He has completed 17 research projects funded by CSIR, DST, UGC, DAE, organized over 30 international national seminars and conferences. Member jury for Young Scientist Award in IIPS conference 2001, 2, 2002, 3, 2003 and 4. His research and administrative contribution are countless. So we are glad to have you, sir, as a chairperson of this session. And I request you, sir, to start the session. This session have one plenary talk, one invited talk, and 3 contributory talk. So I request Dr. P.K. Vajpayee, sir, please start your session.
Uh, Thank you.
Smita, can you tell me how to share before?
Yeah, sir. Yeah, sir. So please share as a presenter to Ajit Kulkarni, sir.
Okay,
Sir, we
great.
have shared you. You make your presenter.
Okay.
You can see the.
Okay, Professor Smita Acharya, for a very exaggerated and nice introduction. And I feel privileged to be the part of NSFT, and especially grateful to the organizer for providing me this opportunity of sharing this session, in which we have one of the very exemplary speaker as the plenary speaker and invited speaker, Professor Ajit Kulkarni and Professor K. Srinivasan, a very good friend of mine. Then we also have 4 oral presentations in the last. And before taking any time, I invite our plenary speaker number 4 of this conference, Professor Ajit Kulkarni, who has been the professor in the Department of Metallurgical Engineering and Material Science, IIT Mumbai. Before I invite Professor Kulkarni, let me give a very brief introduction of our plenary speaker. Professor Kulkarni is currently the Institute Chair Professor at IIT Mumbai. He obtained his PhD degree from IIT Kharagpur in 1984. He had been head chef from 2005 to 2008 at IIT Bombay, Vice Chairman JEE in 1996-97 at IIT Bombay, Scientist B at SSPL Solid State Physics Lab, New Delhi in 1984-85. He started his research as a senior research assistant at IIT Kharagpur from 1982 to 84. He has a teaching experience of more than 27 years. His research interest includes materials and properties, especially electrical properties of material and structure property correlations in ceramics and glasses. His expertise in impedance spectroscopy and ion dynamics in glasses, ionic conductivity, glass ceramics, polymer gels, electroceramics, dielectric ceramics and thin film, lead-free piezo, ferro, pyroceramics, nanophosphors, quantum dots, and on devices including gas sensors, batteries, especially sodium and lithium batteries, SOFCs, actuators, piezo sensors, luminescence, photobiology, and so on. He has completed around 18 research projects sponsored by DAE, DRDO, DST, MHRD, IFCPR, DST, JST, AICTE. He is supervising 9 postdoctoral PDFs and 6 PhD students. 20 students have completed their PhD under his guidance. He is author of several books and chapters. He has 3 patents granted and 7 patents published. He has about 150 research publications in peer-reviewed journals of international repute. He had been on several prestigious positions as a visiting professor at IMRAM Tohoku University, Sendai, Japan in 2005-2006, visiting professor at Augsburg University, Germany in 2004, Humboldt Fellow, Oxford University, Germany in 1997-98, postdoctoral fellow at Purdue University, USA in 1985-87. He is a fellow of Maharashtra Academy of Sciences, member of National Academy of Science, Allahabad. He is the recipient of number of prestigious honors and awards, including IIT Bombay Research Paper Award for the year 2012, Best Paper Award in around 10 conferences. He is the DIT PSRG member for National Projects Monitoring for Lithium Batteries and Superconductors at CMET Pune and Thrissur, Kerala. Academic member Center for Carbon Research, Bangalore. Member of Executive Council, Asian Society of Electroceramics. Member of Awards Committee, Indian Ceramic Society 2013-14. Secretary, Asian Society on Solid State Ionics from 2008 to 12. Member of Editorial Advisory Board, Indian Ceramic Society 2004-2006. He is the member of several professional bodies, including American Ceramic Society, Indian Ceramic Society, Indian Society of Solid State Ionics, Material Research Society of India, and his professional contribution and academic contribution to the field are enormous. And we are really glad to have such a exemplary plenary speaker. I invite Professor Ajit Kulkarni for his plenary talk. Professor Kulkarni, please.
Good morning to all. Thank you, Professor Bajpai, for this very generous and long kind introduction. As you said, I did a MSc in Nagpur, so that way I always feel good to be talking to people in Nagpur, and I'm very happy that my professors are there, Professor Kamal Singh, and other colleagues from when I was in Kharagpur, and also Professor Chaudhary, I think, is there. He was also one of the mentors at Kharagpur. So I'm happy to be in this conference, and I was also part of this national conference, which it was previously, I think, in 2004 or 5, something, or maybe before, I don't know, 96.
Hello, Ajit ji.
Ajay, namaste.
Arey, namaskar, bhai. I'm happy that I have seen you after a long time.
Yeah.
Sir,
बहुत अच्छा लगा.
चौधरी सर प्रणाम.
नमस्कार सर, नमस्कार सर, नमस्कार. जय हो सर, जय हो. अरे वाजपेयी जी
सर प्रणाम.
अरे सर, मैं कई मैसेज भेजा, लेकिन आपसे बात नहीं होती है ना मैसेज होता है. क्या हो गया?
सर की गलती हो गई.
नहीं, कोई प्रॉब्लम है क्या? मैंने नहीं आपको
नहीं सर, मैं काफी समय दिल्ली में था तो वहां देख नहीं पाया.
अच्छा. नहीं, हम कहा कि शायद मोबाइल में प्रॉब्लम होगा, इसीलिए आई वाज गेटिंग वरीड.
There was a personal function at home, so for 15 days I was at Jhansi and then I went to Delhi.
नहीं, आज के जमाने में कोई मैसेज नहीं मिले से चिंता हो जाती है ना सर. नहीं, जो समय खराब है ना, इसलिए चिंता होती है. हम लोग एक दूसरे से समाचार पूछते रहते हैं ना, सब लोग ठीक है कि नहीं.
सर, आपकी ब्लेसिंग से.
जय हो सर, जय हो. मेरे भाई की जय हो, मेरे छोटे भाई की जय हो. अजीत जी प्लीज. हाँ, अपना काम शुरू करिए सर. जय हो सर.
जय. अभी ये शेयर करना पड़ेगा. स्मिता के लिए. हाँ. I think I also sent you. Is it okay? Smita?
Not yet, sir.
Sir, have you got a share tab?
I don't see.
Share tab is there. Share tab. Have you got a share tab? Because we make you presenter. Now you got a share tab. Just on below your screen, just see the where there is a sound control, video control. There, just of the neighbor of this tab.
All these 3 controls I don't see. Even sound, video, audio also I started from the right panel.
सर ऐसा करिए, थोड़ा अपना कर्सर जो है उसको होंगे लैपटॉप में कर्सर को थोड़ा नीचे लाइए.
नहीं, फिर भी नहीं आ रहा.
There is share tab. Okay. Because after making you presenter, you can see the share tab, and it is just below your screen where our video is our WebEx video. You observe our WebEx video. Sir, have you observed WebEx video?
I can see your name. You are speaking. This layout business.
Yeah,
Some
yeah,
problem.
yeah.
Exit full screen. Okay, I exited full screen.
Yeah, yeah.
Or you do it. I sent you a mail in my file in your mail.
Oh, I
Okay,
show
that is also
your
possible.
file and you just okay. 1 minute, sir. I will
Earlier I
see
was
that
able
file.
to see. Why I can't see now?
Yeah, yeah.
I got it. I got it. Okay. So
Okay,
I'll
okay.
share.
Okay.
Share. So I have
Yeah,
shared.
share.
Now this is
Yeah,
doc.
yeah, yeah. You, yeah, yeah.
Now
Yes, sir. Yes,
it
sir.
is
We can
come.
see your screen now.
It,
Yeah, yeah.
it is coming.
Okay, now I will make it full screen.
Yeah.
Okay.
Yeah.
I think
Yes,
Right.
yes, sir. It's okay. Okay, sir. Okay, okay, right.
Okay. Now
Huh.
only one screen is coming here on the side. Okay, doesn't matter.
Yeah, you just have to press the down or up to change your PPT.
That I will do. Laser point.
Okay.
Okay, good. Everything is
Okay.
fine now. Okay, so good morning
Yeah.
again, all of you. Though I did not attend all the lectures the last 2 days, I saw the program, and of course there are many speakers before me have introduced this area very nicely, and for the young audience, many tutorials have really helped. Okay, and many of those things now have covered the required physics to understand the piezo ceramics and applications, the chemistry, probably to make how to make these materials. So I thought that I will give a bird's eye view of a materials scientist. Now that I do mostly materials of various types with focus on electrical properties. So I thought that I will talk about the materials, the overall bird's eye view of the piezo ceramic material. And in my view, even if we do right chemistry as well as the physics to understand the structure of this material, when you want to utilize this material or these materials in a given application, that also demands certain external processing of the material, which makes it or which enhances the properties and makes it an optimum material for the given application. So what I'm going to do today is essentially giving this material scientist viewpoint on what to do this material, how to make and process them, etc. Of course, initially with a brief introduction of the fundamentals and the applications that are there, which we essentially are interested in trying to exploit. And then the physics factors which are important for piezoelectric coefficient, and what are the materials factor that if I apply to a given system will let me improve the properties of the material. So for that I have chosen a system which is the niobate system. Okay, so sodium potassium niobate and combination of potassium niobate. That is because there are a number of PhD and postdoctoral students who are working on these topics, and therefore I have some data to show you. And looking at the synthesis and structure, we will see what additional optimization is required. And after doing all these things, we got the material and how we have tried to use these for certain applications, which are either piezoelectric or magnetoelectric, with a combination of the ferrite, which my friend Dr. Venkatramani had been doing for last 20-25 years at IIT Bombay. So we combined our expertise and tried to make the devices out of this. Okay. So to start with the fundamentals, don't worry about it's a IIT lingo that we use. So you have done in the tutorial what is a direct piezoelectric effect. Okay, so when we have an impact on a piezoelectric material, in the output we get an electrical impulse or pulse or voltage that is developed. and therefore, when you have a polarization in the material, because of the force, you get a potential. And these are the equations which essentially tell you that the displacement that we get in the material is related to the piezoelectric constant of the material and the stress that we apply in the material. The converse is also there. Okay, and in this case, when you input an electrical signal on the material, you have deformation of the material or the change in shape and size of the material, and that essentially leads to strain in the material, and that strain is again proportional to the piezoelectric coefficient of the material, which is converse. So in this case, suppose we take only one coefficient, we call it D33, which is the picocoulomb charge developed per unit area, whereas in this case it will be strain, or D33 star, that is the displacement per unit voltage that you apply. So therefore, by either applying a stress or giving an electrical signal, we can change the way material behaves, and therefore can exploit it for certain applications. Now, before we go into the materials, macroscopically, what we see, even this, I think somebody discussed yesterday about the hysteresis loop. Okay, so the same relations I have put here. Macroscopically, if I look into a material, I will look at the polarization, that is displacement, as I told you before, polarization as a function of the electric field that I apply. Conversely, I will look at the strain which is developed in the material as a function of applied electric field. Okay, and this is what is also called as butterfly loop when you cycle it in all the four quadrants. Okay, like the hysteresis loop, you also have a butterfly loop that you get here, and you have to also remember that this superscripts essentially mean the T means the mechanical stress, and the strain means the electrical strain, which you either keep constant or measure depending on what you are trying to do. Similarly, since you are going to use this material and material for various application, it is going to undergo deformation, the change in the shape of the material. If you take linear, then you can say it is going to expand, or we are going to make it move, and then it will move back and forth, and therefore the mechanical behavior of the material is equally important. Okay, therefore the stress versus strain curve for all these materials is also important, and that is what we call as the ferroelastic elasticity, or you can say the domain switching. I don't want to get into this theory right now. Okay, so macroscopically you look at this butterfly loop, the hysteresis loop, and also how the mechanical hysteresis looks like in this material when you stress strain curve changes. So if we have these three curves, and if I want to use this material for certain application, however, what is important is the portion of the hysteresis loop which I have shown here in red. Okay, that essentially gives you the total delta P that you are going to have, the polarization that you are going to develop, and this value we call like the saturation polarization. So this curve from the polarization from this to this point till saturation is very important. Similarly, if I look at the butterfly loop, then the delta S is very important. And therefore, we operate the devices in a unipolar fashion. That means we'll go from this, say, 0 to +5 and +5 to 0, or any other value that we have. And we are not going into all the four quadrants during application. And therefore, when we are going to develop the material, we have to make sure that these are properly optimized and you get the maximum values for this red line that I have shown here, that is the saturation polarization, and the maximum that you get in terms of the strain, and therefore I will be able to use the material in an actuator. And that is why what we want to work with. So what parameters, or when you develop the material, what properties we essentially need for various applications is I have briefly shown here. Okay. So if you decide to work on pressure sensors, try to maximize D33. If you are using for micro positioning system, which are used in these microelectronics, people to move the move the mask and draw the lines on the or make the various electrical elements on the IC chip. Okay, in those cases, you want large strain, because then with the smallest possible applied electric field, you will be able to push it larger and make various circuit elements. And as far as possible, the hysteresis should be minimized over a large range of field that we are going to apply to move it for a longer distance. In the high stroke actuator, such as a fuel injector, okay, in an automobile, which is one of the most important discoveries people had in Germany, that led to new materials as well as a lot of job easing, because so many jobs opened up after that. So that saves your fuel. So the air to fuel ratio can be controlled by this actuation when you press on the accelerator. Okay, and then of course for many other applications, or in general, you want a large delta S by delta E, that is D33 stars in the material, low loss, minimum loss of energy, and widely stable temperature range. So with these parameters and all, if you develop for various different materials, so what you see a huge number of applications which I have tried to put in this complicated figure here, and all these typically are the industrial applications of this material. Okay, you have pumps, you have robots, you have biomedical sensors, and then of course each of these can be classified as actuators, medical sensors, energy harvesters, tactical sensors, and so on and so on. So each one of these is very important and essentially uses the characteristic which I showed in the previous slides, okay, and the physics which is involved in this. However, if you look at the day-to-day applications, the day-to-day applications which we see almost every day we use printer head. The printer head has a piezoelectric effect. Then camera, which does an autofocus, that also has a lens which is called as this USM. Then this mobile speaker, we don't see any hole in the mobile screen, okay, but we are still able to hear because we have these piezos and the vibrations and electrical conversion and all that. Ultrasound, then the catheters are easily put if you have these materials. Then you want to clean something, so ultrasonic cleaner. And then of course the most important thing is the automobile, where you have the NOx sensors. Because of the pressure, you can develop signals and you will know there is an obstacle. And similarly in the parking lot, when you want to park your vehicle, you use these rear sensors, so that you do not have any obstacle there. And finally, when we walk, we want to use this pressure, okay, or the force of walking on the piezoelectric material to convert it to power. If I'm correct, I think there was a news, and it may have, I have not gone to Nagpur railway station, but I understand there is some part of the Nagpur railway station, I think in the lobby, they have the mats with piezoelectric, and they use this generated power for the electrifying that area, the reservation counter and whatever that they have. And this was one of the startups which was there in Nagpur, engineering college students had done. So I'm very happy about it. Okay. Now, so when all these things are there, then how do we achieve this? So therefore comes the materials person, and then materials person says, if I have to exploit all these things, I need to look at the parameters which I showed before. and the best material which will exhibit this very easily and of course at a much lower cost. So the one single material which has outshone many others so far is one PZT, okay, lead zirconate titanate. This material is very widely used in all the industrial applications that I have shown. Okay, of course, there are exceptions like NBT, which is used by one of the automobile companies in the front part, that is the engine and somewhere. And these are the general properties that we expect for this material to be successful in all such applications. Of course, what is the interest of a materials person? The materials person, of course, is looking at physics, chemistry, as I said before, how to make material, the correlations, etc. But he's also interested in developing technology because there is a world market. There is money. And if you look at the global piezoelectric device market, okay, materials, devices, automobile, ultrasonic, and all that I have shown on the left, in 2020, the world market was US dollar about 30 billion and is expected to be about 34 billions by 2025. That means the market is growing typically at 3.5 to 4% per year. And therefore, that is an added advantage for the materials, engineer, technologists, and all other interdisciplinary people who come together as materials person and engineers. They have interest in this material. However, as I said, the only material which is dominating this almost 95 to 96% so far, other than their composites, etc. Okay, I mean all put together. Only one phase if I talk about, then PZT is the material, and this PZT, as all of us know, contains lead, and this lead is so bad as I have shown here. We just take a human being, and in the human being, these are the various parts of the body where the lead will go and settle or precipitate or stay, and then will mess up with the whole function of our body. And therefore, it is one of the dangers of this better material, which is on one hand, it is giving you a good lifestyle because there is no shock in your vehicle and so on and so forth. It is also giving trouble. And the worst part is, it is not only during manufacture of this material that we get into this trouble, but even during disposal of the material is equally bad because it gets into environment and so on and so forth. Okay, so the recent UNICEF report I read recently, and it is titled "The Toxic Truth: Children Exposure to Lead Pollution Undermines a Generation of Potential." It's a lot of problems that create for this generation and these young children who are enjoying. Some of them essentially get into deformities because of the lead. I think recently, maybe last month or a couple of months ago, in Hyderabad, there was a big issue with the health of the children because of lead. Okay, so I think we have to be cautious, and we need to, as far as possible, avoid these things. So just as a side remark, even the chili powder contains lead. Of course, we are not going to stop eating it, but it's just one reference that I have. All right. So what we should do? We need to avoid this threat to our environment and our own self, and therefore we think change the strategy. We must change the strategy of trying to avoid using the lead in lead-based materials while achieving the same value which this wonder material PZT is giving. It is kind of a challenge that the materials people took up all over the world and have been working for quite some time in order to mitigate the use of lead and get the materials which are as good as PZT. Okay, and with that, starting with barium titanate, people have started making various different kinds of material, and that's where we are today. And of course, in our own small way, we are also trying to contribute looking at this system from the academic point of view. Now, while trying to replace this PZT, if we have a close look at the science and technology and ceramics phase diagrams that people have developed, we have to note 2 points. That if you want to get the best of the PZT was available around this composition, which is called the morphotropic phase boundary, where these 2 phase boundaries coexist, that is rhombohedral and tetragonal. Okay, and of course this is the temperature. So as a function of composition, you can tailor these boundaries, and that is where you get the maximum in terms of the properties. And therefore, you take a cue from here and see if we can have systems in which we achieve the same morphotropic phase boundary. We will get better properties, or properties closer to PZT. There are some others who argue that instead of trying to make and always look for this boundary, morphotropic phase boundary, where you get an abrupt, say, rhombohedral to tetragonal phase transition, whether you should look for a composition versus the polymorphic phase boundary. Okay, where there will be over a range of composition, you might get this. So there are various different ways people try to achieve the maximization of the coexistence of such phases, and hence get enhanced dielectric, piezoelectric properties, and of course the temperature stability, like it is shown here. Okay. So with this, you dig into the literature, and then you see that the whole world, almost the whole world, is working on the piezoelectric materials these days, and that at least is an indication from this list of publications that people have. Okay, and all these which I am talking about are the lead-free materials. Okay, and a peep in the literature tells you that in 1980, first time it was discovered, and since then we came to World War time. Then you got this barium titanate, or better, okay, though capacitor-based material for in the World War itself, but then subsequently more and more of scientific knowledge base was developed for this material. So barium titanate became well-known material for us. Then came the Jaffe. There you got this PZT. Okay. Then this potassium sodium niobate in 59, and all those things. So you also got another good material, BNT, or which people discovered in the 60s. Okay. But after all these things, we have started emphasizing now very heavily on ROHS, which I just now discussed. And therefore, if I look at only the materials and their properties that we have developed, you will see that not every property is closer to PZT, but various different important systems which are developed do show fairly high D33, say 300 here, or 750 barium titanate, modified barium titanate, textured barium titanate, and so on and so forth. So you are in a position to get a range of D33 and a good value of strain, 0.7 in this case. And therefore, if we do a combination, or if you want to use a particular ceramic or a material for only D33 application, we can do that. But if you want looking for all the properties of PZT present in the material, I think it is not achieved yet. And then of course we are still on to it. Okay, so these are the materials which are there. Now, if I choose a material system, okay, any one that you take, or the list which I have given here, what other than the polycrystalline material, what else we can do on this to maximize these D33s with these materials? And these are the additional things that you can do. You can do chemical modification where you want to add 2-3 different things, okay, and get this material where D33 varies from up to 600, okay, in BZT, BCT system, for example. So these are comparable to PZT5H, okay. So this material is quite attractive, and a lot of people have tried to use it with there could be some other difficulty in not getting the exact material properties that we are looking at. The other people thought that most of the PZTs are polycrystalline, and therefore the domains and subdomains which will essentially create problem in trying to maximize the properties. So texture the material. So essentially you try to align all these or use the polycrystalline grains are aligned in a particular say direction, say C, for example, in tetrahedral system along the C direction, and align all those grain during processing. So do a tape casting, add a seed. So seed will make sure, like shown here. So you start with powders, make the slip, add another seed, and eventually make sure that the seed and the material that you have is in the same aligned in the same direction. All the grains, what I mean to say, that means the material is structured in this direction. So it will be akin to or similar to a single pistol, and in that case you can maximize the D33. And this is what is shown here. If instead of a random polycrystalline material, if you try to increase this degree of alignment, the D33 changes significantly. So this is another way for the same material. Instead of using a polycrystalline material, use a textured material. And such things have been employed, or such this technique has been applied to all these materials, okay? And you have again achieved up to 500, 600, and so on and so forth. So that is another way a materials person tries to maximize the piezo and the dielectric properties of this. Okay. The other thing is phase boundary. So you are mixing so many different materials. For example, barium titanate, barium bismuth. I think I don't know what this compound is. Okay. Okay. So this compound. So this essentially shows you a point where the 4 phases, different things are coinciding. So this quadrupolar point, if you take, it has been seen that at this point, you get maximum polarization and maximum breathing. Okay, so like here, 700 is at this color, is 700. People also do a lot of simulation these days to figure out what kind of material they should use to do this. There is one more important material synthesis and fabrication criteria, and that is the grain size. Okay, average grain size that you'll get in the material, for example, barium titanate, and that grain size decides what is the domain size. And of course, we know if we align the domains, the properties get maximized. So therefore, grain size is also important. So the grain size controls the domain size. Domain size also controls the dielectric permittivity, and the D33 can also be controlled or changed or varied or optimized using the average grades. So all these factors a material scientist tries to consider and do that. So some of these we try to use it into our work, okay? And we chose this material that is sodium, potassium, bismuth titanate. Okay, so now what I will do is to tell some of our results and how we try to maximize the properties of this material. So this is the 0.8 NBT, 0.2 KBT composition that I'm going to show here. And once you choose that, that is where you are going to have the rhombohedral and tetragonal as a phase boundary. Okay. However, the average structure that you are going to see here is cubic, though you have the presence of these T because of the MPB. Okay. So that is in the what I should say. If you see microscopically, then you will see that both rhombohedral and tetragonal is present. And why did we choose this? Because one of these is rhombohedral, other is tetragonal. Okay, and we try to mix it. Then the piezoelectric property D33 high, the remnant polarization is good, etc. And then the structure is very amenable, as we have seen in the last few slides as well as in your lecture. So we have this one of the octahedral cavity, one ion is jumping around. Okay, so that is giving you maximum polarization in this material, and the structure, of course, is perovskite with a c-axis longer depending on the temperature. Okay, so how did we make it? We made it with solid state route. These are the raw materials, and these are the calcination and sintering parameters. And when we did this, we got this 97 to 98% theoretical density. So how did we decide on this? So we essentially, so actually as a materials person, we do everything. We don't normally try to look at only parameters from the literature, but we did our own TGA because we had these raw materials. They have to essentially get into oxide, then react, and a reaction has to be initiated. So we saw that the reaction states gets initiated somewhere around this point. After all these carbonates or nitrates or whatever you use, they break. Each of these steps matches with the loss that we see from here. So we make sure that mass loss is there corresponding to theoretical calculation of this, and correspondingly we see the temperatures. Okay, so somewhere here around 800 it is stable, constant. That means the material is going to consolidate, so the reaction is going to take place. So we started 800 for 3 hours at this temperature, and when we did X-ray, we did see formation of the phase. Then comes the sintering. Now, how do we decide where to sinter? Some people say the ballpark figure is 2/3 of the melting point of the highest oxide that you use can be taken, and so on and so forth. But we, instead of that, we this whatever pre-reacted solid state powders that we get, we make them into cylinders and do the dialectometry, that is thermal expansion as a function of temperature. And we see that since the material is green, okay, it will shrink. As it starts sintering, it will shrink, and the temperature where we get the maximum shrinkage is what we use as a sintering temperature for the material. Once we decide the temperature or find out the temperature from these results, we do an isothermal at that temperature to make sure that the shrinkage is maximum, and that is our the sintering temperature and time or parameters. And when we do that, we get about 97 to 98% density for the material. Okay, so these are the various sizes and shapes that we make because we are interested in devices. So we make long pieces, rectangular bars, maybe for harvester or actuator, some cylindrical thing for lighters, and so on and so forth. And of course for our measurements purposes that we do. Okay, so we also, I'm not going to go into detail of this, but we construct the master sintering curve using all this linear shrinkage and other theories. So essentially we will be in a position to tell the industrial person as to how to achieve the highest density in this material by controlling the heating rate, isothermal temperature, and the time. For many applications other than this, the grain size also needs to be controlled. So we build all those also into this. And when we do all these things, okay, this is the microstructure that we get. You can see how dense the microstructure is. You hardly see any pore when you on the polished or etched surface. We also do the fracture, and even in the fracture, that is inside the bulk of the material, it is very dense. There is no air pocket, so the dielectric properties are also going to be excellent. And those who are interested in ceramics science, these are the growth steps. That is not the topic today. Okay, so then you characterize the material to see what you aimed at is there. So you do the, of course, the X-ray to see the what kind of phase you get, and you get the material NKBT as you desired. You do a repel analysis to see if there is any residue, etc. And in this case, since this is a MPB kind of a composition, you have this model of P4BM, and this thing that is rhombohedral and tetragonal fits very well, and therefore we have a coexistence of this through the splitting of the peaks that we have here. We also do Raman spectroscopic measurement in order to see the various vibrations in various different structural units that we have. So we also see a TiO bond here, okay, and this TiO6 octahedra. Now, and of course some signature on the A side. Now this being an A side disordered material that we have chosen, the signatures are not going to be very perfect, and because of the disorder, they are also going to be broad and a lot of overlapping modes that we have. So we deconvolute all of those, and based on all those numbers and the structures on the calculation of the 7 different modes that we have, we use all those calculations and match the phase structures that we get from X-ray and Raman. Of course, later what we need is a microstructure. So we see a very good microstructure for this with an average grain size between 1 and 2 micron for this material. The density, I already mentioned to you, 97 to 98% is what we have outside. Then of course see the uniformity of the material. The material is quite uniform, so we do elemental mapping while we do the SEM and the EDS. And you can see that this is for the entire material and this is for the individual elements. All of them are present and they are uniformly distributed, no pockets, no grain boundary, no precipitation and all that. So are they going to give good dielectric properties and piezoelectric properties now? Yes. The polarization loop is perfect, okay, as ideal as we need. And these are the values that we get: 28 kilovolt per centimeter for EC, D33 star, that is the converse, that is picometer per volt is 640, very good. And the dielectric constant at room temperature also is very good. So the electrical properties are good because sorry, the material that we have developed from the fundamental materials principle is extremely good. Do we have the phase transition behavior in the material? Yes, indeed we have. Okay, so we have a transition here, which is the relaxer, and this is the ordered transition. Okay, that we see. Then we do this Curie-wise fitting to find out the various values that fits well. And since there is a heavy real disorder in this material, this diffuseness is essentially fitted with the quadratic fitting function, that is a modified fitting function. So diffuseness also you get about 103 plus minus 1K, higher than the lead base compounds, which is about 45. So we do all this physics that is required to find out the various frequencies, ZBs, the glass model that we apply. Okay, so this essentially the glass model tells us that we have a disorder in the system, and that glass model also fits very well to this system. The other thing that we see is the change in poling of the material. So if you have an unpoled material, you see a relaxer behavior here, which is shown here. Okay. But once you pole, there is the material converts into a ferroelectric material. So you get from relaxer to ferroelectric. So essentially you get into the ergodic transition that we see for this material, because this step now is not like this, it is a sharp step. So that essentially indicates that on poling, there is a small structural change that is, or you can say the order is changing. So you will ask me for a confirmation of this. So in order to confirm this as a function of temperature, we did high temperature XRD. Okay, and this is our dielectric constant versus temperature curve. that we have here at 1 kilohertz. So it's a very nice curve, and you see a good transition here or transition here, anomaly, whatever you call it. And this each color here and the arrow here tells you where we have taken the X-ray diffraction pattern at that temperature. And you can see that we have a 111 split here, okay, up to here. But when you go to this temperature, then you have 111, right? Similarly, if you look at the 220 peak in the previous X-ray diffraction I showed you, so these things essentially change. So what I mean to say is that extremely high temperature, what we have is a cubic material, and we see both 111 as well as 200. So we have done this, and therefore this step, loss of step after this temperature is clearly seen in this. Okay, so that was the, so one will say that is the best that we get in the electrical properties of the material, but we are still not happy. We still want to see if we can really get good optimum polling condition, so that another 5 to 10% higher values for D33 epsilon we can get. So we poll the material. We all know what polling is. So you align them in the direction. Now there is always one question: how do we understand whether the polling has taken place completely or not? And therefore, what we do is to do a resonance, anti-resonance technique, and we look at this angle. Whenever we have angle close to 90 phase angle, that means the polling is complete. And this we keep doing as we change the temperature as well as the field that we apply for polling. And based on that, what we have done is to optimize both temperature and the field at which the maximum D33 or D33 star can be obtained. Okay, so this was one of the additional things that we did, which not, I see only one previous report somewhere on some material. Other than that, people don't do it. So we did publish all these things, and quite appreciate. Okay, so finally doing all these things, this is what we got. We got good properties for this polling field at room temperature, and then these numbers are good: 193 D33, Kp 54%, PR 40, and EC 30. So that means the material is ready to be used as a piezoelectric material. Okay, and this is the other thing. This I'll avoid. Okay. And we also did the mechanical polarization properties on this material. The hysteresis loop, which I showed before, is ideal in this case also. And therefore, if I make an actuator out of this, this will work. Okay. So all these mechanical numbers also are very good, obviously because the density was very good. So then we looked at the application now of this material, and we tried to look at the electrocaloric effect. That is, we know that the material is disordered when E is equal to 0. And when I apply higher field, when I try to align them, so I am getting the system to essentially minimize energy from thermodynamic point of view. And if I do it at adiabatic temperature, there will be heating or cooling depending on whether I order them or disorder them. Okay. So with this, so this will be similar essentially to the refrigeration cycle, that is the vapor compression cycle. So therefore, if you generate a potential change in voltage as a function of applied electric field here, because of the order disorder, I will get delta T either positive or negative, and therefore I will get the heating or cooling. And this is what essentially we have done. We have, of course, I should say we applied the Maxwell's relation to do all those things. Okay. So we have the function of temperature, these loops at each field, you take the slope, okay, that is from here, delta E, then you will get at adiabatic temperature. So, and you integrate, and therefore dP by dt, if you get from the slope here, then you will get the delta T, and that delta T we have seen, depending on the field, the value that we got maximum for this blue curve at 20 kV per centimeter is about 2.5 Kelvin difference in heating as well as cooling. Okay, and we did further calculation. So this is one new application that we have in mind for this material. Of course, one has to do a multi-layer device probably, because 2 degree will not be enough. So you go on making multiple things and you can do that. And from these curves, which somebody showed before also, we calculated the energy, and we the energy for recovery and the total energy ratio that essentially gives you the efficiency of this storage, and that this should have been eta. Okay, so I did convert it into symbol. So the efficiency is the ratio of this, and which is also pretty good. The other application is magnetoelectric. I will not tell you this. So we are interested in making the magnetoelectric laminates composite, because in a single phase material, the voltages that we get are magnetoelectric effect that we get is little less, and at two different temperatures are widely apart. So, but in a composite, you get better signals, and therefore we are interested in trying to make this. So between two ferromagnetic material, we sandwich the ferroelectric material, and these are the signals that you will get in this. So this is one of our application. So we chose nickel ferrite, okay, which is an inverse spinel, and the magnetostriction also there is very good, as shown here. This is the work of Professor Venkatramani, who had been working on this for a very long time. We made the bi and tri layers of this in the bulk form by using silver as an epoxy to attach these two layers, and then we studied the alpha, and we found that alpha is about 30 ppm, which is quite sorry, lambda, not alpha, lambda. Okay, and these are the interfaces. You can see there is a nice interface between the two different ferroic materials with a silver epoxy, and this is bilayer, this is the trilayer, and obviously in the trilayer we got the higher values. This is our setup that we made ourselves, and all these measurements we do. The values that we got for the trilayer, about 86 millivolt per centimeter roasted, fairly high. Of course, one might say that you should compare with terphenol and all that, which are very, very high. But we'll get there, because we are right now using only these materials. The other thing that we have initiated on this is to make NKVT thin films by laser ablation. So we use PhD. These are the parameters. The substrate is silicon, platinized silicon, okay, with SiO2 on that for a better adhesion as well as integration into the circuits. We optimize the deposition conditions for this, and this is our setup for the PLD. We have characterized all this film, okay, and we do get the single phase in this material. We did a cross section. So we see the silicon layer, this platinum titanium coating on that for the adhesion, and then very clearly the NKBT that we have. Okay, so this is the NKBT thin film that we made. Again, you do X-ray diffraction and see that the two phases are present. You Raman, look at the microstructure, and of course proof of the pudding is in eating, because somebody will have a question that during the PLD, did you lose some of the oxidation states and the elements at all from this? We did not. All the elements are present in their valence state as required or as dictated by the compound formation, and the environment also is good for each one of us. Then we do the piezo response microscopy on this material, and this shows the morphology, phase, and amplitude. So you can very easily see that we have the growth is there. Then we did the piezo response microscopy. The D33 star is 130 picometer per volt, which is very good for thin films, because it's very easy to integrate this later, and you can do that. And when we did the image of this, we also saw that the morphology is like this. But if you apply the do this loop, piezoelectric loops, you also see the domain or phase contrast because of the domain reversal in this material when you apply plus minus 20 volts. That is minus 20, see this, plus 20, you see this. Okay. So this is what we have done. This was our structure, NKBT structure. The dielectric constant of 500 is pretty high for a thin film. The loop is there. The loops normally do not saturate, but we do get a value of this. See, it is said that the thin films are not poled. I am also sometimes confused about it. Are not poled, so they do not show saturation. Some others say that when you apply this field, since the z-axis or z dimension is not there in thin film, they pole themselves during the application. So, but we are trying to figure this out, and maybe next time we meet, I can tell you a better answer for that. Okay. So, what next we should do now is the question before I end. Okay. So, what we are planning to do now is to concentrate on the thin film magnetoelectric, because we believe we have done the best NKBT in terms of the bulk properties, and they exhibit expected bulk behavior, and the multilayers that we have made with multilayers of MKBT are also showing good property. The literature is rich on NFO made with PLD from our own institute and our own department. So it is natural for us to construct these thin multi-layer devices on silicon, and then with the help of microelectronics center here, when we optimize the layers and the microstructure, integrate this into some microelectronic devices for possible application in the various electronic sensors or military mines, safety, or medical instrumentation that can be attempted. Okay. So all this work is done mostly by my students. Okay. They help me, all these students who work very hard in the lab. This is my institute, which supports me through facilities. Okay, the department supports me, and of course there is the Department of Science and Technology and other funding agencies, which I must acknowledge. Okay, all the students who made all those things possible. And finally, I would like to thank you for giving the opportunity by the organizers and for your attention. Thank you very much.
Thank you, Professor Kulkarni. What a mesmerizing lecture it was. Especially to younger people, those who have entered into the research, this is a demonstration how the material research is done. Starting from how the material should be prepared, characterized, and converted into a device, I think hats off to you, Mr. Kulkarni. Certainly, it was a very self-explanatory lecture, but still there may be certain questions. So can I take one or two questions from the audience? I don't see any question in the chat.
Sir, there is a chart in chat. Can you access the chat? In chat, there are questions. 5, 6 questions there.
Okay, I will just see. I think I was in the end of the chat. That's why I could not see. I'm sorry.
Yeah.
Yeah. The first question is from somebody. I can't see the. What is the benefit? What is the benefit of large D33? Professor Kulkarni. I think he has already explained, but still.
Yeah. Okay, so D33 essentially when it gives you more deformation, okay, more displacement, and if you have larger, it will, and you can make more sensitive devices using them. For example, if D33 is very large, and if applied, if I am converting force into electricity, okay, then at a lower force, I will be able to get better signal.
Right.
So it has to be larger in that sense. So if my weight is same. So I jump on one place and somebody else with half my weight, then he will get lower voltage than I am generating.
There is a second question almost connected. Can you explain the vibration power generation, that is piezo power generation probably? That is what you want to say. Vibration power generation.
Yeah, so here, in addition to D33, you also need flexibility.
Yeah.
Okay, because the power that you generate, if I am correct, it is a product of D33, that is the vibration
Piezoelectric
part,
coefficient.
the flexibility, and the flexibility of the polymer, for example. Okay, so if you have this D33, higher D33 with a flexibility, then you will be in a position to convert that. So what we are essentially, it is done D33 with a lower signal. For example, this electrical signal which is weak, if that you can tap to on the piezoelectric elements which are smaller in weight, you will still be able to convert this.
The power conversion efficiency will be better.
Yes, that's right.
Okay, yeah. The third question is very specific. It relates with slide number 12, that is the TGA curve that you have shown. So he's asking, I want to know, sir, at slide number 12, TGA, why there is further weight loss above 1200? What happened to the stoichiometry? Can this decide the limit of sintering temperature? He's saying there is some weight loss.
13. I think this slide 13, if I'm correct.
Okay, yeah. This is the slide that you are showing. In TGA, there is a weight loss above 1200 degrees centigrade. So he wants to know why this weight loss is there and what happened to the stoichiometry. Can this decide the limit of sintering temperature?
So the problem is, what we are doing in this case is we are using sodium, and in certain systems, the alkali elements are known to evaporate or sublimate. Okay. So that can happen. So therefore, we essentially don't want to go there. We want to stop here at wherever it is a kind of a plateau. Okay. So that we avoid the losses and the compositional changes do not take place. And this loss, of course, I have not calculated whether this 5% loss is because of the loss of alkali. And bismuth also is there. Okay.
Yeah.
So alkali, both two alkalis and a bismuth is a dangerous thing to do.
Yeah. Their evaporation is very high.
Very high. Okay.
Yeah.
So therefore, if you are somewhere around 1150, it gives density like I showed, 97, 98. Right. And for most ceramic system, that is good enough. You can tolerate 2% porosity, which could be a closed porosity also, which need not be an open porosity.
Perfect, sir. Sir, final question is, the compound NKVT, you are using at inside sodium, potassium, and bismuth. What probably he wants to do, what motivated you to use in the formation sodium, potassium, and bismuth? Why not other elements? The composition.
There are other also possible, but again, I said, as a materials person, sometimes we want to have a good control over composition. For example, we have some work on lithium also. Okay, LNN is the compound we call it.
Right.
Okay, lithium, sodium niobate, okay, or titanate or potassium titanates and all that. So here the idea was to have a disorder at A site and exploit that disorder to have higher, as I showed, various vibrations, and you can get the phase as well as the higher polarization. So the idea is to have a disorder at A site. Some people have at both sides, A and B side. That is also possible, but that makes the system more complicated.
And bismuth is compulsory. Bismuth is compulsory. Bismuth presence is compulsory because of the ferroelectricity.
Yeah, that's right.
Yeah. One more question has come up. How can we decide the polling conditions, that is field and time, for good D33 according to particular material?
Okay, the first thing is try to be below TC of the material. So unpoled condition, you measure the dielectric properties so that you know the transition temperatures. If you are not, if you are not done previously, and try to be below that, then the polling is limited by the oil bath that you use, in which you dip the sample. Typically, if you use silicon oil, you cannot go beyond 200. So 180
Right.
is what we recommend. Go up to
Right.
180 because the oil itself starts evaporating. Okay, so that is one you have to use. First, optimize the field. For that, you try to get that resonance, anti-resonance angle to be as close to 90 as possible. And if you are far away from that, you go on increasing time.
Yeah.
The field typically is the other thing that if you have a smaller power supply, okay, say only 5 kV or so, then you will have to thin the sample down so that you get a higher field on the sample. Okay, so what I told actually are all the practical kind of
Right.
things with the limitation that we have. Okay, so like that you do. So one you do one temperature. Sorry, first field optimization, and then you temperature optimization. Both you can.
Time optimization.
Time optimization.
Time optimization. And then you have to avoid the breakdown also.
Breakdown also. That's right.
Breakdown also.
But the completion you have to, for completion, you have to remove the sample, dry it, and check it on the impedance analyzer.
Right.
Make sure that the phase is okay.
Okay. Now, Professor Kamal Singh, he wants to ask one question. Professor Kamal Singh.
Yes.
Professor Ajit, I'm just curious about the characteristics of bismuth oxide, because when we heat it, it changes its valence state, 3 plus, 5 plus. You are already using the alkali oxide, carbon oxides, say Na2O, K2O, and niobium oxide, titanium tetra. So in this stoichiometry, does any time bismuth troubles, or it was trouble free?
It did actually. We did all analysis. We did chemical analysis. Okay.
Yeah, then it is okay.
So it is the nominal composition and the actual composition doesn't show significant change. And even the balances we checked with ESTA, so they are also correctly in place. Okay, so we don't expect that lot of loss or change in composition.
Because I was worried about this one. Thank you very much.
And we also did this elemental thing. If you had, if you can see this, I don't know.
Yeah. Not only this, he has shown the XPS also. I suppose the binding energy clearly shows the balances.
That's right. That also we have done.
Yeah.
And the mapping is uniform distribution now. If it was evaporating, then you will see some evidence in the non-uniformity on the surface of the color, particular color.
The only question, the last question, sir, I want to ask, when you have prepared the thin film, and if you see the Raman spectra, you are getting lot of disorder around 1000, you are getting the lot of intensity in Raman. That is a signature of disorder. But that disorder, it doesn't appear in the microscopic micrograph. So, have you tried to find out what kind of disorder has been this? Otherwise, the spectra is perfectly okay. But there is some disorder as evident around 1000 intensity, 1000 wave number. There is a lot of intensity in the thin film that is not shown in the bulb.
Yeah, that one is one of my postdoc is doing now, because see those Raman equations he is trying to figure out. Okay, those A7 and all those things.
Right.
I don't remember all of those. So
No,
sorry.
No, it's okay.
We'll look into it. I should say we'll look into it.
Right. So, friends, we had a wonderful lecture and equally good explanation of every phenomena that they have observed, and the material reaching towards device. That's a very laudable part of this speech, and we thanks Professor Kulkarni for this wonderful plenary talk. Thank you very much, sir.
Thank you very much.
Now,
Thank you.
now we have the next lecture by equally eminent person, Professor K. Srinivas. Professor Srinivas is Professor, Department of Physics and Astrophysics, University of Delhi, a very good friend of mine. Professor Srinivas' research interest includes condensed matter physics, especially experimental condensed matter physics, gas sensing mechanism in semiconductor materials, dielectrics, ferroelectrics, piezoelectrics, properties of ceramic composites, single crystals, and sputtered film, magnetron sputtering, surface acoustic waves, SAW, ferroelectric memory devices, acoustic, electric, and magnetoelectric effects, UV light detectors, and light upconversion effects. Professor Srinivas is the recipient of several awards and honors. Government of India's National Merit Scholarship in 1972, UGC nominee for the Center of Advanced Studies at University of Bardhaman, West Bengal, and the Indian School of Mines, Dhanbad. 27 Best Speaker, Best Team prizes in English debating at college university level during the year 1972 to 80. So we also remember it at the time of the students' contribution. Annual Canadian Ceramic Graphic Competition Award in 1987, 1989. Professor Srinivasan is the Director of University Science Instrumentation Center, University of Delhi. He had been Dean, International Relations, Science and Technology, University of Delhi from 2008 to 2017. Scientist, Engineer E at Indian Space Research Organization ISRO in 1996, January to November. Visiting scientist at Royal Institute of Technology, Stockholm during period 1993-95. Group leader in Swiss Federation Institute of Technology, EPFL, Lausanne, Switzerland. Manager, postdoctoral fellow, Queen's University, Kingston, Canada during the year 1985-89. He has guided around 27 PhD scholars. He has authored several books and monographs. He has more than 150 research publications in index peer-reviewed journals and 75 conference presentations. He is a member of Lasers and Spectroscopic Society of India and Electron Microscopy Society of India. He has completed about 15 major research projects sponsored by DRDO, DST, UGC, DOE, MIT from 1997 to 2015. He is actively involved in various international national research activities and much more. I know Professor Srinivasan. His contribution to this field, which is covered by NSFT, is enormous. In addition to this, he is a very noble person, very humble person, and one thing that I have learned from him, he is always ready to make others learn, and a very person attached with the ground realities of research. So we will learn a lot apart from the research that he is going to present on non-contact detection of ferroelectric phase transitions, how actually to do research for younger generation who is involved in this conference. He will be one of the inspiration. I invite Professor Srinivas to deliver his talk. Professor Srinivas, please.
Thank you, Professor Vajpayee. I hope you are all able to hear me. And
Yeah.
as it's on my video also, it's nice to say hi to all my friends. My regards to my chairman first here. And for all the kind introduction and afterward, you forgot that Professor Srinivas will soon retire in November.
Sir, you keep your mic slightly away. It is echoing.
Okay, slightly away. Now it is okay. Yeah, it's good.
Yeah, it's okay.
So
Perfect.
let me now start my presentation. I will share the content and quickly get into the move.
Yeah, share. I make share, sir. You can. I make you presenter. Can you see the share tab?
I hope everyone is able to see it.
No, we can't see your transparency, sir. We can't see your transparency. You just share it on the share tab. You go through the share tab. Have you seen the share tab? Have you seen the share tab?
Yes, please. Yes, please.
Have you seen the share tab? There is share tab.
Side of stop video,
Yeah,
right?
No, yeah. At the site of start or stop video, there is a share tab. Okay. So first you will have to open your PPT on desktop and then go through share. So you can easily observe that PPT. You just click on that PPT so that we can observe that your PPT.
Oh, okay. Can you observe?
No. Open your PPT on desktop now.
I have opened my PPT.
Yeah. Now go to share.
Go to
share. Yeah. Now go to share.
Sharing now.
Yeah. Now go to share. Yeah. Yes. Now we can see your PPT, sir. Yeah.
Okay, you could get it now?
Yeah. You click on this. Click.
Yes. Yes. Which one should I click?
Sir, on your screen you can see the PPT. Have you seen the PPT window on your screen?
Yes,
you have
please,
seen
yes,
window.
Yes, please. Yeah.
A PPT window. Have you observed the PPT window? You just click on PPT window. 3-4 windows in our screen now. Is it?
Yeah, I'm clicking now. I don't know.
Yeah.
You can see now?
No, sir. Have you clicked on PPT window?
I don't know where to click.
Sorry, just on that PPT window.
Hello?
Hello, sir. Have you seen 3-4 window now on your screen?
No.
Your PPT window. Have you seen PPT window? PPT window.
Yeah, okay. Yes,
sir, wait.
No problem.
Yes. No. Have you click on this? Have you seen your PPT on the screen?
Yes, I'm seeing the PPT on my screen. I'm seeing PPT
Yeah.
on my screen.
Now just you will have to click.
I clicked it.
Yeah. How you click it, then it is automatically open. If you click it, it automatically
Can you start presentation now?
No, but we can't see your PPT currently on screen.
Professor Acharya, what you do, you have the presentation, you start sharing, and then he will speak.
No, sir. I don't have his presentation.
Okay, sir. Then go below the screen. You will see stop वीडियो के बगल में एक शेयर टैब होगा, उसको दबा दीजिए. जहाँ
शेयर टैब दबाया है सर ने. शेयर टैब दबाया है. सर आप स्क्रीन पे भी गए हैं ना, तो स्क्रीन पे एक 3-4 विंडो दिख जाती है. उसमें आपकी पीपीटी विंडो भी दिख रही होगी आपको.
उस विंडो को दबा दीजिए.
हाँ. अपनी पीपीटी विंडो दिख रही है सर आपके स्क्रीन के ऊपर?
पीपीटी पूरा ही दिख रहा है. विंडो क्या पूरा ही दिख रहा है.
नहीं, आप शेयर से गए क्या अभी? आप हैव यू गॉन थ्रू शेयर?
Yes, I've gone through share, but I don't.
शेयर के थ्रू जाने के बाद आपको 3-4 विंडो दिखे, जिसमें एक विंडो में आपकी पीपीटी भी दिख रही है. वो पीपीटी विंडो पे क्लिक करिए तो आपकी हो गया सर. हो गया सर.
It's all like hit and try. इस बटन को दबाओ.
Sir, you can shift it on slide show mode also. Slide show mode.
Can you all see?
Yes,
Can
okay.
you all see the PPT clearly?
Yeah, we can.
Yeah.
Now I proceed. Yes.
Okay.
So, my regards to all my friends and all my seniors, and good afternoon, everyone. The presentation, the title of this talk was Detection of Ferroelectric Phase Transition by a non-contact optical. partly I will get into a little bit of polymorphic phase transitions, then get into light up conversion. Especially this material system will be considered terbium and tritium. So they will come. Now, on the basis of differences between the absorption of the radiation and the emission of the radiation, luminescence broadly gets into two categories: up conversion and down conversion. And we are specifically interested in the conversion of long wavelength, infrared, near infrared, etc. So the basic idea of this luminescent material is to convert the radiation. It has a lot of applications. And one application, I think in last year I discussed, I don't know, is optical temperature sensing. People would like to sense temperature because it's quite insensitive to external electromagnetic interference and allows mapping. Now, if this is my radiation, and this is my green up conversion, I'm getting green light probably earlier to soak in this. But this emission light intensity can change due to temperature at this platform here, the phase change, or due to the strain, or if they are undergoing the phase. So I would like to put this phase transition for now. So this light up conversion allows spatial mapping over a large scale with high sensitivity. So people are interested in many things, bioimaging. They are already interested in different kinds. But in recent years, temperature sensing has attracted a lot of attention. And I will not go into it. And why this is done, because all these rare times, they have a pair of thermally coupled ones. And they are the most preferred for any kind of temperature dependent phenomena. If you have dope with single dopants, co-dopants, tri-dopants also, sometimes they transition methods. And they have been doping all kinds of things. Fluoride, telluride, silicate, graphite, you name it. Okay? And for temperature sensing, especially, it's still not found an ideal, especially for high temperature applications or for the. There is a nice review of articles, tell you, and suddenly, amid all these compounds, people started doping them in ferroelectric compounds. And there is a specific reason. Everyone knows that once you have erbium or ytterbium or any of these data times in the system, you can absorb photons, one photon absorbed, another photon absorbed, two photon erbium, and you go down to this level, and you begin to fall down to the lower underlying levels. So each one of these levels, some light comes. Different things. There are non-radiative and radiative processes. Measure time resolve resonance. Ytterbium helps. So this is a standard system, everyone. If you have erbium or ytterbium in any host, this will be available. That will explain what kind of light is. You can have intense green light or weaker light because the energy differences are different. And the other rare earth materials you can get some other wavelengths. And you can also have ytterbium cooperation, and you can get state. So one should understand, if once nuclear exciting your sample with a certain data. What are the different light emissions? Now, why are we interested in putting rare earth ions in ferro? Come. One difference, a unique difference the ferroelectric material has is when you try to modify the composition, the crystal structure. I mean, some of the materials also, but ferroelectrics are very good. And second, so far, optical functionality has been seen only in unsparing crystals. Here we are talking about ceramics. They're mostly opaque. How can we add some optical functionality to it is by introducing some rare earth ions. Once we introduce the rare earth ions, we can excite it with some radiation and we can get some light. And so now we are saying that piezoelectric functional properties can be augmented with an optical function. One other thing also, as I said, for temperature sensing also people are putting all kinds of real ions. There are some ferroelectric materials that platinum calcium, which have very high heat. So that means they are having a very thermally and chemically stable geographic structure. And if erbium goes and sits somewhere, its surrounding environment is stable. It has a very stable environment. But then, you see, on one side, we are looking at materials which are expanded with very high DQC values. But if you go and see quartz, some of the materials which are naturally available, they have very low DQC, but they have fantastic stability and very long temperature. So people are interested in all kinds of high DQC materials. Doesn't matter if they have a small temperature stability or even low DQC materials, very low DQC materials, which are very good. So it's becoming important to understand how we can. Now, as I said, when we took these rare earth ions into ferroelectric materials, different kinds of materials, they show sensitivities which vary right from low value to high value. People have gone much higher than this value also. People are interested in much wider. So that means we are making a temperature sensor which is for a very wide. So that's one aspect. So I will not go into this because I dealt with this topic last time a little bit. And this time we have hit upon something else. And the last time the technique that we saw was that bismuth tightening, I think erbium, I think erbium is and I think erbium is in touch. Wow. The reason was very simple. I fixed my erbium and I fixed my yttrium also, and I vary my tungsten also. I go through a structural phase transition inside the material, which is compositionally driven. I'm very tungsten. Okay. And since erbium is there somewhere in this lattice, I'm wearing the surroundings of this erbium environment. As a result of that, there is a change in crystallographic phase, crystallographic symmetry, the fragments of orthogonal, and finding variation in these. This is just the erbium, this is just the daily erbium yttrium, and this is the erbium yttrium. So now we are beginning to see that. As I said, I go back to the first slide where I showed here. This upconverted light is responding to compositional changes. These compositional changes, which are now introducing structural or crystallographic change in the system, and this is intensely. So in a way, sometimes if you want to study, if I'm grading the composition, especially, but limited to those which are having one way, you can figure out how the composition is. Modification, spatial mapping. Now I'm talking about spatial mapping of a technique. If I make that spot very, very small, go back, sorry for this shifting of my, if I make this spot very, very small and I do a spatial mapping and I try to study this intensity variation, I can build a very nice image. Say that how well or how uniformly good the system is. This is one application. We have not yet done it because it means collecting a lot of information, a lot of data, and then squeezing them into one image. It's a lot of computational work. You need to have a very good algorithm. And this is one. Now, you can do temperature sensing. As I said, you get these two emission bands. This way, then you take the ratios of these things and this temperature, you can figure out temperature sensitivity. But as I said, people are still not obtaining very good values with this. But ferroelectrics have been really promising. They have shown quite good value, 0.0123, this is calculated. And this is now competing very well with some of the molecules, which have shown very high. And people are interested, although they would like to have a very linear variation of sensitivity over a wide ranging temperature. These are all the parameters which researchers are working on, and there's a lot of room for improvement. So now I will slightly go away from this, but I want to show to you all how ferroelectric phase transitions can be detected in this non-contact. Now, our previous speaker, Professor Ajit, has been also, and yesterday, a day before yesterday, Susan also, they all mentioned about it. Morphotropic phase boundary and polymorphic phase boundary. Now, morphotropic phase boundary, the classic one, which has been seen in physics. The composition is fixed, and this line is almost vertical. At room temperature, I'm seeing the coexistence of two phases. This is rhombohedral, this is fixed. I go up to temperature, this is still phase. And only at a temperature here, about 355, if my one leg, if I'm standing in rhombohedral, I will see a rhombohedral cubic. That depends upon my ratio here of the composition. Or if I'm in tetragonal, I'm going to cubic. Or if I'm somewhere here on the line, on the line of that, the coexistence. I get over it. So what we are seeing is that the temperature, this is fairly independent of it. So what's the line going? Slightly bending here. And in between this rhombohedral and tetragonal, it is mediated via a monoclinic. This has been seen by advanced neutron diffraction techniques, synchrotron diffraction techniques in recent years. But long ago in 1980, Peter J. Nikita has seen this coexistence of phases on the basis of electron diffraction. It's a classic paper in the case. In comparison to these, people always say lead is not good. We are moving away to lead-free. In lead-free materials, there are two systems which have attracted a lot of attention. One is the system which Professor Kulkarni discussed in the previous talk, KNN-based system, and the other one is Indo-based. These are called polymorphic phase boundary. Here you know it is depending on this access it is high. It is varying with composition and also depending on it. This is the polymorphic phase. Now, why people are interested in polymorphic phase boundaries, the fields? There is one disadvantage. Despite disadvantage, people are interested in it. What is this disadvantage? If I am here at this point, let us say at this point, I have 0 degrees here, I have 0.06 count. It's likely the temperature varies. The composition corresponding to some other composition and my properties. Whereas here it is the composition, because in ferroelectrics, they are very strongly dependent upon properties are dependent upon composition. Because the composition determines the crystallographic structure, and the crystallographic structure determines the polarization. The composition is stable, you get a stable form. So now we are seeing a big disadvantage with polymorphic phase boundaries. The moment the temperature is changing, it changes to another value. This corresponds to some other composition in the property. But despite this, people are interested in polymorphic phase. And we have selected the polymorphic phase boundary for our study. Now, understanding this diagram is very simple. You make 0, 0 with a gradient cycle, 3 classic tetragonal, cubic tetragonal, orthorhombic, orthorhombic. Now, so these are the 3 classic cases. When people start putting doping, either you are substituting the A side or either you are substituting the B side, you need to shift. It goes this side, this side, but this is refusing to go to this side. People are still not able to increase the transition temperature much higher, and always get worried that it is limiting the practical application and it is not as good as heat. It has a large high transition and provides. Now, that is a stumbling block. Understand it and probably the system that is allowed. But still, people are interested why these are shifting. Now, as I said, we go back. Just like coexistence of phases. Here also, this is not a line, but it has a coexistence band. Coexistence. Now, when I'm introducing thinking to this and trying to figure out, this is what tells you about the X-ray diffraction analysis, neutron phase diffraction analysis. X is equal to 0 to a gradient calculus. Most of the people have always come to this diffraction. There is one paper which says that it is probably a coexistence diffraction of it. Now, when we introduce tin, we collected this literature. Someone is saying tetragonal, someone is saying O. At some other compositions, these are all declared as T plus O. These are declared. So, what is this problem? Why is it that this gentleman, like someone, got T plus O? Okay? And when I measure in the lab, I find a full tetragonal composition. I do. This is a big. This has happened a lot. And what we figured out was that this is how we begin to see this coexistence of things. We're introducing things. This is my temperature axis. This is typical polymorphic phase boundaries. Now, when I'm trying to do my XRD, or when I'm trying to measure my I'm measuring them at root long. And if I have made a composition x is equal to 0.05 on the boundary line, I should see purely a tetrahedral phase. A purely tetrahedral phase, because between this line and this line, I'm having tetrahedral. Between this line and this line, I'm having orthogonal. Here I'm having rhomboid. So I make a composition x is equal to 0.05. I see this tetrahedral. But I begin to see a T plus O. When I take the experimental X-ray diffraction pattern, go and do ritual refinement and fitting and all those things, I'm unable to fit. I'm unable to get a goodness of fit value when I consider tetrahedral symmetry of the space. No. But when I consider multiphases and I tell the computer, now please go ahead and fit with both tetrahedral and orthorhombic with some phase fraction. This is 80%, this is 20%, whatever. It fits. Now, we figured out that this phase here, this is 27 degrees. We don't know, we have not proved it yet. We are doing some other experiments. This was just 12 degrees away from the point A, which is on my room temperature line. Okay. This was 12 degrees. I think details are in the case. Whereas this point here was more than 12 degrees. When I do my X-ray, right, I clearly see an orthogonal. Somewhere we feel that when I'm trying to do X-ray diffraction, there is a band along this line. When I see the temperature difference here, within certain temperature difference of this line, if I'm following, my point is following between this line. That means if I make x is equal to 0.04, that my doctor is here. And I'm doing my X-ray here, this temperature difference is really less, I'm bound to see a coefficient. Whereas if I make x is equal to 0.06, I'm measuring my X-ray diffraction pattern at room temperature. But the system is already here, which is more than 12 degrees centigrade. I'm going to see it. Or some other person in some other country has a different room temperature. He has 19 degrees or 15 degrees. Depends. Cold countries, they put the diffractometers there in the corridor itself in a small room. It's to be cold. They don't need air conditioning. They will have a different. So, very important to know how these phase boundaries are going, what temperature are they. For example, the interest is that basically that all these phase boundaries they meet at this quadruple point. This happens at point 1 to 0.11 or 0.12. People anticipated that if I'm close to this place, I can benefit from all the polarization planes, the switching directions, the vectors of tetrahedral and orthogonal and rhombohedral, and I would get very high value. Very high value is the functional property. Dielectric constant. This is a small signal property. Ferroelectric property. The property is used after applying a very large signal, which is all the dielectrics. Now they did observe very high ferroelectric coefficient, more than 1,000. 1022 or 920, these are the different ones. But a very careful analysis of the paper. Now, when I make the material, when I started, I not getting those values. And I realized that they got these values only when they heated their ceramic to 49 degrees Celsius. That heating value of a very high value which they have reported in their papers was at 50 degrees. It was not at room. So you have to pour them very carefully and then. And when I come down to room temperature, no doubt, I'm no longer here the system, I'm going out somewhere here, and I will end up in video. So now what is the width of this coexistence along these lines? Because it is separating two polar phases, the tetragonal phase and orthorhombic phase. It's exactly like the tetragonal and rhombohedral in case of T. The tetragonal or rhombohedral phase, like in the previous speaker, Professor Baker's lecture here. People are now debating if I make a material, if I make a solid solution, what kind of a boundary I should have and what kind of phases should I have. The tetragonal orthorhombic phase boundaries will give you the enhanced values. It's going like this. At x is equal to 0.09, I'm somewhere here, and I'm very close to the separation of a tetragonal to orthorhombic phase. Are materials like PZT, which are separating tetragonal to rhombohedral boundaries, very interesting, or systems, lead-free systems, like barium titanate, orthorhombic rich, or tetragonal orthorhombic, or KNN-based materials, which are showing tetragonal to rhombohedral. KNN is a very good system. First, it shows that tetragonal to orthorhombic, and you put no additional dopants into it. Lithium, etc. These are there in the papers there. I don't have those citations here, but it moves to tetragonal to rhombohedral. So, what kind of a phase separation? Now, some of the recent papers, a very recent papers which I have now reviewed, it clearly indicates that the tetragonal to rhombohedral phase separation gives you a much. So, this is always. Now, this is what is happening when you keep on increasing x, that is steam value. Firstly, this is the steam. The first phase transition, the second one, and the third. This is for classical grading. You keep on introducing tin. This cubic tetragonal is moving. That this fellow and the other one here, they are moving the right. Ultimately, they are all meeting here at the quadruple point, 49 degrees. All in phase transitions. This is the first one, second one, third. They are all, these are rising values, they are coming. At the green one, x is equal to 0.12. Now here we are very close, but at these temperatures being close to root, this quadruple point, that means this line coming with this slope, had it come arrive at this slope, and these slopes have also have changed, then I am having a merging of all three polar phases along with this phase at the root temperature, and I would get very, very high value because I'm benefiting from all the polarization planes in the vectors and the system direction, and I would hit very large polarization. This has not happened. People are interested. How can we adjust the boundaries by components? That is, how can we design materials? So, as we keep on increasing, it becomes from a proper ferroelectric. I would say this is a proper ferroelectric behavior. We are slowly getting into diffuse because all the transitions are merging. It's a diffuse phase transition, and slowly at very high value, we begin to see the relaxation. We are introducing tin It is doing some good, but a lot of bad also. It has destroyed my good, proper ferroelectric sharp phase transition into a diffused one. It slowly into much more diffused. It is now, but it increased the values of the discomposition, but thereafter it will reduce. Now, because, as I said, so people try to, whenever they are trying to figure out the coexistence of phase, rhombohedral, cubic, point 1, 0.10, two rhombohedral cubic. I'll again take you back to why am I saying this 0.12 is a rhombohedral plus cube. Let's go back. 0.1, 0.11, 0.1. This configuration is 15. Okay, and I'm doing my X-ray diffraction at room temperature. On the phase boundary, 0.12 is intersecting Q. The difference delta Q between this black dot and where I can see is less than 12 degrees. I'm bound to see a code. I'm bound to see a code. Whereas if I go to X is equal to 0.15, I draw a line like this, it's a point here. I'm doing my X-ray diffraction here. This is more than 12 degrees. More than 12 degrees. I'm bound to see rhomboid. Bound. If by chance I'm in Sweden, my room temperature is not 27 degrees centigrade, my room temperature becomes 20 degrees. This dashed line comes very close to here. I will then begin to see coexistence of phases. The coexistence of phases is like that. Hello. How close I am to the band will allow me to see coexistence. How far away I am will allow me. Coexistence of phases is also one of the configuration and temperature. So for point 1, we saw that my XID is quickly very to R plus C. For 0.15, it is, what is it saying? Let's go back. 0.15. For point 1, 0.1, 0.15, I'll have the table. It says cubic cube. Okay? Why this says cubic and why does it say R plus C for 0.12? We go back here again. See this guy. Because I'm doing my XRD here and I'm analyzing this pattern. This is far away from the so-called magic gap of 12 degrees. I'm claiming now. I don't know. I have to verify. It is really 12 degrees. It is more than 12 degrees, and my XRD is saying here that magic gap. This gap is less than that magic gap of mine, 12 degrees centigrade. Now, if I want to really prove that this gap is 12 degrees centigrade, I need a very highly resolved X-ray diffractometer, which takes the pattern for every 1 degree interval here and 1 degree interval here also, and exactly figure out where I find coexistence of phases and where I have moved away. Only temperature dependent XRD is true, because we don't have data. And so this is something which is remaining in the literature. Nobody has. Because this, see, in my days, when I did learn X-ray diffraction 20, 30 years ago, nobody used to talk about coexistence of phases. Okay? Only in recent last 5 years, we all have good high resolution X-ray diffraction meters. We all have acquired the software, frequent refinement, program, and all these things. And instead of one phase, we are now able to introduce 2 phases, and we suddenly see the experimental and the theoretical XRDs are matching very well in goodness of fit. And suddenly we are jumping up and saying that we should be called continuously improving my properties. Now there are three properties: dielectric property and piezoelectric property. And now, if I compare it room temperature line, the room temperature line is here, and with composition I'm changing the pattern, the profiles, the relative response profiles. So I jump now to because it's taking a little late here. I'm wearing my tin content. At each composition, I would like to do my frequency response and go down to the dispersion free region, which corresponds to my intrinsic dielectric constant for that composition. And pick up that value, 1 megahertz value, and I go up and I see that the thing around a quadruple point, 0.1, somewhere here, it touches a very high. Now this high value is very easy. Why is it understood? Here. My x is equal to 0, my x is equal to red one here, 0.05, blue here, 0.1, and I'm at 0.11. I'm bound to see a high value. Because I'm on a different location. And I keep on increasing my values here, and my room temperature value is still coming down here. 0.15 it increases, and then light blue it reduces again here. This maroon color, and then it is green color, this orange color, they are clearly explained that definitely at the quadruple point, we have reached very high value. There is a good contribution probably for each one. Someone else measured piezoelectric coefficient also. I could not do it because I have not been able to get optimize my polling like Dr. Kulkarni has played. If I do it, the problem these Chinese authors did it, and with this composition they got 1,000. But more than that, piezoelectric. Now, here's one more. Now we understood that no signal dielectric properties, they are responding to polymorphic boundaries, they are responding to polymorphic phase transitions. Why do I call them polymorphic phase transitions? The phase transitions. The phase transition nature is changing. This is proper ferroelectric, this is diffuse ferroelectric, and I'm coming to relax it. I'll show you the other slide. I'll come back. Relax. Unfortunately, this relaxed ferroelectric behavior is also supposed to exhibit sometimes, in some cases, very high piezoelectric coefficient material, but this is happening in this system at a very low rate. It's practically very difficult to measure. I don't know at the moment how to measure the value at very low rate or at very high. But this is what the whole system. Now, why this thing has influenced the system, like from normal ferroelectric to a diffuse ferroelectric to a relaxed. We analyzed this. We thought maybe we are creating some disorder in going into the system. My X-ray didn't show, it is fitting very well to all the points of the incident-based formation. But Raman showed us, Raman and infrared spectroscopy showed some very interesting, which I share to you, because I like to share with you all how we are trying to analyze. This is typical Raman. You put things everywhere, all kinds of modes you see. Some modes are appearing, some modes are disappearing. It is a disordered system, it is a disordered. But our focus is suddenly practical. Dielectrics had a classic mode of 700, but this was slightly asymmetric. So we started it. Dielectrics is a very good ferroelectric. By the time I came here, the X is equal to 0.28, I'm beginning to see there is a contribution from another reduced phase that was the thin phase. And the contribution of this probably it is existing in an amorphous state because X-ray didn't. As I keep on increasing my thing, this area and the distance is increasing, is overtaking the one which is shown by K. The ratio of these two somewhere equal somewhere less than one, somewhere greater than one, and we can see that there is an onset. There is the way it is changing the ratio. This is directly correlated with the reducing values of the remnant polar and the setting up the onset. So this what clearly told us that if I was going towards this quadruple point, it showed very high dielectric constant. It showed very high piezoelectric coefficient also measured at that point. But somehow people saw the remnant polarization values were going down and disorder was getting. So where this onset of disorder was being seen could be seen through this deconvolution. And this is a very highly what we call resolved data. A lot of data has been. We saw that very similar to barium zirconate calculus, also which exhibits a disorder in this calculus. This is beginning to have. Okay. Beyond 0.15, we are trying to see this is already 0.2. I don't have the graph between these two. 0.15 is 30. Oh, and then, so right from 0.15 onwards, we are trying to see that I'm creating a disturbance in the system. First of all, the values are decreasing and then getting on. So in this system, we could unveil. Now, this is the day I would not go because we were, as I said, we were interested in why these remnant polarization values. Okay, and all that was explained because of this. Right? You take the ratio of these. This is the original barium type. Okay, which happened in 790, and this comes at the higher. So all these materials which are low, especially the barium type ones, they always show a mode at the highest. This wave number 700 to 850.
Professor Srinivas.
That reveals a lot of information.
Professor Srinivas, we are running out of time.
Infrared spectroscopy. But we have a purely tetragonal system, barium type. I have equal mode here, and the moment I begin to see orthorhombic or contribution of tetragonal plus orthorhombic, I begin to see variation. Double. The moment I get rhomboid. So tetragonal P plus O, and in between the purely orthorhombic system also we never got it because we were doping with thin and disintegrated here to the coexistence of rhomboid. And then 0.12, which is R2. These are all based on the variation of the system and the phases of the system. And from 0.12 onwards, we had purely cubic phase, and you can see that the setting up of the 609, okay, vibration, absorption, infrared absorption, which was corresponding to K. Building up K. This was in perfect correlation with Raman, saying that somewhere here I could see the clear formation of these vibrations here. And by this contribution and then I'm beginning to see my what you call where is the diagram here. And relaxation. That was the answer. Now the story comes, we put erbium into this. We selected something, okay. We put erbium. Again, we do the XRE. For 0 erbium, it shows 3 plus 4 because I already have 0.06. The previous diagram we did for just variant in titanium I have 4. And with erbium, this coexistence phase fraction is the tetrahedral content is increasing automatically. And we were obviously if I'm increasing the tetrahedral fraction, I should improve. But this is a fitting lecture. But then I asked the student, okay, you are saying that I'm increasing my erbium content, okay? I'm increasing my tetrahedral fraction, I'm decreasing my orthorhombic from 78 to 77, 75, 66 to 65, and this is going from 21 to 28. One is increasing, the other is decreasing. What is happening? So that the tetrahedral distortion. Look, had some reasonable good value here. Already for David, type A itself is 1.01. The best one. It has some tetrahedral distortion. But this tetrahedral distortion was fluctuating, but was very, very good. That clearly indicated again back to us that although the system says I have tetrahedral state, it's building up, it's stabilizing the state, more on tetrahedral, and but then my properties are going back. It means tetrahedral distortion is becoming lower and lower. There is somewhere a lot of strain driven process. And I have to say, only a strain can explain, presence of strain can explain to me why my tetrahedral distortions are fluctuating in some cases and preferably going to the zero. So it means we had a system in, they were all merging like this. I selected this composition, 0.06, and I started putting erbium into it. Instead of merging, suddenly I'm seeing this all going back. What does that mean? That's the flexibility. Distributed structural transformation. When I'm increasing things, the cubic tetrahedral is decreasing, and these two are, and they're all merging at 49 degrees centigrade at x is equal to 0.15. All three phase transformation. This is increasing. Yeah. I select the system in this. I fix this thing. This will remain same. X is equal to 0.6. X is 0.0. But I put erbium now at the edge. These are both. There are many systems, 4 or 5 systems which are indicating this very but we were interested in something. He said, this is my room temperature. In the case of thin system, my phase transition is here above room temperature. Can I bring this fellow to the top? Erbium, some mole percent here. Erbium is 0, and I will clean as 0.06 corresponds. So now put erbium into this system, 0.06, and give it to this. And I want to see if my values are okay. Bringing That means I'm adjusting the boundary, I'm adjusting the phase transition to come close.
Professor Srinivas is very Professor Srinivas. Professor Srinivas.
The Kulkarni system.
Professor Srinivas, it's very interesting, but we have really.
They have only this also vanishes, and you have purely a tetragonal to a rhombohedron. This vanishes completely. You have tetragonal. Whereas I still have tetragonal to orthogonal.
Sir, you are able to listen.
So somewhere.
Hello, Professor Srinivas.
Get rid of this orthogonal phase formation completely in between and come to tetragonal to rhombohedral. I'll have a similar system like orthographic phase boundary.
सुनने में प्रॉब्लम हो रहा है.
Hello, Professor Srinivas.
This has been achieved recently in what we call.
Professor Srinivas.
Yes.
Are you able to listen me? Please,
No.
sir, we are very late for the session. It's very interesting.
Okay. I'll just finish in 5 minutes. I'll just finish in
please.
Because we started a little late, so I lost a lot of the time because we started planning to start at 12:35. So anyway, so we are shifting these transitions towards the. Now we wanted all these 3-phase transitions to as close as possible to do my experiment. Now what was this experiment? I would like to know. As you said, we were putting erbium into it. Erbium will give you these transitions. So we now saw that this green intense light changes the composition, changes the power of the power, changes the. When we bring the temperature, because we are getting late, I will skip some of the things and I will come directly. So what am I trying to see? I'll go once this. When I put erbium into it, excited with 980 nanometers, I get these are my up conversion line. I'm putting a longer wavelength into it. This is a band. This is a band. 540 to 537, 537 to 574. This is a line. Line is in the literature, a lot of people have been trying to see whether they correspond to phase transitions. And most of the people say, look at the whole integrated band. A huge amount of take the ratios. But then we thought, instead of these, we take only line. And begin to see just the line intensity. That's all. What I mean by line intensity. At this point, that's all. And I plot with temperature. I begin to see how much is here exactly happening with the transition. It's very clear. The stuff is right. It's 74 degrees centigrade. The lesser temperatures are lower here, and the higher temperatures are also here, and it varies. This is 80 degrees. That means my intensity has decreased in the dotted line. Start at 68 degrees. Start at 68, 70, 73, 74. 68 is a black line, blue line, okay? And 70, 74 is a dark. Intensity. But this requires a very careful resolution. That means on the surface, I'm doing the measurement on, I'm exciting with 980 nanometers light. If I do it on an unfold surface, I don't see it. If I do it on an unfold surface, I see a hazy. But if I see a positively fold surface, I'm beginning to see a large intensity unfold. I'm still unable to explain what way is this inbuilt polarization field inside the material interacting with my photons, and I'm getting more photons light up converted intensities more intensities. Now these kind of experiments can be done with ferroelectrics, not the other host. But here is a classic case. We saw that totally a non-contact. We don't have electrodes here, but it requires good surface preparation, and you can look at the phase line. They are not very, very sharp or very still like that. Well, this was the first reported in the picture where we saw that all the people, other people saw very deep views. But people are all continuing and contributing. So this was ferroelectric. So in order to see this, we had to go through all the polymorphic phase boundary and design a system so that exactly between minus 12 degrees to 75 degrees, I could get all the three phases. So I look at barium title. Barium title is 120 degrees centigrade at very low degree, a large temperature. And the experiment takes too long. So we do the experiment in a highly resolved manner. Figure out where the intensity is becoming peak. So this is what I wanted to share with you all, that how we have now extended a little bit of that luminosity. But this is not a universal technique. I would like to caution everyone. This is not a universal technique to detect ferroelectric phase transitions for non-contact. Raman spectroscopy already exists, differential scanning calorimetry already. Okay? They're non-contact. They're not contacting. This is also one of the techniques. But this requires erbium doped barium titanate is different from barium. Okay? I need a rare earth ion. If you give me a pure barium titanate, and say, Srinivas, can you measure ferroelectric phase transition with the luminescent technique? Sorry, I don't have a luminescent center here. I don't have a light of conversion. So I need to go in a very, very small concentration so that I don't disturb the main. Okay. So I think I'll sign off here, Professor Vajpayee. So we're all going for a lunch. From last 3 days, we have been going to lunch at 2 o'clock. So you have been listening at that time.
Thank you. We have oral presentations also, sir. So it is the end of lecture?
Yes, please. Thank you. I'll sign off now. Yes.
Okay. Thank you so much, sir.
I hope you enjoyed what we are doing in there.
Yeah, it's a very interesting and a very novel kind of application of one of the most celebrated material in material science, barium titanate, the World War material. And one can see how very ingenious efforts can create new kind of applications and new kind of techniques to deal with the ferroelectrics. Certainly, there will be many questions, but we are late, so I allow some of the questions. Yeah, one question from a student, Sohaib Abbas. He has asked a question regarding the up conversion and down conversion spectra. He says that a spectra originates from a transition. What are these transitions and which are favorable to up conversion spectra and down conversion spectra? I think one slide you have shown regarding the erbium transitions. Probably he is asking about that.
So the energy level diagram.
Yeah, right.
Okay, what are favorable? Favorable for up conversion.
Yeah, and favorable for down conversion.
Oh, favorable for down. The down conversion spectra are not shown here. Okay, down conversion spectra are not shown. But for favorable for up conversion spectra are, okay, let's go. For studying light conversion effects, now, see, first of all, you would favorable mean, first of all, you would like to have a good intensity for this. Okay, if you have a very weak emission, And if you're trying to study, for example, here you see, I'm doping with erbium with bismuth titan. This is a emission at somewhere, 492.5. It is further down here with my question. But it is very easy. If I want to study some phenomena happening at 492, erbium has a very small cross section, so I have to put some material. I can increase the yttrium concentration by intensity. So I can work with some data. Okay. So favorable in the sense, sorry, there is nothing like favorable. Because where is that energy level diagram I have here? It's right in the beginning. These values are fixed. These energy values are also fixed. Okay. Right? So you are bound to get only 555. You are bound to get only 550. I cannot get 585 unless I have what you call the erbium ion in some frequency. But if it is maintaining its right valency and then corresponding to this diagram, I will get only 555 because that's what is conforming to this. So favorable transitions are the ones which will have more intensity. That's why we also, when we were trying to detect ferroelectric phase transition, I think 524 was the one which had the highest intensity, which allowed us to look at the ferroelectric phase transition. When I went into the band, completely the band, it's a band of transitions, not one single line, many things. The band. You can go back and see that the band. The band. So you can either work with the band intensity or system. But preferable is the one which has the highest intensity line and one which is very well defined, may be convenient. I think I'll say like
that. Professor, if you allow, I would like to ask one question.
Go ahead. Yeah.
The question is related with this polymorphic phases that you are studying by doping tin basically, because ER is essentially a phosphor, so it is not interacting. We presume that it is not interacting. In the tin case, we have some d electrons, and recently we did some DFT calculations, and what we found that in the case of tin, this hybridization between the oxygen and titanium s orbitals, sp hybridization, this is affected, and tin d electrons create certain local bands near the conduction band. So this in turn affects the TiO6 octahedral glacier tilt. And is it the reason that you are getting this kind of tilting and various phases? This is question number one. By slightly changing that composition.
Yes. There are some theoretical calculations going on. I would share with you something. People have said that, at the merging point here, or close to this here, okay, close to this here, they are anticipating a flattened energy profile, okay, and very high value. Okay. But this merging point is happening at a much higher temperature than we do. Okay. Now, if I want to, but I'm measuring all other properties at room temperature. Okay. I can measure dielectric constant at slightly higher temperature, but people have to measure the other properties also. Then only I can see.
Yeah.
Now, but people are finding that very dilute concentrations of tin itself are enough to give you reasonably very high. Yeah. You don't have to really go down to the lowest energy barrier which will be alive. You can work almost with. So that means we are talking about all along the tetragonal to orthorhombic phase bar.
Yeah.
Is this benefit achieved along this boundary or no? That is the question.
Yes. Thank you, Professor Srinivas, for a very, very, very nice talk and very illuminating discussion on the BATIO3. We thank you on behalf of the organizing committee and on behalf of the participants. Thank you very much, sir. Now we have 4 oral presentations. The first presentation have some minor change. The presentation number 13 was to be given by Mr. Rishi Roshan Bharadwaj from Central University, South Bihar. Now they have requested that this presentation will be given by Ms. Sanjukta Jena. So I request Ms. Jena to start her presentation on unconventional magnetization of Fe3O4 thin film grown on silicon 111 substrate studied by soft X-ray magnetic circular dichroic. Ms. Jena.
Thank you, sir.
And please stick to time because we are running late. So try to present the results instead of going into the deep. Thank you.
Thank you, sir. So my screen is visible, right?
You are visible, you are not sharing. Madam
Yeah, your
Smita.
screen is not visible. Your screen is not visible. You are presenter now. Have you seen the share cursor? Share tab. Have you seen? Share tab with cursor. Hello.
No,
On the
Sanjukta.
extreme down, along with the stop video, you must be seeing the share.
Yeah. You are sharing your screen. Now you just switch on.
Okay.
Sure.
Yes. Okay.
Yes.
Okay.
There was a meeting.
You can go to slideshow. How you are slideshow mode? Yeah. Okay. Start.
Okay. Thank you, ma'am. Good afternoon, everyone. I'm Sanjukta Jena from Central University of South Bihar. I'm a MSc third sem student, and my today's topic for the presentation is magnetic states of Mn and cobalt. Okay, sir.
Others are requested to please mute. All others are requested to please mute. Lot of noise is coming. Yeah, Sanjukta, please continue.
Yeah, so my today's topic for the presentation is magnetic state of Mn and cobalt atom and CMG-MgO interface seen by soft X-ray magnetic circular dichroism. Now I'm going to show you my content. These are my content of the talk. My work is based on magnetic tunnel junction, and it is a basic device for the spintronics. And we can make a magnetic tunnel junction stack by using 2 ferromagnets and placing an insulating layer in between them. And the electron can tunnel from one ferromagnet to another ferromagnet, and here the tunneling is spin polarized. And we all are familiar with tunneling, like it is a quantum mechanical phenomenon, and whenever an electron strike to a potential barrier, then which is having a energy less than that of the barrier, then there is certain finite probability that the particle will cross the potential barrier and it continue its further motion. And in our case, the tunneling which occur is spin polarized, and this is the origin of tunnel magnetoresistance, because the resistance of this junction depend on whether these 2 ferromagnets have either parallel spin or anti-parallel spin, and using this we can calculate the TMR ratio, which is given by this formula. And these are some applications of this tunnel magnetoresistance or magnetic tunnel junction. Like we can use it in non-volatile memories and sensors. A lot of people are working on this magnetic tunnel junction. This is the evolution of tunnel magnetoresistance with respect to the temperature, and there are experiments on tunneling for a very long time for TMR. And as early as 1975, Giulieri found out that in this tri-layer we can find up to 14% of TMR ratio at 4.2 Kelvin. And these numbers are quite much not interesting, but this is interesting because you are the first one to report this TMR. And over this decade, it was found out that the addition of aluminum oxide in this tri-layer, observed that there is a sudden increase in the TMI ratio was found out. And in 2010, it was found out that we can get up to 222 to 36% of TMI ratio in the case of CMG and CMS material, which are also called as half metals. And literature revealed that till now this is the highest TMI ratio that is obtained for the case of CMG. That's why we adopted this material for our study. Now I am going to discuss some of its properties, like this cobalt-based cellular alloys. This kind of, they have a complex structure. They have 4 FCC sublattices within it, and these are the some position of this MnSi and cobalt atom. It has a similar property that of CFS. And this is a theoretical model which predict that this type of material CMG have 2 distinctive bands, and one is for the majority spin and another is for minority spin, and the density of state of the minority spin is very small here. There are high polarities expected here, and these are some experimentally calculated values, and this is the total magnetization which was found out to be 4.96 mu V. And in my first slide, I have discussed about the TMR ratio, which can be calculated with the help of resistance of the 2 ferromagnets. But we can calculate this TMR ratio with the help of the polarization of the 2 electrode. And if this, in the case of half metallic ferromagnets, then P1 and P2 are 1. And by putting this formula, we'll get a TMR ratio of infinite. And this is certain example of this half metals. And nowadays, this TMI ratio has reached a value of 0.92, which is nearly equal to 1, and it is pretty much interesting because we are reaching a value of 100. I mean, nearly a value of 100 of polarization. And in this way, we had prepared our sample. Here, there is an MgO substrate, and to reduce the roughness, we put a MgO buffer layer here, and above it there is an CMG and MgO, and ALO capping is done. In our case, the interface is very important. Therefore, these 2 techniques, which is XAS and XMCD, is very much important and powerful technique for this type of study. And now I'm going to discuss about these techniques like XAS and XMCD. And this is our aim. Our aim was to do the thickness dependent study of CMG and MgO interface thin film with the help of XAS and XMCD. So this is the X-ray spectroscopy. Here, X-ray beam having energy of hν is incident on a core level electrons, and the core level electrons are excited to the unoccupied band, and their PD interaction takes place, and we get X-ray peak, which is and the intensity of X-ray peak depend on this Fermi-Golden rule. You can explain this with the help of this, and this transition PD transition is occur by this selection rule, which is delta L is equal to plus minus 1. And in X-rays, we use 2 type of circularly polarized light, and corresponding to these 2, we get 2 peaks, 2 X-rays peaks, and XMCD is just the difference between these 2 X-rays peaks. Now I am going to discuss about the advantages of XMCD. It is element specific and sensitive to local electronic structure, and the main advantages of X-rays is that it works in 2 modes, like one is TUI and TFI. TUI is surface sensitive mode, and you can detect up to 5 nanometer depth of the sample, and TFI is bulk sensitive mode, work in bulk sensitive mode, and you can detect up to 100 nanometer of it. And in this way, we can calculate the spin and magnetic orbital moment of our sample. And these are some measurement conditions. This is our sample, as I have discussed in my previous slide about it. This is the photon energy, like hν is equal to 625 to 805 electron volt, and all the measurements are done at room temperature, and the pressure is 10 to the power minus 10 torr here. Now come to the result and discussion part. These peaks, this figure are shows the X-ray peak of Mn, L2 and L3 edges, and it is clearly visible from this graph that there is some solder-like peaks are observed, and these are the characteristic of CMG, and here no multiplet peaks are observed, and it represents that no Mn atom is oxidized here, and this is the XMCD peaks of our sample, and it is observed that with the increase in the thickness, the XMCD signal is gradually decreases. This is the integrated peak XS peak, and here we neglect the TZ during calculation because Mn has tetrahedral symmetry in the bulk CMG. And this is the thickness dependent Mn magnetic moment, and this graph shows the variation of thickness with respect to the m orbital and m spin. And we can it is clearly visible from in the graph that with the increase in the thickness, the spin orbital magnetic moment of the Mn atom gradually decreases, and the same occur with the orbital magnetic moment. With the increase in thickness, the orbital magnetic moment is also decreases. And in a similar manner, this is the XAS and XMCD peak for the cobalt L3 and L2 edges. And here the same solder-like peaks are observed here. And this is the characteristic feature of CMG. And no multiplet peaks are observed here. It represent that the no cobalt atoms are oxidized here. And in a similar manner, with the increase in the thickness, the XMCD signal intensity is also decreased here. And this is the integrated peaks of XAS and XMCD. And this is the thickness dependent study of cobalt magnetic moment. And here also it is also observed that with the increase in the thickness, the orbital and magnetic moment are slightly changes occurring there. Now come to the conclusion. Here we have studied the magnetic and electronic state of CMG and MgO tunnel junction. And here we observe that no Mn and cobalt atoms are oxidized here. And we observe that with the increase in thickness, the total magnetic moment of Mn and cobalt atom are gradually decreases. Now, firstly and most importantly, I would like to thank my supervisor, Dr. Vijay Rai Singh, for his guidance and support and providing all the necessary facilities. And I really want to thank my seniors and my friends. And these are our national and international collaborators. And for financial support, I really want to thank UGC BSR and SCRB DST for their support, and also DST India and for their financial support, and Jain CSR Bangalore for managing this project. Thank you.
Thank you, Sanjukta, for a very nice presentation, very crisp and brief. But there are certain questions. One question is, how can you interpret results from peaks in your plots, intensity versus photon energy?
What, sir? Can you please repeat your question?
Question is, how can you interpret results from peaks in your plot, intensity versus photon energy? You are having these plots, intensity versus photon energy, and you are getting certain peaks. He is asking how the information about that this peak is the characteristics of CMG, these results, how you are predicting. And the
So we found out this from the literature review, and literature revealed that these peaks are observed in that CMG structure.
Okay, so this is a learning. You have to understand the genesis of XAS spectra or XMCD spectra. Okay, this is one thing, so that next time you can clearly speak about what kind of transitions are taking place. You are showing
so
that
there is P to D transition is occur, and that's the reason behind it.
So
PD introduction takes place there.
Okay, so there is no other question. So let us thank Sanjukta for a very nice presentation. Thank you so much.
Thank you, sir.
Next presentation is oral presentation number 14 by Mr. Jahangir Nelutla. He is from Srinidhi Institute of Science and Technology, Ghatkesar, Hyderabad, and his topic is structural and dialectic studies of multiferroic BiFeO3 ceramics synthesized by molten salt flux route. Mr. Jahangir, please start.
Yes, yes. Good afternoon. Very good afternoon. Good afternoon, sir. I'm very thankful to you, madam, giving an opportunity. Yeah, I am from the faculty of Srinidhi Institute of Science and Technology, and I am doing the research in the BITS Plan Hyderabad campus on the part-time basis, working on the BFO composites. So my topic is today my structural and the dielectric studies of the multiferrite bismuth ceramic synthesis by the molten salt flux route. Now the content of the topic, it is what is the introduction, and the next one it is what synthesis of the bismuth ferrite material, and other one it is called characterization of the bismuth ferrite material, and the dielectric properties of the bismuth ferrite, and the conclusion. Now we'll start with the introduction. What do you mean by the multiferrite? So multiferrite we know very well. It is a more than one ferroelectric, but it's with the ferroelectric and ferromagnetism, and also with the ferroelasticity, right? This is what you call multiferrite. So why is a multiferrite material? So multiferrite materials are material that's combined two or more of the primary forms of the ferroic order. That is what ferroelasticity, right? In the what you call material gets is the what you call elasticity, right? In ferroelectricity we'll get the spontaneous polarization, and in the spontaneous magnetization, right? And next one is why multiferrites. Why I'm choosing multiferrites? We have the number of applications in the this last decade, especially in the memory devices, spintronics, so magnetoelectric devices, filters, oscillators. Now the recently we also observed that photovoltaic application, that means we can convert into the light energy into the electrical energy with help of the multiferrite materials. And now synthesis of the bismuth ferrite, as we gone in the last 2 days. So there are a number of presentations. We synthesized this bismuth ferrite material. So why it will be the why we have to synthesize this bismuth ferrite material among the other materials? Because it is a very good, well-known material at room temperature. It is shows the exhibit the what you call multiferrite materials at room temperature. So people are working with like this what you call work at the this bismuth ferrite material. Now the case study. So what is the beauty of this bismuth ferrite? So this bismuth ferrite is a high Curie temperature. It is 1103 Kelvin, and it has a mean temperature. It's 673 Kelvin. It has a weak ferromagnetic moment, and it is belongs to that R3 space group. Now we have to discuss about that, the beauty of the bismuth ferrite. So what is that? It is how you will get the multiferrocity. So now if you look into the diagram, so it is a structure of this what you call in the bismuth ferrite, how you will get this ferroelectric and the magnetism, how you will get the antiferromagnetic. Now you look into this one, there is an oxygen octahedra. So this oxygen octahedra rotate along the 111 direction, along the 111 direction along the opposite by 13 point something angle. So what happened if it is that this oxygen octahedra is rotate, there is a large displacement will takes place between the bismuth ion and the FeO6 oxygen octahedra, that leads to that spontaneous polarization. So the beauty is what, whenever the displacement of these charges will get the ferroelectric spontaneous polarization, so that will be the origin of this what you call this ferroelectricity. Now coming to this diagram, there is a small antiferromagnetic moment which is due to that G type. So if you look into the diagram, this will be that Fe spin. So the Fe spin coupled in ferromagnetically and antiferromagnetically within that what you call this plane. This plane is what 111. So we'll get that one, it is called ferromagnetically and antiferromagnetically. That means what? So that is antiferro. That is the spin moment will be that opposite direction. We'll get the weak magnetic moment, that is almost the magnetic moment is cancelled zero, but we'll get small canting magnetic moment will come due to that Fe spins. So because of these things, so it will be acting as a multiferrite materials. So that is the beauty of this bismuth ferrite material. Right now, how we have to synthesize? We have the various method. So that means we have that solid state method. Many of my co-research scholars and my friends in yesterday and day before yesterday presentation, we have that auto combustion method, solid state method, and sol-gel method, chemical routes. And in that, one of the best method when coming to the physical method, we have now come standard sol-gel is there. Sol-gel is the chemical method. We may achieve the bismuth ferrite at lower temperature. For coming to that physical method, let us say that in solid state reaction, or if you take it in the what you call single crystal growth. So along the, compared to this physical method, I choose the physical. One of the best method is what flux method, because I can come down to I can reduce the temperature. So with the molten salt or in the what you call this flux method. So in that I'm using the molten salt. So what is the beauty of this molten salt? Now the structure, there is a flowchart of the molten salt route here. So what I'm taking the reactant powders in terms of in oxides, that is called in the Bi2O3 plus Fe2O3. What I'm doing, I'm just taking the what you call reactants and adding the salt. So I am taking the salt. Let us say that we have the molten salt like NaCl is there, KCl. We have the NaCl. It is what you call the 801 is a what you call point, and 777 is a KCl. Out of that, I choose this NaCl. What I am doing mixing and what I am grinding in the Presnell motor, eject motor. After that is doing to the calcination. So what will happen when we go into the calcination? The beauty of this salt, it will be help to that homogeneity. That means that synthesis of this BFO pure, very difficult to get the BFO because there is a kinetic formation. There is a metastable state will be formed. To avoid this metastable state, we are taking that NaCl. So it is enhance these. What is that? The homogeneity, diffusion content will be increases in the when going to the calcination process. After taking the sample out from this furnace, then taking that to because of my sample containing what we call NaCl, I should have washed out that NaCl because in that pure paste we may get the NaCl peak, or in the other type of peaks will come. So I am doing the washing with the distilled water, and after that drying, because if it is in hydroscopic nature, I should have go into the drying. Then we'll get the final powder that is in the form of in the what you call BFO. So this is what the structure of the molten salt. It is one of the old technique, but still we are getting the good result on this molten salt when it is in the physical method, right? So now in the coming to this XRD pattern, so I did this what you call I just variation the flux ratio, like I'm taking the reactants in the 1:1. So I got XRD with the lower impurities. So what I did then, I started again this I increasing the molten salt. So then 1:2 ratio, right? We got is a very good XRD structure, the conformation, and again 1:3 and 1:4. So finally, what I optimize, so I for this entire process, so where it will be the good what you call BFO without what is that less impurities. So we were observed that at BFO at 1:3, we got the very good phase at 650. We were calcined at 650 4 hours. So we were optimized at 1:3, and we took the 1:3 as a finalized. So then we are taking the characterization part. So these guys, if you see that there is a less impurities coming to observing the 1:1 to 1:2 or 1:3 to the 1:4. But here same impurity phase. But thing is, there is an intensity will be very, very, very less when you come into the 1:3. Now we were calculated the crystalline set with help of the very well known, all people are very known, that is called as the Schreier equation. We got this 442.97 nanometers, right? The Debye-Schreier formula, we calculated the average crystalline size, and we were also this micrographs. It will be clearly indicates that it will be average granular size and granular shape of crystallized with less porosities, right? The VDAX is there. VDAX also we measured this. All constituents are the stoichiometric ratio. Now, if you look into this VDAX picture, right, all will get the in the stoichiometric ratio, right? Then we also we find that in a vibrational analysis, that means FTR structure, FTIR we got in the we confirm that the peaks at 542 centimeter and 459 are the attributed to the modes of FEO stretching vibrations of the bending vibration respectively. So this confirm that it is a metal. So we can confirm that it is belongs to that what we call this BF. Along with that, other peaks also we are observing that, because now if you look into the other peaks, this 630 and the bending vibration due to that H2O. So why it will be H2O will be coming to the picture, because what I'm doing after taking from the furnace, so I am washing out so with water. So I can expect that. So we can expect that there is a peak due to the water. So that we confirm that in the vibrational structure. Now coming to the XPS investigation. So what this investigation XPS? So XPS will give you the chemical composition along with that oxidation state. So bismuth belongs to what state it is, and Fe2 belongs to the what state. So we got XPS survey spectrum. So it is very clear that bismuth is an 3+. Right, in oxidation states, we got in the it will be very good matching with the literature. This is the typical survey spectrum as shown in figure. This includes the match with the result obtained from the XRD and the IDAX. So X-phase spectra 4f orbital bismuth revealed 2p centered at 158.3, and it is correspond to the core line of BF bismuth 4f 7/2 and the bismuth 4f in the 5/2, which is in the multiplicity, it is in suffix. Sorry, I just forgot that. Then we are going to discuss now. After that, this structural is over, microstructural is over, and I just found that in the dielectric properties at room temperature. So we were observed that that frequency depends at very low frequencies. What is that high dielectric constant? At very high frequencies, it has a lower frequency, very low. What do you call this? This high dielectric constant. So that means when you come into the frequencies increasing, so what will happen that the dielectric constant will be decreases. Why it will be the decreases? Because of the you're applying the more and more frequency. That means frequency means it is nothing but energy, no doubt. So whenever your frequency that is, it is very difficult to align. That polarization is won't takes place at very low frequency. What will happen? So there is a all contribution due to the electronic polarization, or it is an ionic polarization or space charge polarization. We can get the more dielectric constant as on frequency will be increases. So what happened that the dielectric constant will come, but it is due to that space charge polarization. It is similarly that similarly the same thing it will be applicable to the what you call loss also, right? So this will be the along with the temperature. As we increasing the temperature, what will happen? The beauty of in the bismuth material, the oxygen ion will, with respect to the temperature, the oxygen ion will be increases. Because of that, what happened that that dielectric constant will be increases. So whenever we are increasing the temperature, the dielectric constant increases because that oxygen ion vacancies will be increasing in our material. So then I shown it is in around 1 kg and 10 kilowatts and 100 kilowatts, then with respect to the temperature, so that it will be increases. Now coming to the conclusion, BO4 we were synthesized at the what you call molten salt with NaCl media. So NaCl is a flux that is called molten salt. Almost pure phase BF4 powder were synthesized at 650 with salt ratio 1:3. NaCl played an important role in formation of the BF4. That is the highlight of this method. See, we have the large oral presentation, number of presentation on the BFO, but here it is a beauty of the this is molten salt. You know, this will be promote the good formation, and we were observed that good uniform granular shape of crystallites and BFO ceramic at the higher dielectric constant and the lower dielectric loss was observed BFO ceramics data from the molten salt synthesis route. So we were doing on this BFO with composites, other materials. Right now we are doing on that. So here I shown that the single phase dielectric material with the molten salt route. So thank you all. Little fast. Thank you so much because of the time constant as I instructed this. Thank you so much to all.
Thank you so much, Dr. Jahangir, for
sir,
a very confident presentation. I could not see your dielectric loss. Dielectric loss, sir, where it is?
It is, I plotted here only, sir, in single graph only here. So one side, this will be that.
Which
here,
one?
Sir, electric. This one, sir.
This is your loss. Okay.
Yes, sir. Yes.
So,
I took in
loss is quite high with respect to VFO. It is 0.3, 0.2
yes, sir.
or something. No?
Yes, sir.
So anyway, there is a question for you.
Yes, sir.
Is there anything beneficial you got in your research while following this molten flux route?
Sir, we can reduce the temperature. Sir, in physical method, suppose if you see, I'm talking about the sol gel, sir. In coming to the physical method, if I'm using the molten salt, I can reduce the temperature. So I can reduce now 650, the phase formation is formed, sir. But if you take the solid state, it may be going to the 750, but still there is a impurity peaks. But with help of this molten salt, we can reduce the temperature. It is one of the low temperature technique like in sol gel method. That is an advantage we were observed, sir.
Okay. So since there is no other question,
thank you, sir.
Let us thank the speaker for the very nice talk.
Thank you so much. Thank you, sir.
Our next speaker is Dr. Muhammad Tanviruddin Kamaruddin Kaji. He is from Anjuman College of Engineering and Technology, Nagpur, and his topic is structural, electrical, and magnetic characterization of BFO-BT. Dr. Kaji, please start your presentation.
Just a minute.
Tanvir, you share your screen.
Yes, ma'am.
Okay, okay. You can start.
Okay, madam.
You start your presentation. We have not seen your presentation. Okay, okay. Okay, it's okay. You can start now.
I'm a Tanvir Kazim from Anjuman College of Engineering, Nagpur. My topic is structural and electrical and magnetic characterizations of bismuth ferrite and barium titanate. I included the introductions, applications of multiferrites, preparations of material, characterizations, in which I included the structural characterizations, P and MH hysteresis loop, and finally I explain the conclusion. Multiferrites actually order, including ferroelectricity, electricity simultaneously. More especially in this material, show a ferromagnetism, ferroelectricity, and the coupling between these two order parameter. The polarization can be handled by magnetic field and the magnetizations of the material by an electric field. And such a material are known as a magnetoelectric multiferrics. The term multiferrics was introduced by H. Smith in 1994, and the property of magnetoelectric moving crystal was predicted by Curie in 1894 based on symmetry considerations. There is applications of the multiferric state, which is used in multiferric state memory, ferroelectric storage with magnetic read and vice versa, tunable refractive index, magnetodielectric property, and electrical tunable magnetoelectric property, and vice versa. The objectives of my topic is to prepare the composites material by combining the ferroelectric BaTiO3 I choose for that, ferromagnetic BiFO3 at room temperature. This material I have prepared by solid state method. First, we prepared the bismuth ferrite and barium titanate pure materials, and then we prepared the solid solutions of bismuth ferrite and barium titanate with different weight percentage from 5 to 90 weight percentage. This is the flow chart of the my preparations method, where I prepared by using the reactant bismuth oxide, iron oxide, barium carbonate, and titanium oxide in stoichiometry amount. The appropriate amount of the reactant were mixed together in agate mortar by grinding for 2 hours and then pressed into the pellet with a uniform press. A series of ceramic samples of solid solution with composition from 5 to 90 weight percentage. The 10 mm pellets were calcined at 800 degrees Celsius for 4 hours and 1000 degrees Celsius for 12 hours for 85 to 100 weight percentage in the platinum foil. After the calcination, the sample were reground and again pressed into the pellet with a press of 3 ton per centimeter square. The pellet were again centered by wrapping in a platinum foil from 850 to 1200 degrees Celsius with increasing the percentage of BaTiO3. Then we characterize the solid solution or pure material by using the XRD, MH, and P hysteresis. We studied the structural characterizations by using the X-ray powder diffractions. For that, we use the pan-analytical X-ray diffractometer, which is operated at 40 kilovolt and 30 milliampere. Diffraction data was collected in 2 theta range from 10 to 90 degree. Observed diffraction pattern we indexing by using powder X software, and we refine the unit cell parameter. This is the XRD pattern of different materials, pure BaTiO3, BiFO3, and number composition from 5 to 80 weight 50 weight percentage. The single phase nature of BiFO3 was confirmed by the observed powder exit data with the reported earlier. Similarly, the phase purity of BiTiO3 was confirmed. No segregations of Bi to Fe4O9, Bi to 5 FeO40 type was observed in any compositions of the prepared series. In Bi, rich compositions from 5 to 15 weight percentage are closely similar feature as that of the BiFeO3. As the powder excited data for the composition at BaTiO3 end are closely similar to that of the tetragonal BaTiO3, they are compared with the excited data of BaTiO3. By comparing the end member of compositions, we clearly identified the rhombohedral tetragonal phase region in less than 30 and greater than 50 weight percentage respectively. The powder excited data of composition with less than 30 show the similar reflection like rhombohedral BiFeO3 type phases, while the composition with 50 weight percentage show the similar reflection like the tetragonal BaTiO3 type. Mentioned earlier, BiFeO3 crystallized in the rhombohedral symmetries like a R3C lattice, where the clearly separated doublet is observed. The feature is observed at the 2 theta 32 degree gradually merge to a tetragonal P4 structure. In addition, this doublet gradually shifted from 32 to 31.5 degree, which is less than for 58 percentage. This is the table of the lattice parameter which we obtained from the PowderX software. Here you can see the different lattice parameter structures and the C/A ratio and volume of unit cell. From the unit cell parameter of rhombohedral phase compositions indicate the rhombohedral distortion decreases with increasing in BiT3 content in the BiFO3. In addition, unit cell volume show the increase in thread with the BaTiO3 content. Similarly, the unit cell parameter of the tetragonal BaTiO3 decreases with increasing BiFO3 content. In addition, the tetragonal distortion of BaTiO3 lattice decreases with the increasing BiFO3 content. The next is the P and MH. We observed the P hysteresis by using the 50 Hz AC frequencies and using the EGN GPR vibrating sample magnetometer. This is the next is P. This is the P and MH hysteresis loop. In P hysteresis loop of 10 weight percentage and 50 weight percentage at room temperature, which indicate the weak ferromagnetic nature. The observed MH loop with a small but non-zero magnetization in small sample 30 than 50 weight percentage suggest the cycloidal spin structure of pure BiFeO3 may be suppressed in 10 weight percentage. The ferromagnetic property of 50 weight percentage appear to be better than all other composition in terms of the coercivity for such as 475 Reminus 0.0086. The sample 50 weight percentage and 10 of the P hysteresis loop have nearly similar coercivity, but the remnant polarizations are 0.01 and 0.21 respectively. Similar to the magnetic behavior, the polarization behavior of 58% Ki3 is better than the other studied composition. This effect may be originate from the internal distortion of 50 weight percentage compositions. Finally, conclusion. In my conclusion, single phase end member BiTiO3 could be optimizing the heating conditions. Solid solutions of BiFeO3 can be obtained either by rhombohedral or tetragonal lattice. Decrease in distortion in rhombohedral lattice is observed with BiTiO3 addition. The polar lattice BiFeO3 is retained throughout the solid solution. Ferroelectricity is also observed in all the solid solution enhancement of the ferromagnetism in BiFeO3, which is contained antiferromagnetic, is achieved in this study. Thank you.
Okay. Thank you, Tanvir, for the very nice presentation. There are few questions. One is, magnetization is observed in ferromagnets. What can be considered in multiferroics?
Hello?
Hello. The question is, magnetization is observed in ferromagnets. What can be considered in multiferroics? He is asking why you are observing the magnetization in multiferroics.
Actually, sir, we have focused the whole study on the morphotopic phase boundary of these compositions. So we have taken choose the two material, out of which two material 10 weight percentage and 50 weight percentage.
This is okay. He is simply asking magnetization in multiferroics. So it should be there because multiferroics has magnetic ordering and ferroelectric ordering.
Okay, sir.
Okay. See, the question which I would like to ask is, because BFO-BT is a very well-known system, very well exhausted, studied, and we all know that in BFO-BT there is a morphotopic phase boundary at 0.06. What your observations are showing that even above 0.06 you are having a pure rhombohedral phase. So this goes against the reported results because after 0.06 there is a phase transition. You have, I don't know whether you have missed it, you have not prepared the 0.06 phase where you should have observed the coexistence of rhombohedral and tetragonal phase. And beyond this, one should not observe the rhombohedral phase. So why you are observing? Have you checked it? Please check it with the literature. Please check because this morphotopic phase boundary in BFO-BT is very well known. And second thing, what was the purpose of doing this study? You were looking for morphotopic because you did not get the morphotopic phase boundary in your compositions. Anyway, look into it. Very nice presentation. Thank you very much.
Thank you, sir.
Next oral presentation is oral presentation number 16 by Dr. Jayant Ramchandra Gulgule, Yashwantrao Chauhan College of Engineering, RTM Nagpur, and his topic is effect of lanthanum dopant on pyroelectric characteristics of lead germanate single crystal. Dr. Gulgule.
Thank you, sir.
Sorry, have you seen the share screen? Yes, sir.
Yeah. You are welcome. I am all present here. I am Jayan Gulgule from Yashwantrao Chauhan College of Engineering, presenting a effect of lanthanum dopant on characteristics of lead germanate single crystal. Potentially useful for device application because of their high dielectric and nonlinear behavior, polarization reversal, domain structure. In particular temperature ranges where the semiconducting materials fell. Secondly, doping can modulate the physical properties of ferroelectric materials suitable for device application. With this aspect, we have undertaken the impact of lanthanum doping. So we have grown the single crystals of pure and lanthanum doped germanate by a method of controlled cooling of the metal. Then the of grown crystals have been studied over a temperature range of 40 to 300 degrees centigrade. The measured room temperature, pyroelectric coefficient, and estimated values of spontaneous polarization of grown materials are compared with the values reported by other investigators and the mechanism of pyroelectricity in grown materials. About here. It has become attractive material for device application because of large spontaneous polarization, its reversibility, and nonlinear optical properties. In view of properties which are applicable in both and applied sciences, these crystals have been intensely studied over the past. These crystals are uniaxial ferroelectric which undergo second order phase transition at 177 degrees centigrade, at which the crystal symmetry changes from hexagonal to trigonal. Studies of their structure, dielectric, piezoelectric, pyroelectric, and optical, mechanical, and other characteristics have been carried out by a large number of. This component has potential use as pyroelectric material in ferroelectric memory devices and for hologram recording. There are methods which are used for study of the pyroelectric effect. First one is the Chinavet dynamic method, in which the crystal and strong light pulse and produces the pyroelectric current given by equation 1. Second one, static or charge integration method suggested by Emgas, which involves a continuous integration of charge developed on crystal faces as the temperature of the crystal is raised. Third, which is also called as a direct technique for measurement of pyroelectric coefficient, wherein pyroelectric a change in temperature alters the lattice spacing of a non-symmetrically located ion, which varies the spontaneous polarization of the crystal. This variation of spontaneous polarization produces a displacement current parallel to the polar axis given by equation 2. And the instrumentation, we have grown the single crystals of pure and doped magnet by cooling of the light. Initial material was prepared by mixing the lead PbO and GO2, so high grade material in 5:3 molar ratio, and thoroughly mixed material was divided into 3 parts. The first part was used to grow the LG crystal, which are pure one, and in other 2 parts we have added lanthanum oxide in 0.58% and 1%. The powders were thoroughly mixed and tablets were prepared on hydraulic press by applying pressure of 1 ton per square inch. Centigrade. A platinum crucible for about 6 hours in close in air. Tablets of LG, LG1 and LG2 were recrushed to fine powders and crystals were grown. The crystals were made ready for measurement by using an electrode with air drying silver paste. Crystal holder was designed and used measurement. The variation of both pure and doped crystals has been measured by SES nanometer in the temperature range 40 to 300 degrees centigrade with an interval of 10 degrees centigrade. The instrument is essentially designed for low current measurement for high impedance source. The 1.4 degrees centigrade per minute and the cooling and that of cooling equal to 1.5 degrees centigrade per minute was maintained during the measurement. Temperature was measured by chromium alloy thermometer and controlled by automatic temperature control, which is of endothermic. For measurement, wear and rounded technique and pyroelectric coefficient was calculated using equation 3. The equivalent circuit for this measurement apparatus is shown in the figure 1. Most of the investigators use direct measurement techniques suggested by wear and rounding. It also shows the variation in magnitude of room temperature values measured using different techniques by various investigators. Magnitude values are comparable with the values reported by most of the investigators. The variation coefficient with temperature, which shows that temperature pyroelectric coefficient are negative for pure and doped composition. Change of sign in Lg and H1 with small peaks respectively at 180 degrees centigrade and 160 degrees centigrade. However, both are not observed in Lg2. Insignificant temperature dependence of pyroelectric coefficient below respective transition temperatures for all three samples. Significant temperature dependence of this pyroelectric coefficient above respective transition temperatures for all the three samples. And lanthanum dopant has reduced the magnitude of room temperature pyroelectric coefficient. This reduction increases with for these composition at various temperatures is estimated using and following the expression suggested by Matsumoto et al., which is given by equation number 4. And with temperature is shown in the figure 3, which shows that the room temperature values of spontaneous polarization are positive for pure and doped sample. It reduces to 0 value near the respective transition temperature for all the three samples. Lanthanum doping has reduced the spontaneous polarization in Lg1 and Lg2 compared to Lg in ferroelectric phase. This reduction becomes more with increasing the concentration of dope. Above transition temperature, Lg1 shows the marginal rise of PST compared to Lg, while in Lg2, PST increases in negative direction. Table 2 shows the comparison of reported room temperature values of spontaneous polarization crystal and ceramics with our estimated values of pure and doped sample. It reveals that the order of magnitude agrees with those values reported for lead germanate single crystal by other researchers. Lanthanum dopant has reduced the magnitude of spontaneous polarization. The observed results can be explained on the following basis. A.S. Bhalla et al. Suggested that the measured pyroelectric resultant of primary and secondary components of the pyroelectricity in crystal, which is given by this equation 5, where the secondary pyroelectricity in the crystal is expressed as, that is Pc of T is equal to E33 into alpha plus twice E31 into alpha. That is equation 6, where Eij are the pyroelectric stress coefficient and alpha are the expansion coefficients of the single crystal. Using reported values of Eij and alpha, the value of secondary component we have estimated, and presuming the contribution of secondary pyroelectricity same for all the three compositions and is equal to our theoretical value, we have estimated the primary pyroelectric coefficient for all the three samples, which comes out to be negative in all the three compositions. This contribution of pyroelectric may be due to dipole relaxation, domain configuration, and domain wall motion. Pinning and clamping of domain wall may significantly affect the primary value. Efficiency may also affect this primary value. Lead germanate composition belongs to the system of non-isovalent impurity, causing enhancement of lead ion vacancy sites. These sites may result in increase in localized phase charge formation, which can increase pinning of the reduction in magnitude of primary as well as the total pyroelectric coefficient at room temperature in Lg1 and Lg2, therefore can be attributed to pinning of domain in these compositions. The release of trap charges and strain remain insignificant at room temperature. Except near transition temperature, the temperature-dependent dipolar relaxation and domain wall motion also remain insignificant. Probably these are the origin of temperature-independent pyroelectric coefficient below transition temperature as observed in figure. With temperature, there is a change in reorientation of the dipoles, causing the change in polarization of the surface. Further, above transition temperature, probably two processes may contribute in pyroelectric behavior. Number one, the release of trap charges at domain configuration, effect states, and vacancy site, as emphasized by V.V. Aristo et al. And V.Y. Eshu et al. And the thermal and mechanical strain contributing in secondary pyroelectric phenomena. The generation of additional charge due to unknown impurities and release of accumulated charges at interface between bulk and surface charge there towards the pyroelectric coefficient or heat. All these parameters are probably contributing towards significant temperature dependent pyroelectric behavior in LG and LG1. However, in LG2, above transition temperature, the contribution of thermal and mechanical strain within the crystal may become less. The resultant effect of primary pyroelectricity and release of one type of trapped charges. The observed change of sign of pyroelectric coefficient in LG and LG1 may be due to the change in the nature of liberated trapped charges and their relative strength and contribution of primary and secondary pyroelectricity together. However, in LG2, the nature of relief charges may remain same. Acceptability of any material to be a pyroelectric detector, it should have a pyroelectric coefficient, high pyroelectric coefficient, high resistivity, and small dielectric constant, and low thermal capacity. The output voltage of the pyroelectric IR detector depends upon the heat capacity of the material as determined by the volume specific heat C prime and the dielectric constant epsilon. For voltage responsivity is expressed by equation number 7. By considering the value of volume specific heat, that is 2.0 joules per degree Kelvin centimeter cube of pure lead germanate single crystal for all three compositions we have made using equation number 7. Compared with others as well as with the reported values of pure and doped lead germanate. This table reveals that lanthanum dopant has reduced the magnitude of figure of merit. The result suggests that both PC of T and FM for pure and doped compositions are comparable with the reported values of lead germanate and other materials except TGS. Further, TGS crystals are hygroscopic, hence show less thermal stability as reported by H. Bloomberg et al., which causes bad reproducibility. However, our estimated value of PCOP for pure and lanthanum doped compositions are temperature independent in low temperature region. Therefore, these compositions can be claimed and are significant for construction of pyroelectric detector. Conclusions: single crystals of pure and lanthanum doped lead germanate show pyroelectric effect. Dopant has reduced the magnitude of room temperature pyroelectric coefficient. Temperature dependent PC of T shows in LG and LG1, which is not observed in LG2. The observed pyroelectric behavior in these compositions can be attributed to contribution of primary and secondary pyroelectricity as envisaged by A.S. Bhalla. The estimated room temperature values of PS of T are positive. Lanthanum dopant has reduced the values of spontaneous polarization in ferroelectric phase. All three compositions may be used as a sensitive material for pyroelectric detector because of better thermal stability than TGS in low temperature region. These are used in this particular paper. Thank you very much. Thanks for giving me an opportunity to present my paper in this conference. Thank you.
Thank you, Dr. Gulgule, for a nice presentation on very important pyroelectric detectors. There is a question for you.
Yes.
In your slide number 9, why do you say LG1 shows a marginal rise above room temperature?
Slide number 9. So could you repeat the
question is, why do you say LG1 shows a marginal rise above room temperature, above transition temperature?
In PS
not room temperature.
Graph for this LG1. This is the graph for this LG, and this is for LG. So when you shows marginal rise is having the more value of spontaneous polarization, that is the marginal rise above this one. That is as compared.
Okay.
Okay, yeah.
I have one. Yeah, it's okay. I have one or two questions from you because it's a very sensitive result.
Yes.
First thing
Sir,
you say that
sir,
for a
one minute. Instead of question, if I will receive the suggestions from.
no, it's okay. It's not a suggestion, it's a query. For a good pyroelectric detector, definitely pyroelectric coefficient should be high, resistivity should be high, but you're mentioning that dielectric constant should be low.
Yeah.
This will create a problem because the ordering, which is very important for pyroelectric detector, over a period of time will become random. And this is one of the problem in TGS.
Yeah.
Why TGS detectors becomes less sensitive over a period of time? It is because of we try to reduce the dielectric constant in order to increase the thermal stability. Second thing, why you are comparing TG with TGS? Why not with the dope TGS? Dope TGS, especially aniline dope TGS, have very good thermal stability.
Yeah.
So, and TGS sensitivity is slightly better than what you are showing. So, in what way this detector will replace TGS, especially dope TGS?
So, because exactly we should know the value of that.
No, I tell you, I mean, we have worked on one of the basic problem of pyroelectric detectors is not the sensitivity, it is the long-term efficiency. Over a period of time, like if you have this detector and measure the pyroelectric coefficient after a year, you will find that the coefficient decreases drastically. And as a result, we can't use these pyroelectric detectors, especially for sensitive defense applications like imaging and other things. The coefficient must be constant or invariant over a period of time. And this happens because the dipolar ordering it becomes switchable, and because of the switching dipole ordering in ferroelectrics, they become random, and therefore switching inhibition is one of the important component for any good pyroelectric material. So why you have not seen the switching inhibition, like the measurement over a period of time? That will be a very good test of these materials. Measure after 1 month, after 2 months, after 3 months, and measurement over a period of cycles.
Yeah.
Okay, thank you so much. Thank you so much for the very nice presentation. And with this, we end the session. I would like to thank all the speakers and oral presenters for presenting very nice research conducted by them. I thank especially Professor Kulkarni and Professor Srinivas and all the four speakers. And finally, I thank Professor Smita Acharya and all the senior members, Professor Kamal Singh, Professor R.N.P. Chaudhary, and all others present for providing me this chance to hear the session. Thank you so much.
Thank you. Thank you.
Thank you, sir. Thank you, sir. And it's actually we are delayed by half hours of this session.
Okay.
So, PK Bajpayee, sir, you are continuously arranging. So, should we take a half-hour break or because you are tired?
Whatever you feel.
Sir, we take a half-hour break. We will join.
Okay.
Yeah,
Okay. Okay. Okay.
We will
Okay.
join at 3:30, sir. Okay. Now it is
Okay.
at
Thank you. Thank you.
3:09. It is 3:10. So 3:30. Okay, sir.
Okay.
Okay,
Okay.
sir.
Okay.
Thank you very much, sir. Thank you, Srinivasan, sir.
Thank you.
Yeah.
Thank you, Kamalji. Good evening.
हाँ, गुड इवनिंग। मुझे बहुत अच्छा लगा आपका कंडक्टिंग, बहुत ही बढ़िया।
Thank you. Thank you.
और लकीली अपने को स्पीकर भी बहुत अच्छे मिल गए,
Thank you,
अजीत
madam. Thank you.
और श्रीनिवास। तुम्हें देखकर ही बहुत खुशी हुई।
कमल प्रसाद जी नमस्कार। आप म्यूट है, पहले अनम्यूट कर लीजिए।
नमस्कार सर, मैडम को मेरा
कैसे हैं?
चरण। हाँ ठीक है, बहुत बढ़िया, बहुत बढ़िया।
नमस्ते।
एक्चुअली हमारे यहाँ कन्वर्सेशन होने वाला है ना, तो उससे जल्दी जल्दी भाग के आए कि नहीं भाई मेरा प्रेजेंटेशन है, जरा सा आए इसलिए।
Sorry, sir. We are getting little bit 30-minute delay. So
कोई
we
बात
will join. Okay. So we will
मैं
join.
थोड़ा स्क्वीज कर लूंगा, उनको थोड़ा वो दे दीजिए, कोई बात नहीं, वो हो जाएगा कोई।
हाँ, तो हम सर 3:30 ज्वाइन करते हैं। ओके सर।
ओके ओके ओके।
Because PK Bajpayee sir from morning he is doing the share.
या
Okay, so we will see you at 3:20 sir, 3:30 sir. Okay. Okay sir.
ओके।
मुझे प्रेजेंटर करो, that screen I will share. Hello, ma'am. Kamal Singh, ma'am. Can you hear me? Kamal Singh, ma'am. Ma'am, Kamal Singh, ma'am.
मैडम तब तक एक बार शेयर करके देख लें, शेयर होता है कि नहीं। हेलो हेलो प्रोफेसर आचार्य, आर यू हियर मी? हेलो 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 हेलो।
वो लोग चाय पीने गए हैं डॉक्टर साहब।
हाँ हेलो श्रीनिवास साहब, नमस्कार।
लगता है प्रोफेसर आचार्य वगैरह सब लोग चाय पीने गए हैं।
नहीं नहीं सर, हम यही है, इसके सामने ही बैठे हुए हैं सर। सर हम इसके सामने ही बैठे हुए हैं। सिर्फ वो
कमल प्रसाद कुछ शेयर करना चाहते थे अपना प्रेजेंटेशन।
मैं स्लाइड शेयर करके देख लूं ये हो रहा है कि नहीं, फिर तो।
हाँ सर, सर मैं आपको प्रेजेंटर बनाती है, 1 मिनट।
हाँ हाँ।
Sir, I have made you presenter. Now you can see the share screen in lower part of your laptop screen. In lower part, have you seen mute, unmute, stop video, and then there is share.
Share, yes.
Yeah. First, what you do, you go to your PPT, open the PPT on desktop.
Open the PPT. Okay. Yeah.
And then go to share. Then go to share. Click on share.
Click on share. Yes.
Yeah. Now you can see your PPT there. 3 or 4 window may open there, and in one yeah. Okay. Now you are sharing your PPT. I can see your PPT now. Okay.
Okay. It's okay.
Yes. Yeah. It's okay. It's okay, sir. Okay. Good.
Okay. Thank you.
Okay.
Thank you.
Okay, sir. Okay. How are you, sir? Now? How are you? Because we are meeting after 2 years.
Certainly.
2018, we are meeting in Bilaspur.
Right.
Yeah.
And Srinivas, we also meeting after 2 years.
Yeah. In NSFD 2018, we are meeting Srinivas sir also.
Bilaspur. So how things are going on in Nagpur?
Good. No problem. Again, Corona is there. Last 9 months, we are in lockdown. So almost the life is stopped. But it's okay, research is going on, no issue. And currently, I have got some administrative responsibility as IQSC director, NAC, and our university have NAC due. And just
Same
now,
here also.
Every teacher is busy in NAC. To whom I asked, and he said that I'm busy in NAC because NAC make him a very hectic schedule.
हाँ वो कर दीजिए जरा सा मतलब आज एक पेपर में दे दीजिए कि वो लाइव कर दिया गया है ठीक है ना वही ऑनलाइन कन्वोकेशन के लिए ऑनलाइन जो अप्लाई करेगा बच्चा लोग हाँ अच्छा हाँ और आपको वो दे दें वो शेयर कर देते हैं उसका लिंक आप उसको पेपर में दे दीजिए ठीक है ठीक हाँ बस नहीं नहीं है नहीं ठीक अभी भेज देता हूँ ओके
कन्वोकेशन भी आप ऑनलाइन ही ले रहे होगे ना
जी वही आज लिंक लाइव करके आ रहे हैं वहीं से जो है
लेकिन अच्छा लग रहा है सर मुझे ये ऑनलाइन का अच्छा लगा क्योंकि एवरीथिंग सभी को अपने अपने जगह से पूरे काम भी हो रहे हैं और मुझे ज्यादा ये नहीं एफर्ट्स नहीं करने पड़े ना अभी ऑफलाइन होता था तो सब ये अपना हॉस्पिटैलिटी और एकोमोडेशन इसमें सब बहुत ज्यादा ये चला जाता था टाइम
ये तो है सही बात
ऑनलाइन में बहुत ये हो जाता है टाइम बच जाता है बहुत
बट कोरोना ने ऑनलाइन में घूमना फिरना बंद कर दिया
हाँ वो एक है
नागपुर आके तो संतरा उतरा खाते इधर उधर घूमते
जी
और अभी तो नागपुर बहुत प्लेजेंट बन गया है सर एक तो विंटर है और डेवलपमेंट भी अच्छी है नागपुर में so it's really one of the nice place now to come this time is really one of the nice time आते तो बहुत अच्छा लगता था नागपुर क्योंकि बहुत प्लेजेंट एटमॉस्फेयर है और डेवलपमेंट में भी नागपुर अच्छी डेवलपमेंट हुई है अभी लास्ट 5 साल में तो
मतलब आने की इच्छा थी वहां पर लेकिन अब क्या कीजिएगा ऐसा समय आ गया कि कोई उपाय नहीं है
और एक्सटेंड करके भी मतलब नहीं था सर क्योंकि अभी लोग मुझे नहीं लगता कि 1 साल लोग देरिंग करेंगे एकदम आने का ऐसे गैदरिंग में
सही बात
तो एक्सटेंड हुआ 1-2 महीने एक्सटेंड करती तो भी नहीं पॉसिबल था मैंने वो बहुत सोचा फिर आरएमपी चौधरी साहब से भी बात की तो वो सर बोले नहीं ऑनलाइन अच्छा होता है और ले लो बोले उन्होंने कहीं अटेंड किया
ठीक ही ठीक
कोमल जी नमस्ते
हाँ सर नमस्ते क्या समाचार है
अच्छे है।
और
आप कैसे हैं?
बस
बहुत दिन के
बढ़िया।
बाद आपको देख के खुश हो गया हम। हम लोग हम लोग
हमें भी खुशी
कानपुर
हुई है सर।
हम लोग कानपुर में मिले थे, वो जो उड़ीसा कानपुर गए थे, याद है?
हाँ हाँ हाँ, या वो बहुत
सार का ये कॉन्फ्रेंस।
दिन।
हाँ।
हाँ हाँ,
आप तो
बहुत।
जैसे थे वैसे ही रहे, आपका कोई चेंज हम नहीं देख पा रहा हूँ। यू आर रियली मेंटेनिंग योर हेल्थ वेरी गुड।
गुड, थैंक यू
गुड
सर।
हेल्थ। ठीक है, कभी आइए जब।
जरूर जरूर,
हाँ,
एक बार हम सिंगापुर गए थे 2 साल पहले लगता है ना?
वॉइस
लेकिन
सीमेंट ना।
हाँ वो, लेकिन फिर उस समय हम पता नहीं चले आए जल्दी से।
हाँ हाँ, आप हमारा टॉक में थे
ऐसी बात में
ना, आज का टॉक में थे आप हमारा।
नहीं, आज तो हम अभी असल में आ ही रहे हैं, जल्दी भागे भागे ना, वो कॉन्वोकेशन
ओहो।
हो रहा है। ठीक है ना, तो
अच्छा
उसी को
अच्छा।
लाइव करके अभी हम ही इंचार्ज हैं उसका।
अच्छा
आगे
अच्छा।
भागे आए, सर मेरा
आप तो
टॉक
बहुत
है
बिजी है। ठीक
है ना?
है सर। हाँ, बाय।
और बाय बाय।
मैडम आपको एक मेल मिला होगा अर्पित मेंढे के नाम से। वो अपन ने जनरल बॉडी मीटिंग एनएसएफडी की रखी है 4:30 बजे की। हाँ सर। हाँ हाँ, बस उसमें उसने आपको बस ज्वाइन की बटन क्लिक की ना, तो आप डायरेक्टली ज्वाइन हो जाएंगे उसमें। ठीक है। ओके ओके ओके, तो कोई प्रॉब्लम नहीं आ रहा है ना अभी? कोई प्रॉब्लम नहीं आ रहा है ना? ओके ओके। हाँ ठीक है, तो वो नहीं, वो जो मीटिंग है वो मैंने दूसरे प्लेटफॉर्म पे रखी है, क्योंकि ये प्लेटफॉर्म पे ये जो है उसमें ये चलेगा ना, अभी पोस्टर सेशन चलेगा। अच्छा, और दूसरा है ना, आपको और एक मेल मिला होगा जिसमें एनएसएफडी की तरफ से, कि जिसमें श्रद्धा ने आपको 19 पोस्टर दिए हैं चेकिंग के लिए। हाँ क्या? और तो उसमें क्या करना है, बस आप वो जो एक्सेल की शीट भेजी है उसमें वो ब्लू कलर की लाइन दिखेगी ना, उसमें जस्ट आपको क्लिक करना है। जैसे ही आपने क्लिक किया ना, तो आपको वो लिंक ये खुल खुल जाएगा आपका पोस्टर। ओके, और पोस्टर खुल जाएगा तो
Hello.
Hello.
Good afternoon, Acharya. Good afternoon, Acharya madam.
Yes,
May I
yes,
audible?
sir. Yes, sir. Yes, sir. Welcome, sir. Welcome. So, have the Bajpayee sir have joined because he is the speaker of this first speaker. So I just Bajpayee sir. Bajpayee sir is there. कहीं इधर उधर गए इसलिए वो आना चाहिए.
Pranam, madam. Singh madam, pranam. Ajay from Yavatmal.
मैम है क्या? हाँ दिख तो रहे हैं.
Madam.
है. अजय कॉलेज चालू हो गए तुम्हारे ना? ऑनलाइन लेक्चर ले रहे हो ना तुम लोग?
Madam, can we take five more minutes? Actually, I want to have a cup of tea.
Okay, sir. Okay, sir. No problem. Okay.
Just give me five minutes.
Okay,
Sir,
sir.
you
Okay,
take your
okay.
own time, sir.
Yes, sir. Actually, we feel that we give punishment to you. So you take your own time. No problem, sir.
Yes, madam.
Welcome, sir.
Yes.
Yeah, yes, sir. Yes, sir. Welcome,
Should
sir.
should I start sharing?
Yes, sir. I make you presenter. So we are going to start session 10, application of ferroelectrics and dielectrics. The chairperson of this session is Professor Ajay Lad. He is belongs to our group and good friend. He is from Department of Physics, Amolakchan Mahavidyalaya, Yavatmal. Dr. Ajay Lad is presently serving as professor in Department of Physics and IQSC coordinator at Amolakchan Mahavidyalaya, Yavatmal, teaching to UG, PG, post-PG students. He is the chairman of Board of Studies in Physics of Santa Gadge Baba Amravati University. He is also the member of various academic and professional body. Dr. Ajay Lad has authored 5 books for physics students of SGB Amravati University and RTM Nagpur University. Also, to his credit, more than 57 national international research papers and received many more awards, including Young Scientist from Indira Gandhi Center for Atomic Research. His research is focused on the development of conducting glasses, ceramics, nano glass ceramics, thin film, polymer, etc. for various technological applications. He is also reviewer of several international journals. The 4th student has been received PhD under his guidance, and 3 more students are pursuing PhD degree register at SGB Nagpur Amravati University. Dr. Ajay has completed 1 minor research project. He has successfully organized national and international conference. So I invite Ajay to please chair the session. Your session consists of 1 plenary talk, 1 invited talk, 1 contributory talk, and 1 oral. Okay. So Dr.
Thank
Ajay,
you.
please start your session.
Thank you. Thank you. Thank you, madam. Good afternoon, everyone. Pranam all gurus. Pranam Kamal Singh, madam. A national seminar on ferroelectric and dielectric in collaboration with the Dharampet Science College, Nagpur, organized by the Department of Physics, Rashtrasanta Tukaji Maharaj, Nagpur University. Today is the 3rd day of the seminar, and I am very thankful to the organizer, especially thanks to the Dr. Smita madam to provide me opportunity as a chairperson of this session, which is delivered by very eminent scientist, educationist, Dr. Bashvi Sarji, Pranam Sarji, Dr. Kamal Prasad sir, Dr. Smita Chaturvedi madam, and Vikrant Ganvir sir. I am very happy and lucky fellow to introduce the Dr. P.K. Bajpayee sir. He is a very eminent scientist and educationalist. Everyone know the Dr. Bajpayee sir. Bajpayee sir is currently working as a professor and head Department of Pure and Applied Physics, Central in charge and National Center for Accelerator-Based Research, Department of Pure and Applied Physics, head Sophisticated Analytical Instrumentation Facility, Guru Ghasidas Vishwavidyalaya, Bilaspur. Bajpayee sir had been the coordinator of the National Knowledge Commission Network based activities, chairman of the core committee integrated university management systems, e-governance initiative of the university from 2012 to the 2017. Coordinate IQSC internal quality assurance cell coordinator from 2004 to 2018, Guru Ghasidas Vishwavidyalaya, Bilaspur. Sir has many noteworthy achievement and honor to his credit. He established National Center for Accelerator-Based Research, Accelerator-Based Interdisciplinary Research Center in the Department of Pure and Applied Physics, various sophisticated instrument facilities such as FTR, UVVIS, mass spectrometer, NMR, etc. at Regional Sophisticated Instrument Center, and many more. He is the member of many professional bodies such as American Nano Society, International Academy of Physical Sciences, Allahabad, New York Academy of Science, Executive Council, Indian Society for Particle Accelerator, Board of Director for Research, American Biographical Institute, USA. He is also a recipient of INSA Coastal Visiting Fellow, SERC Visiting Fellow. His PhD thesis was selected as one of the 6 best research work in solid state physics at national level in 1987. Sir holds distinguished position in many statutory universities. He has great contribution to the Guru Ghasidas University, chairing many committees. Sir is the author of many more than 30 international journals, published 85 research paper of national and international repute, and 15 research scholars completed their PhD under his supervision. Sir has guided 33 MP students. He has completed 17 research projects funded by different funding agencies such as CSR, DST, UGC, DAE, organized over 30 international national seminar and conference, member jury for the Young Scientist Award in conference from 2001 to 2004. His research and administrative contribution are countless. Sir, today, respected sir, deliver on the talk challenges and road ahead in the design and development of multiferrics. Sir, please you start your informative and innovative talk. You have take your own time, but as per the program schedule, you have 45 minutes, sir.
Thank you, Professor Lard. And I'm grateful to the organizers and especially Professor Acharya for providing me this opportunity to interact with you all through this online, what we call Sanjal mode. Before I start my talk, I would like to congratulate all of you on the eve of Yuva Divas, the birth anniversary of the great Swami Vivekananda, the youth icon of the world. He also has a very important role in instilling confidence in Indian values and Indian scientific way of thinking. And this is what actually happening in science also. Being a plenary speaker, we can have the choice of saying something blah, blah, blah before the talk. So I take few minutes of especially to our youth. If you see the evolution of science, modern science and technology, it evolves with the singularity. A single idea unifies the cosmos more and more. First such unification was done, as we all know, by the Newtonian mechanics, when the celestial and terrestrial objects were unified, that they belong to the same law. The second such unification came with the Maxwell. The electricity and magnetism were unified. Third such unification came with the Einstein, when space and time was unified. And then with the advent of quantum mechanics, we unified all the forces. And in the unified theory, now we are in a world, we are in a cosmos where all the laws that are followed by animate and inanimate objects are same. And this resembles very well with the Indian thinking of unity in diversity, ekatmata. Everything belongs to same. Now, coming to the today's topic of how to look at the material science for the development of humanity, for the sustained development of the nation, and for providing the peaceful solution for the problems that mankind is facing, this is what is the crux for what we all are doing research in various fields. Now, our vision of doing research and our thinking, our path towards research has to change in the manner that as the science is evolving, it is becoming more holistic, and therefore seemingly uncorrelated phenomena are correlated. This is what science is telling. And in the material science, all of us, we are looking for such observations, such facts, such phenomena where more and more things are getting correlated. If you see the condensed matter physics, we have wonderful materials like ferroelectrics, ferromagnets, ferroelastic materials, and these materials were used in large number of technologies. But then came that multifunctionality behavior of these materials because of the coupling between different modes of freedom. And these coupling, this cross connections is what evolves the world, or the interactions among different species. So from that point of view, our material science has to become more holistic, more multidisciplinary. And this interdisciplinary approach should be the thought process while doing research. This is one message that we wanted to convey. Now we come to the today's talk, and let me see here. Okay. Is it getting clear? Sorry,
Yes,
can all
yes,
of
sir.
you-
Yes, sir.
Okay.
Yeah. You just slide.
So-
You can convert in slideshow mode.
That's right.
Okay,
So
sir.
this is the topic of my talk today. We have seen many presentations on this multi-ferroelectrics, a large number of presentations. But I am not going to repeat what others have said. What we are going to do in this talk is to analyze what are the various aspects of multiferroics, why we should develop multiferroics, and what are the challenges in the process. And therefore, this will be a journey of whatever little understanding I have of each multiferroic material. This is what I have planned, and I will not take more than 45 minutes. It is 3:45. So from now onward, I will stop exactly at 4:30. First, as usual, I will give a basic understanding and importance of multiferrocity, and then discuss some of the conceptual things, especially why this multiferrocity has taken so much time to evolve as the niche area of condensed metal physics. Then little bit fundamentals about the classifications from the point of view how one can design the new materials in different categories of multiferroics and where we should focus. Then I will focus on in a very brief manner, especially focusing towards the young generation. I was not knowing that this might have been covered by during the this tutorial, but even if it is repetition, it will be good. Then what are the different strategies people are following at present to develop new multiferroics? What are the future directions? And then some of the recent advances, especially some of the results that we have got for bismuth ferrite, doped bismuth ferrite, where we could improve the coupling. One of the basic problem of bismuth ferrite is that its purity is very difficult to obtain, and then that modulation that exists and creating the canted G-type antiferroelectricity during very small magnetic moment that we try to improve successfully. And then we will focus on a little bit about the new results on compositionally driven phase transition in bismuth ferrite. When we do bismuth ferrite, it goes from one phase to another phase. This is known, but there are a lot of ambiguities about which phase to which phase it is going, and whether during the compositionally driven phase transition there remains multiferroic character or not. So these are the things that we would like to share. And before I start, let me just discuss with the young colleagues that before 1990, multiferroics were known, as many of us have discussed. But multiferroics was not being the focus of research. What was the reason for it? And if you see, in 1989, two databases were published. One was the database for the perovskite oxides, which were ferroelectric, and another database for perovskite oxides, which were magnetic materials. One was published from Japan, one was published from Europe. And both these databases, when people start searching, they found that not a single material is there common in both the databases. So obvious question comes why ferroelectrics are not ferromagnets and ferromagnets are not ferroelectrics. With this question, Nicola Spalding, she started looking for the reason. And we all know this is now the history that which is called D0ness and half-filled d electrons. For the ferroelectrics, you require D0ness. For the half-filled magnetism, you require half-filled electrons or the transition metals. And therefore, this chapter should have been closed. But this is how the science evolved. They started asking, is there any way of creating a condition where both the orderings exist? And as we all know, that Smith has given this coined this term multi-ferroics. Ferroics, we all know how to define the ferroic. I have been listening to many talks, and young colleagues, you are making a mistake. A material is not ferroic if it has some order. This is not the, this is necessary condition, but this is not the sufficient condition. It must have domain. Ordering along with domain makes a material ferroic material. And these domains must be switchable. And therefore, for any kinds of material, contribution and control over domain structures, understanding the domain engineering is very, very important in controlling the properties of ferroic material. Then every ferroic material gets switched by its conjugate field. Then the second question comes, is it possible to switch it by some other field? And this gives a fundamental question that if I can affect you, I am correlated with you. And this is called coupling. So any kind of coupling can be invoked provided that there is a correlation between the two properties. And even before multiferroics, we very well know if you have a ferromagnetic material, it may show the piezo-magnetic property. We don't bother. Such materials we don't call but they are multiferroic. Similarly, we have the material which are piezo-ferroelectric. In fact, when Professor Kulkarni was giving a talk, nobody bothered that piezoelectricity and ferroelectricity are two different phenomena. They are associated because they are coupled. So piezoelectricity is also having the elastic ordering, ferroelectricity is having electrical ordering, and therefore this is also multiferroic. And therefore there are possibilities of many types of multiferroics. At present, most of the multiferroic work is focused on magnetoelectric coupling. And therefore, one of the possibilities that our young colleagues should look for, apart from this magnetoelectric coupling, there are very interesting works being done on elastomagnetoelectric multiferroics, where three parameters are coupled together. There is also a possibility of, instead of looking for ferromagnetic ferroelectric coupling, you can look for antiferromagnetic, ferrimagnetic, paramagnetic, and especially on super paramagnetic coupling. That is a there are very, very interesting areas of applications in this. And this field is open. The third important thing is that the innovation aspect. Innovation means if you have carefully watched the lecture of Professor Ajit Kulkarni, what he was showing, one slide he was showing that this is the market for piezoceramics. And this market is growing by 4%. This is what the innovation element. What drives the research in a particular field is possibility of value addition, possibility of economic growth. And therefore, this is now is the policy of our government, STI, what we call. You do science that drives technology with innovation. It creates the innovation. And therefore, while designing our research for multiferroics, we must do work on the fundamental physics of correlated oxides as we are doing. But in addition to this, there must be a multi-pronged strategy among the scientists who are working, and this forum is a very good opportunity where instead of just doing the research for publication, Let us make a target that within 5 years, this is what the device we will make based on multiferroic. And these are the materials that we will be proving. And this is what is the type of research that we are going to experience within next few years through National Research Foundation. So this is another important point, that multiferroicity as one of the niche area, along with the carbonaceous material, graphene, smart material, multifunctional material, and ion beam controlled novel materials, and so on. One has to find the niche areas and niche topics where the combined efforts of teams of scientists who are having expertise in various domains, they come together, forms the proposal, and NSFT has taken many such steps. I am sure that on the final day, NSFT will certainly discuss on some of the topics where researchers can come together to form the collaborative projects and to aim for converting the material properties into devices. That will generate the value addition, and we have the confidence that we have seen in the vaccine. We are one of the first countries to develop our own vaccine. I'm sure that we will be the first country to develop our own multiferroic-based spintronic devices if we have this cluster collaborative approach in understanding the multiferroics. Now, since we know the multiferroics, just for the sake of completeness, let me say that effectively you can divide the multiferroics into two categories. There are many, many more subcategories. Type 1 are those multiferroics where the dipolar ordering and spin ordering are separate. They are independent. Now, such materials are easy to design. But the problem with this material is that the coupling between these materials between two ferroic order is inherently weak. And therefore, they are not by nature very suitable for devices. The second type of multiferroics are where the magnetic ordering induces the dipolar ordering. Not directly. Again, there are two types of these things, where the magnetic ordering through elastic or the structural changes, structural disorder, it creates the dipolar ordering. And there are compositional multiferroics, where one composition is having the ferroelectric property, other composition is having the magnetic property. And here some of the niche areas that are coming up are the interfaces, heterostructures, nanomaterials. And some of them, they are also having some novel phenomena along with the multiferroic, and such as what you call transport properties. In these materials, you have many so-called correlation effects, like we have the condo insulators, moat insulators, and so on. And therefore, our young generation should look for, while designing the multiferroics, to understand what are the factors, especially the role of 3D, 4D, and 5D electrons. When you know all these are the D electrons, but the exchange interaction between the 4D electron is different than the 3D electron, and 5D electrons are having very weak interaction. So one has to understand the quantum mechanical exchange interaction that I am going to discuss. Now, again, what we have to understand that you can create different kinds of magnetic ordering, like I have shown A, B, C, D. These are the very well-known magnetic ordering, by simply designing a material in the same phase. As you can see, A, B, and C, these are the unit cells, where these red are the spin atoms. So by changing the spin atoms, either through chemical means or now you can do by implantation. So this ion beam implantation is one such effort where you can design the multiferroic of your choice. Now this we all know that these are the three fields. The corresponding conjugate response parameter, if I couple, then I have 9 types of multiferroics that can be generated. these are the couplings that we have shown, and these couplings, as we all know, some of them have been explored, but most of the researches that have been done, they have taken two order parameters at a time. Even the basic physics of coupling between three order parameters, such as thermodynamics based free energy explanations for three or four parameters coupled together, that is not done. That is another area that can be developed. It is very simple, but it needs lot of insights about how to design the material. Now, we all know historically, we know that it was from 1960s. One of the classic paper is Astroke paper in 1960. That has shown, and of course, Curie, we all know that magnetization in certain materials, in this case, it was the chromium oxide, is directly proportional to the applied electric field. So this is called magneto-electric coupling. This was known, and this was also investigated by many scientists, but this does not create interest because the reason was, as you can see, the alpha value was very, very small, 10 to the power minus 5, and there were very limited compounds that were known to have this effect. And therefore, for almost 30 years, this does not interest scientists to work. Then from 2000, from 90s there was some, but basically from 2000, there were some new theoretical concepts. It's not that somebody has found some material where the theory was developed. And in the phase transition theory, there were many effects, especially CMR and GMR effects in transition metal compounds, especially in the manganese-based compounds, where giant effects are seen. And when we started understanding the theoretical background of this thing, then we realized that these small effects can be improved. And therefore, magnetic electricity or magnetoelectric coupling was reviewed on the design basis and new materials came up. Now, problem with this was this coupling term, that it cannot be greater than the geometric mean of electric and magnetic permeability. And therefore, this type of coupling, if you consider, then you can have the multiferroic effect, but very weak effect.
आप लोग फोटो स्क्रीनशॉट ले रहे हो ना इंटरवल में?
But with the advent of new theoretical dimension based on the density functional theory, it was found that this effect can be generated much larger when you take the higher coefficient, and especially in ferroelectrics and ferromagnetic materials, this magnetoelectric coupling can be much larger than was predicted in 1968. And so far, the largest effect was found in ferroelectric ferromagnetic. Now, the question that Nicola asked, do ferroelectric ferromagnetic exist? Because the region was B0ness and half-filled B. And once this question was asked, as I said, asking right question is the base. Rest of the things comes automatically. And this was the question which is in the classic paper now, why there are so few multiferroids. And this was the answer. Yes, it is possible to have the ferroelectricity and ferromagnetism together, and this was coined as multiferroids. Now, obviously, we all know what is multiferroids, but to understand how one can play with them, we have to have a very clear picture. What is ferromagnetism? You have a spontaneous polarization. From where it is coming? Due to the exchange interaction, not because of the ordering of the spin. Spin ordering is the result, What is genesis? The tunability and variation of exchange interaction. And what kind of exchange interaction we can tune? We will come in the next slide. Similarly, what is ferroelectricity? We say spontaneous polarization which is switchable. Not correct. Dipolar ordering, that can be by anything. And the earlier explanation that ferroelectrics can have two types of mechanism, displacive and order disorder, is no longer valid. They are called conventional ferroelectrics. Now you can generate the ordering on the basis of electronic degree of freedom. So electronically driven ferroelectrics are not reality. Improper ferroelectrics are reality. So spontaneous polarization need not to be the order parameter. And therefore there is a possibility that a non-ferroelectric material can be developed as a ferroelectric if you include some transition metal in it that generates distortion, and we will come to this topic, and so on. And therefore, extension of antiferroic forms of ordering has to be looked for to generate new multiferroic material. I still have 30 minutes. I am looking for. Now, another important point, another very important point that we have to look for, that if you consider, say for example, perovskite, most of the young people, if you see the perovskite, it's not a single lattice. It is a mixture of two sublattices. The A site is a different sublattice, and B site, along with the oxygen octahedra, is a different sublattice. Now, as we have changed the oxygen with halogens, you have seen the whole solar energy market has changed. Perovskite solar cells are the different. Similarly, these two sublattices can be tuned. We have not made efforts, and this BiFeO3 is the result of that. In one sublattices, you are putting a ferroelectric entity. In another sublattices, you are putting a ferromagnetic entity. And therefore, this lone pair based, I'll come to that again. What I'm trying to stress is that we have to see the entity, structural entity in their real picture. There is very little interaction in a perovskite cell between the A sublattice and B sublattice. And therefore, those who are analyzing the Raman spectra, they consider these two sublattices as different entities and they take the interaction. Very recently, in 2019, we have published a paper. Based on this analysis, you can explain all the sequences of phase transition perovskites using the Raman spectroscopy very nicely. So it gives you the new facets. Now, we all know that ferroelectricity and ferromagnetism is very good at quantum level, at classical level. And we also know that both these materials are the backbone of industrial revolution. They are still very, very important. Now, let us look at them. And I have given just two examples that we know magnetic valve based on the ferromagnetic. We know the spin transistors based on the ferroelectric. So they are technologically very important. Then why we want that they should come together? And what are the reasons they are not coming together? If you try to understand that, say for example, memory devices that we are making based on ferroelectric or storage devices based on ferromagnet, what are their problems? In the ferroelectric based memory devices, first of all, they are the two-state devices. So when you have to read and write, you have to provide the current that generates the voltage and reads it. Now, providing current means there are losses. So the devices have losses. Now, if I can make these two things similarly in the magnetic devices, during the storage, you have to use the current, and during the writing, you have to use the voltage. If I am using the current-based devices, then my losses are more, and the choice of writing and reading becomes limited because of the interference effect. If I have the four-stage device, if I mix the ferroelectricity and ferromagnetism together, then what will happen? I can control the reading and writing of the ferroelectric memory by a magnetic field which is voltage driven. And therefore, devices will be extremely lossless. Further, these conjugation of four devices, you can write in the cross direction. and therefore the storage capacity of the devices improves enormously. And obviously, there are many fields. I'm not going to discuss the field. You can have the magnetic field-based sensors. You can have the microwave devices, resonators, shifters, delay lines, etc., many. And there are new opportunities that are open up which we have not thought. But what is the problem? Look at the periodic table. All of us we know. I'm not going to tell something new. If I want to have a ferroelectric, what kind of materials I look for? These are the materials. Titanium, vanadium, niobium, tantalum. Okay. Or these are the materials. Lone pair materials, lead, bismuth. If I want to have the magnetic material, then I look for the transition metals, chromium, manganese, iron, cobalt, nickel. And if I want that both ferroelectric and magnetic materials should be there, then one has to look for these so-called lanthanide materials. Cerium, praseodymium, neodymium, prosimium, samarium, etc. So from the chemistry of the material, we know that ferroelectrics and ferromagnetic material, they have very little scope of coming together. And therefore, one needs the special strategy to design the material which will have both the degrees of freedom. Now, what are these strategies? Before we understand the strategy, let us understand that how one can control the magnetic ordering. Magnetic ordering can be of three types. It can be the ordering of spin, it can be the ordering of charges, it can be the ordering of orbitals, and there can be a cross connection between them. Now, all these magnetic effects are the quantum mechanical effects, and therefore they are governed by exchange coupling, what we commonly call exchange interaction. And exchange interaction one can understand. I have shown the molecular orbitals of a metal oxide, and there can be three situations of this coupling, and accordingly we define direct exchange. In the direct exchange, if you see this corresponding figure, what I have shown, okay, there is some inherences. I take my what I have plotted is moments versus metallicity. If you see all these five types of interactions, if you see them carefully, then what you are seeing, even I can't see, I don't know, you are able to see this figure? If the
Yes, sir. Figure is there. We can clearly see the
clear?
figure.
Okay. So
Yeah,
you can see for the indirect exchange, what you require? More localized moments and more metallic correction. For direct exchange, you require more localized moments but more insulating correction. For super exchange, for itinerant, and so on. So there is a, if you see, if I show this figure to some layman, he will say there is a possibility of tuning from one type of exchange interaction to another kind of exchange interaction, because it is the simple question of making it more metallic or less metallic, making it more localized moments to more delocalized moments. This is the only difference. And therefore, changing the magnetic character of material is nothing but playing with the exchange interaction that governs. Then this thing all of us know, but what is important here, that if I can change the magnetic interaction, then what I have to change? Magnetic interaction or the exchange interaction comes basically in one class of compounds known as the correlated oxides. And in these correlated oxides, most of the properties are very well known. Say, for example, in the MOTS insulators, we all know how these spins can be tuned by taking, say, for example, Mn3 plus, Mn4 plus. We all know what kind of interaction will change. just as an example, bismuth ferrite that I will discuss little later, the canted magnetic moment is due to the Zyloshinsky-Moria interaction. We all know. Now this Zyloshinsky-Moria interaction, it depends upon if I have the parallel spins which are separated by the oxygen p orbital. If somehow or other I can create, suppose apart from the iron, if I dope with the chromium, then this spin is affected, and therefore this interaction will be affected. So by changing the spin or the Zyloshinsky-Moria interaction, I can manipulate the magnetic moment of bismuth ferrite, and I can either induce more coupling or I can decrease the coupling. Now, since in this case, I have to change the spatio-modular coupling, I want that this spin-spin interaction must be reduced. So the canting is less, and therefore the antiferromagnetic ordering is smaller and ferromagnetic ordering increases. This has been attempted by various means, by chemical doping, especially at A side by rare earth or B side by transition metals. We will come to this. So this manipulation of ordering, especially in the magnetic ordering, if you want to do, then you have to have a very clear understanding of exchange interactions and their manipulation in the correlated oxides. Now, application areas I will not touch because slowly and slowly I am moving in time. As I discussed, what is the problem and how they overcome this problem? We all know that Astrove in 1960s and Zyloshinsky in 1959, they analyzed the materials on symmetric ground. Like we all know that for magnetic material, how the spatial and time reversal symmetry, they have to be broken. And for the ferroelectric material, which symmetry is invariant, which symmetry is broken. So on the basis of this symmetry analysis, they predicted the magneto-electric effect in chromium oxide I have already shown earlier. And the first ferroelectric material was discovered in 1960. Smolensky also explained that you require the D0 and Dn conditions, and the simplest way is that put both type of ions in one material, and this is what is the first design equals. You put a D0 material in perovskite ion at B position, you put a Dn material at A position, and you will get. And many such materials were discovered in 1960s. Okay. And up to 1980s, Godunov and Longo, they compiled and analyzed all the magnetic perovskites, as I have said, and a comparison was made. The problem was discussed thoroughly in Santa Barbara in 1999. And as a result, as I said, Nicola asked this question. There were two Nicola Hill and Nicola Spalding. And they have taken these 5-6 criteria that what is the problem. And it is a very good reading for the young people to understand what is the meaning. What are the symmetry requirements? It is opposite. For magnetic ordering, you require the breaking of spatial symmetry. For electrical ordering, you require the breaking of time symmetry. On the basis of electrical property, most of the ferroelectrics are insulators, most of the ferromagnets are metals. D0ness condition I have already shown you. Even the size of the cation, it is very important to watch. And therefore, based on this, there was an anonymous understanding that it is very difficult to produce the multiferrate. But then there were two very important developments. Professor Ramesh, who was the keynote speaker in this conference, I suppose, he produced a barium ferrite thin film with a very large pole like this. Wang produced a paper, and at the same time, Kimura group, they published papers giving a new class of multiferroids. And that generated the interest that why it is happening, why we are getting something against the theoretical understanding. And that created questions not only of the application but on the theory side. And these are the things that I will not discuss because all these things I have narrated in my text. And therefore, that you require polarization if you want to reverse, what kind of symmetry breaking you require, magnetization for what kind of symmetry. And if you have to have, these are purely thermodynamic arguments. And if you want to have a multiferroic material, both the symmetries are to be broken. Now, these symmetry broken requirements, how they can be met. Okay. Suppose I have a magnetically ordered material, and if I broke the time reversal symmetry, what will happen? You all know that the magnetic moment will take different direction. So it will, how this can be broken? This can be broken by breaking the, see carefully, this oxygen breaks the inversion symmetry. They are, if I can somehow or other break this particular thing, it will break the inversion symmetry. And this type of effect has been seen in lanthanum copper oxide. This is the typical mechanism that if you change his position, then the interaction starts and you get the weak magnetization here. So magnetic exchange interaction causes displacement of manganese 3 and that also gives a weak ferroelectricity. So not only the magnetization is infused, but it also gives the polarization. And this polarization, as you can see, polarization is proportional to this wave vector. And therefore, a coupling between the magnetization and polarization can be induced. This is one strategy that has been adopted. But the problem is, this coupling is very, very weak. So far, we did not get any material where this coupling can be enhanced. And there are reasons for it, and there are strategies also for it. This is again how this initial state can be changed by time reversal or by space reversal. And if you operate both the operators, then you can have the invariant state or a multiferroic. And this is the strategy how it can be point of inversion on symmetry basis. It can be done. It is operated on chromium oxide. It is operated on this cobalt-based oxide. And in fact, we have developed the magnetoelectric effect. Now, what are the strategies that can be practically adopted? First strategy, we all know that if you have the hybridization of orbitals, as we all know in barium titanate, this is the p and s hybridization. And as a result of this hybridization, one of the titanium shifts towards the oxygen atom, giving rise to the polarization. So if there is no hybridization, this is a purely cubic structure. If there is a hybridization, this becomes a tetragonal structure and so on. So the ferroelectricity is generated by hybridization. Similarly, if you see the electronic structures, okay, we don't have any d electrons here. In barium titanate, you put some element where you can fill this d electron, then you can generate the magnetism along with the ferroelectricity. So this was the first effect, that is by doping A side and B side by such elements where you can generate the hybridization, creating ferroelectricity. You can generate the magnetic ordering, creating magnetism. And one of the important strategy that has been used, that either design a mixed perovskite containing the ferroelectric active ion with a configuration of B0 and magnetic ion with configuration B1. These are known as the complex oxides multiferroids. Then having the magnetic ions with magnetic ordering, you have to change the exchange interaction, and because of this reason, it becomes very difficult to have many materials of such type. And secondly, all such materials which were explored in 1960s, people are still trying to find out ways out, but they have the weak coupling. There is one material, lead iron niobium oxide. This has ferroelectric transition at this and nil temperature this. Lekin this is quite close to the room temperature, but the coupling is very weak. So such type of systems people are doing, but not much interest is here because of the weak coupling. Second strategy is making magnetic perovskite ferroelectric. That is, the idea is to use the coupling between rotation and tilting of oxide octahedra that is occurring in the perovskite. We all know the theory of glacier tilting and how this tilting can be done by simply changing the phases from one symmetry to another symmetry. So that is very well standard thing. Now, if this thing can be done, then it will change the geometry. And therefore, these ferroelectrics are multiferroics are called geometric multiferroics, in which the ferroelectricity appears as a secondary thing. It is not having a ferroelectric origin. Why it occurs? Because of the rotation and tilting of MO6 octahedra, and it creates the structural distortion, and this structural distortion creates the ferroelectricity. This is called improper ferroelectricity or geometric ferroelectricity. And most of these materials have been tried, and YMNO3 so far is the best material for this. Now, there are another sub-strategy in this, what is known as the geometric constants. Geometric constants means space filling. We all know that there is a closed packing, and if I rotate something and there is a space filling thing, then it will create a strain and a structural instability will be there. The free energy will increase, and as a result of this steric effect, there will be a polarity created, a polar state will be created, and this hexagonal magnetites, they are some of the best known examples where the steric indifference is created by changing the rare earth. There are other materials also, but this barium nickel ferrite, this is being followed very closely. These are the mechanisms. I will not go into the details, but essentially what is important here, that the structural instability that are created in geometric ferroelectricity, both these modes, they are having the polarization, but polarization can be switched. So this creates the ferroelectricity, and these layer structures, they are not perovskites, please remember. They are bipyramid structure in which you are having the rare earth ion, and by changing the rare earth ion, you can create a distortion in the AO bond, and therefore the local dipole moment changes. So here there is a possibility by chemical substitution of changing not only the polarization but also the coupling. Then there are various strategies, and this is a very important strategy which has been published in 2018. See, generally, what we have learned in the soft mode theory, that the instability in ferroelectricity is due to the one of the mode becoming softening, and this softening means the mode is having the restoring force 0, and therefore the basic, if you go into the basic soft mode theory, then CM Burma and I don't remember the name, they have predicted that a single mode will get soft. Multiple mode softening is not allowed. But what one can do is that non-soft modes, non-polar modes, if I put together two modes, then they will generate a polarity. And this is a very interesting idea. You have a primary rotational mode Q, Q1 and Q2, Both Q1 and Q2, these are the rotational modes, and I have shown over the figure how you can generate these modes. Each modes put together in a material, they become polar. Individually, they are non-polar, so they are not generating the dipole moment. But if these two modes come together, they become polar. And generating such type of polarity, this is called hybrid improper ferroelectric. So this is again a very interesting idea. You can have a rhombohedral tilt, you can have a orthorhombic tilt. You put together these two tilts and you can generate the ferroelectricity in magnetic material. This hybrid multiferroics, they are the very, very new phenomena, and these phenomena will be especially important in the two-dimensional material, nanomaterials, because they are creating tilts or changing the phases at local level is very easy. In bulk material, it becomes very difficult because the local symmetry does not change the average behavior. Then third, you all know the lone pair driven ferroelectricity. I will not go into the detail because when I am discussing this bismuth ferrite, we will discuss it. Most of the type 1 multiferroics are generated by these three types of strategies. So the presence of transition metal is one way, presence of lone pair is another way, and presence of rotation and distortion creating the steric hindrance and geometric ferroelectricity. These are the three ways of creating the multiferroicity in the essentially magnetic material. Okay. Now, this is one way that you are taking the magnetic material and you are creating ferroelectricity by three ways. Okay. Why can't we do the other way? We have a ferroelectric material and creating magnetic another. So this is the second type of strategy. The first strategy was, this is called charge ordering driven ferroelectric. Now the mechanism is very simple. The ferroelectric and multiferroic behavior, this is possible by having different kind of charge ordering. And this different kind of charge ordering essentially means that you have to broke this inversion symmetry. And one of the example I have given, John Taylor interaction. In the half dope magnetite, if you see where you have the Mn3 and Mn4, and in the magnetites, if you see where you have the D6 and D5. This John Taylor interaction is different, creating the different types of orbitals, and as a result of this, the charge ordering in these materials becomes different, and this charge ordering can be created in one type, which is called checkerboard type of charge order, and this is called side charge ordering, which gives the genotype of Poulin. I will not go into the detail of this, but the different kind of charge ordering gives you the polar distortions that can create the ferroelectric. Then very fundamental change has come up in terms of understanding the mechanism of ferroelectricity. I think my time is over, so I will go very fast. And this is called very-phase approach. In this very-phase approach, the fundamental thing to take home is that purely electronic contribution to polarization without any polar structural distortion may appear and significantly contribute to total microscopic polarization. This is what is the new theoretical background called electronically driven ferroelectricity. So you need not to bother about the polar distortion to be created by structural distortion, and still you can have the ferroelectricity. This is new dimension. These are the type 2 multiferroics where different kinds of spin-driven mechanisms are used to generate the magnetic moments, and electronically driven polarization is used for ferroelectricity mechanism. These are the completely different mechanisms from the type 1 multiferroicity. And there are various possibilities of these magnetic structures. However, all these magnetic ordering does not give you the ferroelectricity. So one has to focus only on cycloidal magnetic structures where you can generate the ferroelectricity. And this has been done in a terbium-based compound in MnWO4. Then there is a new thinking. And this new thinking, you can go to these two papers, Kimura 2003 and 2007. This new thinking is very, very simple. That you look for magnetic material, their phase diagram, and try to find the region where the antiferromagnetic materials are there, and then see what kind of spiral magnetism is there, and those compounds that are having the colloidal phases, look for those compounds and create the ferroelectric field. This new line is being followed in type 2 materials, but the problem with the type 2 material is their coupling is still very, very weak. So using this strategy, there are many new results that are being shown. I don't have time now, so I will not discuss this thing. I think please forgive me because I want to show some results. This paper, since I don't have much time to discuss, please go through this paper, Nature Materials, where Nicola Spalding and Ramesh, they have discussed the various ways of how the future of multiferrocity will change. These are the various branches through which you can have the different kinds of multiferroic materials, and the challenges that are there that has been discussed in this paper. How to combine the two ferroic ordering other than the magnetic and ferroelectric, how to control the ordering, understanding the chemistry of these complex materials, and developing the new characterization tools for associated behavior. Let me go to the second part. Please. This is what is our work, and since I have only 5-10 minutes, can I take 5 minutes, madam? I'll just show some results and then stop. So we all know that bismuth ferrite is a room temperature multiferroic, blah 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 blah. It is very good, but it has certain very basic problems. One, bismuth ferrite achieving in pure phase is impossible. Thermodynamic considerations are there, metaphases are there. Second, it has very high leakage current, so for devices it is not good. Third, it has a very small ferromagnetic moment. How to improve it? I have shown the phase diagram. There are large number of phases where it so it's very difficult. Therefore, the strategy is dope with something so that one phase becomes stable. That was the strategy, and this approach have been used in large number of these rare earth ions and alkaline earth elements have been used to stabilize the single rhombohedral phase. But the problem is, as soon as you put these ions in high concentration, there is a phase transition. So this was the challenge, how to control this phase transition and understand. So we tried to understand using the lanthanum, what is the nature of this transition, and we found that this compositionally driven transition, as reported in earlier reports, it is wrong. And most importantly, after transition, the material remains multiferrous. These are the various things. We did the temperature dependent Raman analysis, as we were saying. This is based on the three papers. One is our paper in 2018. Then Professor Sood, he has analyzed the perovskite two sublattice, and Slojak and Kulaman, they analyzed. Based on this approach, we tried to analyze the Raman spectroscopy, and based on this, what we have inferred that thermal broadening and thermal disorder of the lattice change in bond length between oxygen cation and magnetoelectric coupling. That magnetoelectric coupling can be changed by creating the thermal fission. And then we analyze what kind of electromagnetic coupling changes, and we found that near the nil temperature, there are certain modes which are associated with the VIO phonon. They change drastically, and therefore this magnetoelectric coupling changes becomes very, very strong. To validate this, we did the this magnetic measurement, and we found that this lanthanum dopes, initially the saturation polarization and the remnant polarization as usual is very weak, but the magnetic behavior. This magnetic behavior increases order of magnitude. It is 0.001, it is 0.189. So exchange coupling at the interfaces between the multiple magnetic domains forces the system to act as a natural system for generating EV. And of course, the magnetization is still remains unsaturated. It is having the mixed magnetic ordering, but the ferromagnetic ordering improves. Then we did the temperature dependent study, and we found that this is a very important thing, a new result. I don't know where is my मेरा वो हाँ मिल गया. This is very important. Fill pool and ZFC. Absolutely no change. So there is no spin flipping. This is very, very important because the doping is not decreasing the coupling, rather it is enhancing the coupling. Then we tried also with the V-side doping with chromium also, and we got some very important results, especially the loss becomes very, very small. As you can see, the 10 delta decreases drastically. And we have also done the complete impedance analysis and tried to find out which component is having the change in the resistance. And then finally the magnetization and especially the MC magnetocapacitance increases drastically. And this type of observations are reported in other multiferroids, but this is the final proof of strong magnetoelectric coupling in BiFeO3. And still some more efforts we have done, but I think based on the phonon behavior, we have tried to understand why this coupling is getting enhanced. And now we are looking for B side reduces the loss, A side induces the coupling. So co-doping of A and B side appropriate element in BiFeO3. This is what is our aim for future. I think with this we stop here. Thank you very much. Yes, madam, I have finished. Thank you.
Very nice lecture, Professor Bajpai, very informative lecture. Really, and thank you very much for the beautiful lecture. It was very informative, Professor Bajpai.
Thank you, sir. Should I remove the presentation? Hello.
Thank you, sir. Thank you very much.
Thank you.
Ajay, your chairperson, Ajay? Okay, he's somewhere out of. Okay, so there are
In,
questions.
in,
Sir, I
in case of any question, please, I will be happy to answer.
there are. Sir, can you suggest some good books for new researchers like me to understand basic of this field, especially multiferrocity? This question has been asked by Vaidhi Deshmukh.
Okay, there is a very good book by Bosnov. It is published in 2015, and then there are very good review articles by especially Nikolai Spalding. There is an article in Nature. It's not a research article. It is in Material Today, written by Professor Ramesh. And this gives a very clear understanding of what are the directions in ferroelectric, multiferroelectric. Then there are a number of books. Nicola Hill has also written a very good book on multiferroelectric. And there is a series of review articles in reviews of solid state and material science, published by this, I think, Wiley or Wiley, yes.
So, whether are you satisfied? Have you got?
Or you can give my email. I will send the articles to the participant today itself. I have a number of articles I can send.
Okay, okay, okay. So now there is no any other question I received. So I thank you very much, sir, for
Thank
such
you.
a wonderful talk, and it's a very basic talk actually. I like. So thank you very much, sir, once again, and you are always the guide. You are always our mentor. Sir, one more question, just a student type. We talk of polarization, magnetization, magnetic moment, etc. Can you please throw some light on what is spin?
What is?
Spin. S-P-I-N.
Spin.
I
Okay.
think.
In fact, it's one of the most difficult question because no one knows what is spin. Initially, to understand the behavior of electron quantum mechanically, the concept of spin was included by hand. And this is why Pauli explained the nature of fermions by constructing the Pauli matrices. So up to Pauli, we didn't know what is the spin of the electron because electron is not a classical particle, but we used to explain that let us consider electron as a sphere and it is revolving on its own axis. So this creating the magnetic moment and the direction of this magnetic moment defines the electron spin. But this was a classical idea, not actual picture of electron. The spin of the electron came actually inherently when the Dirac gave the theory of electrons. And there the Dirac spinors defines the spin as the inherent property of a quantum particle where it decides the distribution. So that Fermi-Dirac distribution function that we used, and it defines the types of interaction that the electron will have when they change the position. So, in fact, I really don't know how to define the spin theoretically, but this is how we try to convince ourselves that this is the meaning of spin. But certainly the effect of spin we all know. But from where? Because it is not the kind of spin we have classically in the rotating particles. It's something much basic to the nature of the world, like we don't understand what is the meaning of wave particle duality or the dualism in the nature. Similarly, we don't understand what is the meaning of spin in electron, except that this is the inherent nature of the quantum particles where they possess this kind of operators that create certain effects. So in terms of mathematical jugglery, in mathematical model, we know the operators, we know its effect, but we really don't understand quantum mechanically how to visualize the spin of the electron. because it is not a real world. We can't visualize these particles in the real dimension. They are in the what we call infinitely large vector dimensions, vector space. And therefore, having such particles, realizing the picture of spin, it will be a myth. But working with the electron spin is very easy. So when we say spin ordering, it is the ordering of magnetic moment associated with the electron. But the genesis of it, how it is arises, because it is not a particle localized completely. It has a de Broglie wave associated with it. So whenever we are saying that this is the magnetic moment, it is essentially the expectation value of the magnetic moment or the average value coming out from the average spin. But really, I don't know how to define the electron spin. Maybe if somebody knows.
Sir, may I add here a little bit?
Hello?
Hello, can I add here a little bit? This is Dr.
Sure,
Smita
sure,
Chaturvedi.
sure.
To understand very simplistically, the electron spin is a basic property of electron like mass and charge. So when we define an electron, these three properties are important, and its spin is one of the properties. But of course, sir, you have given a very comprehensive definition. I'm just putting it in simple words.
Yeah. No, you are right. What I'm trying to make students understand that quantum mechanics is not to be visualized the way we visualize classical mechanics.
Right, sir. We cannot.
It's an abstract idea, and we work in a different space, and therefore mentally we have to be there. We cannot visualize every quantum mechanical effect the way we visualize the classical mechanics.
Right.
So, Professor Acharya, can I take leave for 10-15 minutes?
Thank you. Thank you very much, sir.
I will join again. Thank you. Thank you. I will come for the next session. Next session is after this session. Any other session, or this is the last session?
Hello, can you hear me? Professor Lad?
Yes, madam. Yes, madam.
You are here? Okay, you say the thanks to this Dr. P.K. Bajpayee sir, and start the new lecture. Kamal Prasad.
Next lecture. Thank you very much, Bajpayee sir. We are too privileged to have sir with us. You are give informative, insightful, informative lecture. Thank you very much, sir. Now, next invited talk, Dr. Kamal Prasad. Dr. Kamal Prasad is a professor, TM Bhagalpur University, Bhagalpur. He had been professor and head at Aryabhatta Knowledge University, Patna from 2013 to 2017. Associate professor at Central University of Jharkhand, Ranchi from 2011 to 2012. Sir received his PhD degree from TM Bhagalpur University on the ferroelectric ceramics. His area of specialization includes electronics and radio physics, condensed matter physics. Today, sir delivered the talk on energy harvesting from 0.3 non-lead ceramics polymer nanocomposite. Sir, you have 45 minutes.
Yeah, but can I start?
Yeah.
Okay. Yeah. So good evening, all of you. At the outset, I must thank the organizer of this conference, National Seminar on Ferroelectrics and Dielectrics, especially Professor Sumita Acharya, for providing me an opportunity to talk on the topic energy harvesting from 03. This is the type actually, non-lead ceramic polymer nanocomposites. So I have divided this talk sheet. During listening Professor Bajpayee's talk, actually, which was very informative and interesting talk. So I removed few slides from my presentation. So I will conclude this presentation within 30 minutes or so, because we are running short of time. So, so basically there are three pillars for the development of modern society. We consider this. First is information, secondly energy and materials. So materials play indispensable role in the development of humanity as a whole. So today's talk is related to energy harvesting using certain type of materials, which is composite one. So ceramic polymer composites, we are using material for energy harvesting. So energy harvesting is nothing, but it is a process by means of which energy is extracted from naturally occurring sources, which may be generated or extracted macroscopically and microscopically on micro scale and macro scale, like solar energy, wind energy, tidal energy, geothermal, and so on and so forth. And energy can be harvested at micro scale, maybe electromagnetic radiation through mechanical energy or heat energy. So mechanical energy may be harvested through this piezoelectric phenomena, electromagnetic or triboelectric phenomena. So energy harvester basically provides a very small amount of energy for low energy electrons. We are no way concerned for today the macroscopic scale energy harvesting, rather we are interested in microscopic energy harvesting through ceramic polymer composites. The converted energy can be stored either in the form of a capacitor for short-term storage and through a battery for long-term use. So why we are interested in energy harvesting basically. See, and we have different kinds of materials which shows variety of properties associated with it, like piezoelectric, pyroelectric, and photovoltaics, and so on and so forth. So we have different kinds of materials. So in today's talk, we are using this piezoelectricity for energy harvesting. So all of us knows that the piezoelectric effect is nothing but we apply pressure we generate mechanical strain in the material so that we have electric current. And just conversion of it or converse phenomena are also there. If we apply electric current or potential across such type of material, then mechanical strains are being developed, which can be visualized by this slide picture. Deformation, we deform the material so that strain are being developed here so that we get voltage. And there are certain kind of material which if we apply voltage, then it will be deformed like this. And one thing must be kept in mind that such type of energy harvesting can produce the power of the order of milliwatt range. One of such example is the dancing power generated from dancing floor. One can have different types of activities like human motion, acoustic noise, vibrations, or pressures. So combining together, we can generate electricity through this such type of flow for us. So this is very useful phenomena, and we can have many applications out of it, like handheld devices, light bulbs, and so on and so forth. Then we come to the nano composite. What are composites basically? It is nothing but it is if we have a judicious combination of two or more materials that produces synergistic effect, a material system composed of two or more physically distinct phases whose combination produces aggregate properties that are different from those of its constituent individual elements are called composites. If one of them or more of the filler components are at nanoscaled material, then it is called nanocomposite. So there are two terminologies basically used in composite science and technology. One is the fiber or dispersed phase, and another is matrix. Dispersed phase are discontinuous and surrounded by matrix, and matrix are generally being used for binder which is continuous one. So this is called primary phase, and this is dispersed or fiber phase is called secondary phase. So dispersed phase may be aligned one or maybe random one. So we are using this random phase in 03 composite. So why we use basically composites? So composites are basically used to optimize most useful property of two phases which are not ordinarily appear together, either in the form of ceramics or in the form of polymers. So if we look at the connectivity arrangement, then we have 10 types of connectivity in case of polymers and ceramic composites, or metal composites, or metal ceramic composites, and so on. So, but in this talk, we are interested in 03 composites. 03 means if the particles are randomly distributed along X, Y, and Z direction in the polymer matrix. Why we have considered this? Because it is very economical in fabrication and it is easy to fabricate such type of material in the lab scale or even industrial scale also. So for today's talk, we have I have considered two types of ceramic material. One is BCZT, which is barium zirconium titanate and barium calcinate titanate combination, and 50-50 combination of these two ceramic at 50% X50 mixed with PVDF, so that we have PVDF, BCZT and NBT composites. So BCZT ceramic system were prepared by standard solid state reaction method, and you can see the beautiful XRD, all are single phase material. This is simple SEM of all those materials. So dielectric measurement showed that it has, apart from that low temperature phase, it has got high temperature phase also, around 400 or 500 degrees Celsius. So this was authenticated by high temperature X-ray study, and accordingly the phase diagram was given for high temperature. Phase diagram was given for BCZT system, which was published in 2017 by our group in Ferroelectrics. So actually you can see from, if you highlight this peak position here, then you can very easily see that the peak obtained in XRD at room temperature is here around say 33.7 or something like that. But if you increase the temperature at 50 degree or something, its peak is around 32 point something. So it's shifting towards left, and then you just see here up to this, it is shifting towards right, and then again at up to 500 degrees centigrade, and then again at 600 it is shifting towards left here. So there must be a phase here, and you might have observed that phase is here. So from this we could generate the phase diagram, high temperature phase diagram for BCZT system. So we took the morphotropic phase boundary combination of BCZT at 50% combination, BCT and BZT combination with PVDF, and which was produced by melt mixing process. Very standard technique. This is X-ray for BCZT, single phase. This is PVDF, and this is for composite. Single peaks very easily shows that all the composites were formed. This is SEM picture. This is TEM, because this is ball milled barium titanate composite. Oh, sorry, BCZT ceramic. This is optical microscopy picture, which clearly shows the flatness of the composite sample. This is SEM. This is for PVDF, and this is for 25% BCZT combination with PVDF composite. This is AFM, beautiful phase appeared, and this is similarly the second composite what we prepared was NBT PVDF nano composite, which is again single phased formation of nano composite form. In SEM, this is AFM picture, again surface of the composite sample, and then we measure the dielectric properties and the piezoelectric properties of both the composites. The dielectric constant loss tangent, the piezoelectric coefficient, and soar D hardness, which were found to be increased in the increasing mode by increasing the percentage of BCZT50 in the composite matrix. And also figure of merit, which was calculated from this formula D33 into G33, is also get increased by increasing the composition, means ceramic content. And of course, dielectric loss is of the order of 10 to the power -2, which is very good for sensing applications. Similarly, the similar results were found for NBT and PVD composites. Let's see dielectric constant and loss, similar nature, what we observed earlier, and hardness also get increased by increasing the ceramic content in the composite. And D33, the piezoelectric coefficient is also increasing by increasing the composition. So basically this talk is related to energy harvesting. So what we did is we prepared this particular setup, experimental setup in our lab. This is base, all are covered and vibration free on the vibration free table. And this is base, solid base. This is test material, and this is copper plate, very thin copper plate. And this is and then we took a rod which was, and these holes are there where we insert some pin, and this standard weight of half kg is allowed to drop from these heights, so that we have different energy or impact energy generated on this test sample. And this was connected to digital storage oscilloscope, and which was, and data were taken care of by this PC connected to it. So upon impacting on the sample like this, by dropping this weight on the sample, we received signals with time, signals in the term of voltages. So you can see the signal strength increases with increasing the compositions from 0 to 25%. Strength increases and peak shift towards right. So by increasing the BCZT content, the contact voltage increases. Let's see for all the composition. And similarly, if we increase the height of impact, then also contact voltage increases. Why? We are height of impact means we are increasing the amount of energy or mechanical energy, impact energy on the surface of the composite. So signal strength or contact voltage increases with the height of impact as well as BCZT content. Similarly, we converted this voltage into electrical energy, and again we saw that if we increase BCZT content, then also the output, the energy output get increased, and upon increasing the height of impact, also the energy got increased for all the composites. So generated energy increases with the height of impact as well as the BCZT content. Then, yes, you see such type of experiment, see force applied mechanical force calculation is very important, because how much force we are putting on the material is very important. So we have calculated the force from this relation, voltage into area divided by G33, the voltage coefficient, and the thickness of the material. So we could calculate the force. The height of impact was 6, 9, 12, 15, 18, and 21 centimeter. So we converted this into mechanical energy by putting mgh or something like very simple calculation, and calculated F3 by this formula. So by increasing impact height, the force of impact is getting increased, and by increasing the composition, this force get decreased. You can see force of impact or impact force is getting decreased, while the voltage coefficient getting increased. This is very important for energy conversion or energy harvesting application, G33 parameter. So it is increasing by increasing the composition. Certainly it will increase because we are increasing the ceramic, piezoelectric ceramic content in the composite, and piezoelectric ceramic content means we have higher and higher piezoelectric material or dipoles, so that we get higher response, and higher response means higher value. Similarly, this is for NBT, PVDF composite, where also similar results are being found. You can see that signal strength are being increased with the increase of composition. Composition means ceramic content, NBT content, and peak shifts. Peak are not occurring for all the composites at the same position. And similar result for voltage, contact voltage in NBT also. You can see, and if we increase the NBT content, voltage get increased for all the combinations. And if we increase the height of impact, then also voltage get increased. Because more and more dipoles are getting aligned, so we have more and more better response with the height of impact. So signal strength and contact voltage again increasing with the height of impact and NBT content. And again, same voltage with the help of MATLAB, we converted into electrical energy. So, and that electrical energy again got increased with NBT content, and with height of impact, energy get increased for all the combinations of NBT PVDF composites. Again, similar results are found, could be seen in NBT PVDF composites also. With increasing the composition, G33 value increases while F33 get decreased. But you can see up to 25% it has got decreased, and afterwards it got little bit increment where observing NBT. So why it is so? So basically, when we apply load or impact the material, what happens? The normal stress on the nanocomposite will produce a shear strain on the components, shear stress component on the grains of the ceramic particles here, and will cause oscillations of PIO or ZRO dipoles within the grain. And secondly, what happens when we apply load or impact the surface? Then it varies. It can cause the variation in the dimension of the sample, and consequently may undergo the change in the dimension of PiO6 and ZRO6 octahedra, causing thereby the variation in the separation distance of the dipoles, which gives rise the time varying dipole moment and consequently the electric signal. And during impact, another thing what happens is the positive charge or free charge on the upper electrode, it starts moving towards lower electrode, giving rise to the positive signal here. And similarly, upon releasing, the reverse signal get reversed due to movement of electric charges in another direction. So this is the reason why we get signal upon impact. So many applications are possible due to this. So such type of nanocomposites could be utilized for structural health monitoring, different sensing and or energy harvesting applications. So for energy harvesting application, you must have realized that the signal was in AC form. So just to convert those signals into DC, we used such circuit, which is shown as inset of this picture, the bridge rectifier, and after that we have a smoothing circuit like RC circuit, RC network, and then the output of which was connected to DSO. So you can very easily see that the voltage output after utilizing such circuit with the material, composite material, we have DC output, very beautiful DC output for the resistance value 47K and for the capacitor value 100 picofarad. And if we increase the value of capacitance, then the value of voltage output get decreased. So by increasing capacitance here C, voltage get decreased. So, but thing is that we have very beautiful output in the form of maybe around 0.327 or 0.327, of course, exactly, volt generated from the impact of 21 centimeter height. So such type, and for students or beginners, one can realize such type of applications. I have shown here one circuit. This is a very versatile circuit using IC timer 555 in a stable mode connection, and here the capacitor is being replaced by our own fabricated capacitor using both the composites, and we allowed to drop a steel ball from different heights. So what happens if we allow this ball to impact on this surface with different height? The output at pin number 3 gets enhanced. The duration W is increasing, because if you have any, if you remember that time period is directly proportional to R and C. So if we allow this ball to fall on the surface, then C increases, capacitance get increases because it is piezoelectric nature of ferroelectric. So the electric constant increases, so certainly this width will also increase. So student may use such idea in their own lab so that they can make any kind of sensor, maybe pyroelectric, maybe piezoelectric or something, some sensor out of it, out of such material, like by connecting your material between pin number 1 and pin number 2 or 6 and apply pressure or apply temperature so that you can make a sensor out of such material. So energy harvesting technologies are everywhere and efficiencies are vastly improving. Thank you. I could finish within time as I promised. So,
thank you very much, sir. Dr. Kamal Prasad, sir. We are glad to have you, sir. Thank you, sir, for such innovative talk and new topic, energy harvesting from 0 to 3 non-lead ceramic and polymer non-composites. Thank you. Thank you very much, sir.
Thank you.
Next talk, contributory talk. Dr. Smita Chaturvedi, Department of Physics, Savitribai Phule University of Pune. Dr. Smita Chaturvedi, madam.
Yes, sir, I'm very much here. Should I start sharing my contents?
Okay.
I think you have to enable me. Yeah.
Yeah. Dr. Smita Chaturvedi is presently Assistant Professor in Physics, Savitribai Phule Pune University. Namaskar, madam.
Namaskar, sir, and thank you so much for the opportunity. I'm trying to.
She obtained her PhD degree in 2003 in specialization solid-state physics from Rani Durgavati University, Jabalpur, Madhya Pradesh, India. Her field of interest include multiferroics and magnetic nanomaterial, structural and physical properties, investigation and optimization to achieve multiferrocity for compact and ultra-low energy device application, nano generator application. She had been on several prestigious positions as project scientist. She got Professional Excellence Award, Nehru Academic and Professional Excellence Award 2018 to 19. She has around 30 publications in peer-reviewed journal of international repute, 7 in conference proceedings. She had completed project at Synchrotron collaboration, Germany collaboration. She is full member of Organization for Women in Science for Developing World since 2016. Welcome, Dr. Smita madam, and today she has delivered on the topic multiferroics, a possible solution for the IoT energy challenge. You have 20 minutes, madam.
Yes, sir. I will stick to time. Thank you so much for a kind introduction. And before I start, I want to thank you, Professor Acharya and the organizing committee for making me part of this NSFD 2021. And I'm really enriching my experience. I just heard Professor Prasad and Professor Bajpayee and very insightful talks they have delivered, much detailed insight of multiferroics. So I am deviating from that detailed or basically more into core hardcore physics for today. So I will talk about multiferroics, a possible solution for the IoT energy challenges. So basically I will talk about what is Internet of Things and how as a scientific community we can contribute in overcoming the challenges that it brings in front of us. So we will look how multiferroics are useful and actually crucial and essential to address the problems which are related to IoT. And then I will very briefly show what we have done in this direction on lutetium ferrite material, nanofibers and nanoparticles. So I hope to finish in 20 minutes. Sorry, is someone saying something? Okay, so I will start with the word smart in my today's talk. So we all are fascinated with the word smart so much that we want our kids to be smart. We set smart goals, and that's why we want smart things around us. So we want smart city around us, smart cars, smartphones we are already using, smart highways, smart factories, and in the end, we are going towards a smart world, right? So what does it mean? What does this smartness inculcate actually? So to understand, consider a scenario where you have had a long day and you are returning from your office in your smart car towards your home. You have to travel about half an hour, and you don't want to wait when you reach at home. So it's the month of January and it's very cold outside. You want the temperature of your home to a certain temperature. You want your water, shower water to be at certain temperature when you reach. You don't want to wait. And once you are ready with the shower, you want your favorite coffee to be ready. All this you can operate and manage while you are driving. So this is what the smartness is, and this is what Internet of Things is all about. So how is it possible and what does it mean? It means everything is everywhere. Everything is smart. That means large number of microelectronic devices are connected with each other. In the end, huge machine-to-machine, person-to-person or machine-to-person connectivity is established. So it is all achieved by connectivity. We have created a digital nervous system around us, and we have lots and lots of sensors which sense and measure physical quantities and convert them into digital representation. So essentially, Internet of Things is, as if you can see this circle, this defines very much the essence of Internet of Things. Anything, any device, anytime, any context, any place, anywhere, any path, any network, anyone, anybody, and any service and any business, everything is connected with each other. Now, this sounds a little complicated and huge. So how is all this achieved? So this is achieved by installation of sensors and devices everywhere. So if we look at data, so 26 billion installed units are there by 2020, 30 billion sensor-enabled objects connected to networks by 2020. And if we look at in the totality, 2012 billion sensor-enabled objects by 2020 will be installed. What does this mean in terms of numbers? So 212 billion objects actually is 28 times of the total population of the world. So there are more, much more. 212 billion is 28 times. So 28 times object than the population, than the people available. So where are we leading? Where is this leading us? So to understand, so everything comes, every good thing comes with challenges. So it is leading us to certain challenges. Now, there are several challenges. We will not look into all of them, but we will just look into those challenges which as a scientific community we can address, okay? So we will see big data and connectivity. These two issues are very, very important, and they are all connected with the large number of microelectronics which is needed to implement the Internet of Things efficiently. So if we continue with the same pace and we don't change in our approach, like in terms of materials or in terms of technology, so by 2030, that means within a decade, we will be consuming 40 to 50% of the global energy just to sustain the Internet of Things. I don't think, and I think you would agree, it is not possible to do so because we have other needs other than Internet of Things, and energy is needed, but energy is limited. So we need to change something. So first of all, let's see, can we fulfill such energy requirement? So actually, nahi, not even close. More microelectronics means more devices, more power requirement for such devices, and requirement will become beyond availability. So then what we need to do about it? We need to, as a scientific community, as a good scientist, we need to look at the future sensor trends. So we need to look at what kind of sensors are required for this technology to sustain, because it is essential. We cannot avoid Internet of Things because it is needed. It is need of the era. See what requirements and how those requirements can be compensated in terms of totality. So future sensor trends shows, like I have shown it here. So there are several kinds of sensors, but we will focus on magnetic and electric sensors. And as you can see, the magnetic and electric sensors together are actually 14% of the sensors, which is more than any individual sensor here. So they contribute, the magnetic and electric sensor contribute to a larger part of the Internet of Things. So how about we have magnetic and electric sensor combined? So that will help in one way, that we will have electromagnetic devices, okay? And that will compact the device because the two functionalities are combined in one device. And then also we can achieve multifunctionality with the device. So if we look at the trend, we now know that we need sensors which are cheaper, smaller, more power efficient, and easier to use. And materials and devices that we are looking for should be compact, low voltage consuming, low power consuming, and they should have low leakage current, so that we every now and there we can save the power, save the energy. So as a gist, we can say electromagnetic devices are desirable and compact devices are desirable. Now, so that means we need to scale down the devices, but can we really scale down further? So as many of you must be knowing that Gordon Moore, who was co-founder of Intel, he in 1965 predicted about scaling of devices that number of transistors on an IC doubles every 2. Now, if the number of transistors is doubling, that means the size of transistor is shrinking, right? And speed of computer doubles. Obviously, the number of devices or number of transistors are increased, so the operations are increased and the speed of computer. And that was true. And since 1970 till 2016, it has stood true. But now what? The size of individual transistor was continuously shrinking. In 2015, the size of transistor was 10 nanometer. 2017, the size became 7 nanometer. And now we are at 2020, around here, we are at the atomic level. So now we cannot reduce the size of the transistor. That is for sure. So we need to change something else. We cannot shrink the device in terms of its elements. So what we need to do, we have reached the fundamental size limit at which a transistor can be built. Now, how do we go beyond this wall? So we have to go back to basics. So to achieve beyond Moore's law, at present, we know that we are using charge of electron to encode the information, which is 0 and 1. Now, what if another fundamental property like spin of electron is also used? So that is the fundamental idea behind multiferroicity. So combining spin and charge, I will actually rush through here because we have heard a lot about basic properties of multiferroids, but I will still just touch it. So if we combine a ferromagnet and ferroelectric, spin of electron is combined with charge of electrons. And then what happens? We a combination of these two properties, but like Professor Prasad and Professor Vajpayee insisted, just mixing the material doesn't help. You have to have coupling, you have to achieve coupling. So there are different ways. I will not go into details, but you have to achieve coupling. You have to make sure that there is coupling between ferroelectric and ferromagnet. And once you have achieved the material that you have now is a multiferroic material, where you can control the magnetization electric field, or you can control the polarization by changing the magnetic field. So what is ferroelectric? Spalding's very famous ferroempty or fully deep orbitals. So there is a chemical incompatibility. So within one material, achieving both the things is impossible. So you have to find another way. So is there any material in which these coexist? How to combine ferroelectricity and magnetism in one material? So there is one material which is widely studied. It is bismuth ferrite. It tweaks kind of the criteria for multiferroicity, multiferroic material at room temperature, and it is the only one so far. So it also shows ferromagnetism and there are problems. There are problems with PFO. Problems like high it has weak coupling again. A lot of people are working in this direction. So Professor Bajpayee also mentioned for the work in nominated, he did not get the prize, but it's a big thing. So you can imagine how big is this problem and how important is this problem as a scientific. Therefore, not effectively disease. So there are a series of rare earth orthoferrites and rare very upcoming material and so like with the dynamics of 3D 4F interactions, and that allows you to play with the properties. So we have recently done some work on biphasic lutetium ferrite, and where we synthesized nanoparticles and nanofibers of lutetium ferrite. I'm not calling it lutetium orthoferrite because we also got hexagonal phase and we got orthorhombic phase, both the phases. So in both type of morphologies, we got a different percentage of ortho and hexa phase. Okay, so this is what exactly we got. So in nanoparticles, we got 73% of orthorhombic phase and 27% of hexagonal, while in nanofiber, we got 27 and 73. So it is established that orthorhombic symmetry favors magnetic behavior and hexagonal symmetry supports polarization in the material. So now we have both in the same material for both the properties, ferroelectric and ferromagnetic. That's what we did. So we looked for the electric properties, ferroelectric properties, and we realized that nanofibers show good ferroelectric properties as compared to nanoparticles. And also when we tested this material for nano generator, we could generate about 7 volt around, less than 8, a little less than 8 volt. So it was a good work, and we have published it recently in nanoscale in 2018. Further, we looked for magnetic behavior in the same material, same or 2 different material, and we compared them, and we found very significant differences in nanoscale magnetism of both the materials, and it is due to morphology difference as well as the percentage of ortho and hexa phase that we have achieved here. So if you are interested, I can go in details, but since the time is limited, I will rather finish it, but I have given the reference. If you would like to see it, it will be good, and you can always email me and let me know if you have any questions about these works. And I will just about what morphology and chemical pressure really matter. So we have tried to pick up 3 different rare earth ferrites, samarium, holmium, and lutetium, on which samarium orthoferrite we have worked a lot in previous times, and we have published 2 physical review papers. So we have now, these are actually X-ray diffraction data, which is converted into electron density by the ritual refinement. So we have done synchrotron X-ray diffraction, and we have refined the data, and we got the electron density for different planes. And we see that there is considerable difference in the polyhedras. So this is one future direction where you can play with the chemical pressure and morphology. The other thing you can do is you can plan structures like multi-layers, heterostructure, superlattices using pulse laser deposition and other techniques. And you can design, you can take some ferroelectric layer and then compress it with the ferromagnetic layer or insulator layer according to your property or multifunctionality that you want to look for. So these can be done. And further, you can see this very famous diagram by James Scott, who is called father of ferroelectrics. And I really love this diagram because it is very comprehensive. It gives you good insight of the materials that you can work for multiferricity. So you can make double perovskite, you can make complex oxides with ferroelectric ordering, you can take complex oxide with magnetic orderings and piezoelectric characteristics, and then you can combine them depending upon which kind of device you are looking for, which kind of sensor you are looking for. So yeah, these are the possible future directions. But I would be had the opportunity want to. So possible solution to summarize for Internet of Things, multiferroics are one of the very potential solution, and I believe it, and many people believe it. People are already working. Intel, Microsoft, they are already working on these materials and the solution. So if we all can pitch in India, we can do something nice for Internet of Things. Yeah, so before I end, I would like to acknowledge my mentors and my colleagues and my students. They all have contributed equally and they have inspired me always. So I'm really thankful to all of them. And if you have any questions, I'm open for that. Thank you very much.
Thank you, Smita. So nice and informative lecture.
Thank you, ma'am.
Yeah,
I hope I could do justice in such little time because I understand everybody's tired and I have really rushed through. I have cut down to contents so that people will not get impatient.
No, Smita. Yeah, sir.
Can I ask a question?
Yes, please.
Not a question, actually, it's my query. These 2 were very wonderful papers I have read, but 2 information I want to know. In your these compounds, these are thin film or bulk?
Sir, give me a minute. I couldn't hear you. Can you please repeat now?
What I am saying, this LuCuO3 that you have prepared, this is bulk or thin film?
Sir, it is nanofibers and nanoparticles.
So basically,
so it's a powder form.
Bulk nanopowder. What was TC and TN?
Sorry, sir?
What was the Curie and Neal? What was the Curie and Neal temperatures for these materials?
Sir, it's around Curie Neal temperature. I can tell you right now, 640. And I think I have a slide here.
Both are above room temperature?
Yes. So, yeah, here. So I did not put this slide because of the.
Okay.
So
And
here is.
Final question. Have you
Yes,
tried to find out the coupling between this
Not yet,
ferroelectric
sir.
and
We don't have the facility right now, but I'm looking for an opportunity.
I tell you a very simple experiment we did. Take the temperature dependent Raman, and there will be a change in the there will be a change around nil temperature. If that change is there in some of the modes, that is the confirmation of coupling.
Okay, sir. Thank you so much. I will do that as soon as I can. Thank you so much.
This is very, very important because more change means more coupling.
Right, sir. Okay.
That will be very nice. Very nice.
Sure.
Very
sure,
nice.
Sir.
Thank you.
Thank you, sir.
Smita, one more question is asked by Muzaffar Iqbal. He says, can we explain the passive infrared PIR sensor in multiferrite material? Passive infrared PIR sensor.
Right now, I cannot correlate IR detection with multiferroicity because I have worked on infrared detectors and I have used different materials, but not the multiferroics. But I can definitely look into it and I will get back to him. He can email me and he can find my email on my website.
Yeah, Muzaffar, have you listened to ma'am? So, okay, sir. He said, okay, we will discuss with you.
Sure.
So, once again, thanks, Smita, for such a wonderful lecture, informative lecture, and sharing a lot of data with us related to ferrite system, orthoferrite system, because it's most lovable to me also, orthoferrite system, and it's a more exciting property. This system is showing more exciting property with small dopant change. So, thank you very much for sharing this information. And our last oral presenter.
Thank you, ma'am. Before you start, thank you so much. It was all my pleasure. And I am also enriched. Thank you. Thank you, sir.
Thank you very much. Now, the next last oral presentation of this session is by Dr. Vikrant Yashwant Ganvir. Okay, he is from Yashwantrao Chauhan College of Engineering, Nagpur. He is going to present his work, The Effect of Lanthanum Oxide Addition on Physical, Electrical and Dielectric Property in Lithium Borosilicate Glass. So, Ganvir, are you ready? Okay, welcome, Ganvir.
Okay. Good evening to respected. Audible, ma'am?
Yes. Proceed, Ganvir. Yeah.
Okay. Respected jury members, panelists, chairperson of the session, and my dear friends. I, Dr. Vikrant, as assistant professor in Yashwantrao Chauhan College of Engineering, Nagpur, going to deliver a oral on presentation on topic the effect of lanthanum oxide addition on physical, electrical, and dielectric properties in lithium borosilicate glasses. Outline of my presentation: introduction, material synthesis, material characterization, so exerted density FTR, result and discussion, followed by conclusion and the references. So what is the importance of rare oxide doped glasses? So rare earth oxide doped glasses is a long history in optical, electrical and magnetic applications. So here rare earth elements promotes the crystallizations in the glasses and which increases the electrical conductivity, it is reported. And such glass ceramics can be have potential applications in the field of solid state electrolytes. So here in the present study, lanthanum oxide is a potential candidates which we have used for modifying various physical electrical properties of the glasses. So in the present work, we have used Melquen's techniques for the synthesis of the glass. System is 30 Li2O, 70 minus X, 1 by 7 SiO2, 6 by 7 B2O3, X LiO2O3, and X, that is lanthanum oxide, is varied from 0 to 2 of 0.5. So here you can see all the materials, the chemicals which we have taken, it is weighted in the beginning. Here B2O3 is hygroscopic, so it is first at 400 Kelvin. So all the chemicals were of high purity, merc grade quality. Then it is weight mixing was done in azide mortar. So weight mixing in acetone was done. So to ensure the homogeneity in the final product. Then after it is dried, that it is kept on a platinum crucible. That platinum crucible is kept to the furnace around 11,000 degrees Celsius. Then it is intermittently stirred to check whether the homogeneity, to ensure the homogeneity in the glass melt. Then it is conventional quenching technique was used to just take out that particular melt, and we have used such type of rectangular and cylindrical molds for the preparation of glass samples. Then those glass samples were kept in a for annealing to remove the thermal stress developed during the heating. Then finally the glass is prepared. So then that particular product was crushed, polished as per the requirement, characterization requirement. So composition of glass samples, we have used Li2CO3, B2O3, SiO2, LiO2, and then the naming which are used 0 BSLi, 0.5, 1.1, 1.5, 2.0 like this. So characterization of material. So we have done here XRD to confirm the amorphous nature of glass samples. Density measurement we have done. FTIR spectroscopy to know the various structural groups present in the glasses. High resolution dielectric analyzer NOAA control technology we have used for electrical measurement. And finally, we have correlated the electric properties of the reported glasses. XRD spectra. Powder XRD spectra shows only humps and no any sharp peaks, so which confirms the amorphous nature of the glass samples. We have then measured density. So this shows that density of the glass samples increases with the addition of lanthanum oxide. So it is attributed to the higher molecular weight of lanthanum oxide. So you can see here lanthanum oxide exhibits the higher molecular weight. So and lanthanum oxide is added at the cost of glass formers, that is B2O3 and SiO2. So that's why ultimately the density is going to increase. Again, here it can be seen from this figure that the molar increase. So this is also attributed to the larger ionic radius of La3+ ions. Here actually what happens, lithium is constant, lithium oxide is constant, and so what happens here, lanthanum is added at the cost of that B2O3 and SiO2. So what happens, the mobility of here conversion of BO3 to BO4 is taking place, so which prevents the mobility of lithium ions, lanthanum ions, and that's why there is a reduction in the vacant site for mobile lithium ions, and hence the molar volume increases. So different physical parameters we have calculated, which can be seen here: density, molar volume, ion concentrations we have calculated from using the formulas, and you can see lanthanum ion concentration is going to increase at the addition of La2O3. Of course, if there internuclear distance will decrease, so internuclear distance is going to be decreased. Polaron radius we have measured, it is found to be decreased again. Field strength is found to be increased. So these physical properties play a very important role in understanding the arrangement of atom in the glass structure. FTIR spectra. So FTIR spectra shows the different functional groups present here. So here the band present at 4 centimeters to the BOSI stretching. Then again here the very important bands 819 and 943, 819 and 943 develop. So that is assigned to the BO4 unit. So here what happens? The conversion of BO3 to BO4 is taking place. Again, here there is a slight shifting of two bands. That is 943. Band at 943 is slightly shifting towards lower wave number side, and at 11 centimeter inverse is shifting at stored higher wave number side. So what happens? Shifting of bands also confirm the structural changes is going to be taking place here, as well as conversion of BO3 to BO4 units. So electrical conductivity we have measured using the impedance analyzer, NOAA control mech. So here you can see conductivity of glasses is found to be increased with increase in temperature of NAS equations. So which is plotted in this particular graph for all the samples. Then we have measured the conductivity at 573 Kelvin. And what happens here, conductivity is found to decrease with the addition of La2. Activation energy is found to be increased. So increase in conductivity is due to the increase in conductivity is assigned to the attributed to the it is very well related to the density. It is also very well supported by the decrease in activation energy. Modulus formalism. We have introduced here modulus formalism. So variation of real part of modulus m dash versus log of frequency. So here you can say at low frequency m dash, the value of real part of electric modulus is close to the zero, and it increases as we increase the frequency. M dash increases with the increase in frequency. So it is due to the relaxation process. The imaginary part is plotted. Imaginary part is plotted here, and m dash max, this peak m dash max, it shifts towards higher frequency with increase in temperature. For higher temperature, that is 673 Kelvin, it is here, and for low temperature 423 Kelvin, it is here. So we have taken here the center of relaxation peaks, that is FP, peak frequency it is also called, and we have calculated torque using the formula torque equal to 1 by 2 pi FP, and that is plotted. Then we have plotted that torque with 1000 by T. So calculated value of whatever the relaxation time we have calculated, okay, it is plotted against 1000 by T, and from this we have calculated what is that EA activation energy torque. We have compared that activation and DC activation energy and EA relaxation time activation energy. So it is found that there is a close match between those EA DC and EA torque, indicate that charge carriers have to overcome the same energy barriers in both conduction and relaxation processes. So we have introduced the scaling here. The conductivity scaling. So here you can see conductivity scaling. So here you can see the conductivity scaling data for all the temperatures, all on a single curve, master curve. And here in second graph, you can see imaginary part of electric modulus, that is m double dash max. So here also it is superimposed on a single curve. So it confirmed that as data falls on a single master curve, dynamic processes occurring at different frequencies need almost the same thermal activation, and which confirm that the processes and conduction mechanism is temporary. So then we have done the compositional scaling here. We have introduced. So here you found, see, data fails to form a single master curve. There is no single master curve. So it is confirmed that conduction mechanism is compositional dependence and not the temperature dependent. Then we have studied dielectric properties. So dielectric constant, you can see variation of dielectric constant with frequency, and here variation of dielectric loss with frequency for different temperature. So you can see there is a decrease in dielectric constant and dielectric loss. So it is attributed to the electron hopping and bond energy implications in the net polarizations. So conclusion, we have confirmed that the glass samples were found to be amorphous by XRD analysis. So various functional groups were confirmed by FTR study. Density and molar volume is found to be increased. We have calculated different physical parameters which correlated with the which supports the density and molar volume values, electrical conductivity, found to be decreased with the addition of rare earth oxide. That is, we have used lanthanum oxide as a rare earth oxide. Scaling, we have done the conductivity scaling and compositional scaling. So we have proved conduction mechanism is independent of the temperature and it is compositional dependent. So dielectric constant and dielectric loss is found to be decreased. Then there is a fairly good correlations among the physical parameters, FTR, electrical conductivity, and dielectric properties for the glasses studied in the present work. So these are the references. Thank you. Thank you very much.
Good. Good, Vikrant. You have done nice work and take hard efforts to complete this and nice presentation also. Very patiently you have presented your work. Okay. So any questions? Vajpayee sir, any queries? So, 1 minute, I have just go through your title.
Okay. I'm sorry, I was muted. See,
Yeah.
when you are putting the lanthanum in your sample, if you see the relaxation is not changing. But you have not measured the width of the modulus peak.
Okay.
We are not sure whether the process is it is a single relaxation, but whether it is divide type relaxation or non-divide type of relaxation. This is one thing that is not clear.
Okay.
Then second thing, the conductivity data are not DC conductivity. They are the AC conductivity data. You are taking from the impedance.
Yeah.
Okay, so actual DC conductivity data will tell you whether the absence of glass former by putting the more lanthanum is actually creating some sort of crystallinity in the material, because the small crystallinity will not be seen in the X-ray, but it will be seen in the impedance result. If some sort of crystallinity is there, then your DC conductivity will not follow the Arrhenius plot. And second thing, if you see carefully the modulus spectra, the real part of modulus is not getting saturated. It's not the sigmoidal curve. It's getting up. So that means the hopping motion going from the long range conduction process into the localized conduction process towards the higher frequency side, this process is not complete. That means the conduction process or the barrier, as you are claiming, is of the same height. That barrier may change at higher frequency. So this is my observation. That saying that it is temperature independent processes, composition dependent, obvious, it's clear. And that is again a indication that in different compositions you have the different percentage of glass former. So that also tells that probably at higher concentration of lanthanum, it is going towards crystalline phase. Not completely crystalline, but some degree of crystallinity. This is.
And again, there is another question. I think it's not related. What is glass? Is it related to spin glass behavior of compound? I think it's a little bit confused. Okay, but can you give the answer, please? What is glass? Is it related to spin glass behavior of compound?
No, ma'am. Glass means it is an amorphous material.
Material, yeah. Yes, Shoaib, actually your question is wrong. Spin glass is another concept and glass is amorphous form of material. So it's not anyway related to spin glass. Spin glass is the magnetic behavior of material. Okay.
But I think Professor Acharya, the student must get the answer of his query. Like in glasses, we have the only short range ordering. There is no long range ordering. Similarly, in spin glasses, the electron spins are frustrated. They are random. The spins are not ordered. So when the spins are showing the amorphous behavior, the material is called spin glass.
Spin glasses, yeah.
Of course, the theory is different, the analysis is different, but the analogy is there.
Yeah,
this is the spin frustration. in certain compounds.
Yeah. And in glass, actually, ordering frustration. And in case of spin glass, there is a spin frustration. Sir, thank you, sir. Thank you. You are very, in few means, in very good word, you have explained this. Briefly, you have explained this concept. So I think, Shoaib, is it clear to you what is the main basic difference between glass and spin glass? Means what is analogy between that two words? They are not anyway related, but there is a analogy given the name, spin glass and glass. Now again he asked another question. There is a increase in transmittance La2O3, concentration in transmittance versus wave number. How can it be understood? He say that, have you understood? With the increase in transmittance with La2O3. In transmittance versus wave number curve. In transmittance versus wave number curve, you have shown that the transmittance increases with La2O3. How can it explain? How can it be understood? Yes.
Actually, there assigned the bands, the transmittance.
Versus wave number curve. Go to your that curve. And you have shown it's the wave number.
No, actually, this is not the transmittance in optical region. This is in the IR region.
Yeah,
so
yeah.
IR spectra, but this is the presentation. There is no change in the intensity.
No increase. Yeah, he just comparing.
Yeah, he just comparing.
Yeah.
So there is no question of transmission. Yeah.
Yeah. It's not that it means whatever presentation he made, na Shoaib, it's not show that the transmission versus wave number is increases with La2O3. It is just present. Okay.
Bands.
So yeah. Okay. So I think almost all questions and all the lecture in this session we completed. Thank you, Vikrant sir, and thank you, Vajpayee sir, because you have throughout the day you have copied us and you have asked the good queries to student also. It make more interactive. So thank you very much. And I say our today's session, total session is over. Only after this session there is a post session, but actually what happened, we have get late. So we have cancelled this poster session and we have displayed all the poster on the conference website. If you go through the conference website homepage, you can see that there is a folder is given. Okay, poster section folder is given. In that poster section folder, if you click, then we divide all your poster in 3 files. Okay, Excel files. You can download that 3 Excel files and then you can just click the now made the YouTube link of every poster. So you directly open that YouTube link and you can observe that poster. Okay, so we cancel this poster session and you just join the NSFD website. Everybody have the website address. So you just join the NSFD website. You there you will get on home page you will get that respective folder. Okay, so thank you very much all the participants and our panelists. You are throughout the day you are with us, you have cooperated, and our today's session are also we are well going. So all the experts give the more informative lectures. So thank you very much, and I declare that today's the third day of this conference is over, and we will join the last day of the conference on 30th Jan. So good night, thank you, and again join tomorrow's early morning because tomorrow is the last date, and we complete officially this session. And 3 to 4 is our valedictory function. So it's again there is some interesting thing in the valedictory function for you. So thank you very much. Good night.
Good night.
Good night. Thank you.
Thank you.
Thank you, sir. Thank you, sir.
Thank you.